we'll flag it if you go over or getting close. It's not a big deal if you don't meet the exact line mark. So
Cool.
easy breezy.
Cool.
All right.
Yeah. Well, you have a book on Vegas as to your myself, right? Geographical visibility column. Yeah, that's why you different. Even with the variability of these, you can build a line different and click it. But it's all massive difference. It's must have ways to check the same. Because actually you're not building.
I'm doing better.
Different ways, you have smarter different
Physically present with the whole thing. You just be like, wow, that is like stuff. Good morning. Oh, I'm sorry. Good morning.
How you doing?
Sorry?
Everything well?
Very well. I think we are all citizens and congratulations because we didn't bother to assume one.
I double checked on no
It
one.
was amazing. I was shocked that we were able to do that.
Don't worry, we got a good team.
But thank you for setting us up for success. That's why we were able to do it.
Thanks, Alex.
So did you accept your lunch? Yes. Very much.
Yeah, you guys are wasting.
I just gotta grade the.
Yeah.
No.
That's a thing.
If it's a bespoke suit, then this one isn't, but if it's bespoke, you can do this last one, that way you show the constitution.
I'm learning a lot. Yeah,
Figure that out.
I got into 3 Ps from.
Oh, yeah.
Like if you have an actual handmade suit, these are, you'll have certain discounts which make it real.
Oh, I see.
You know, most suits like this one are like just ornamental.
I can actually find this because it's just one piece.
Interesting. Good to know.
It's a
Maybe I'll
whole,
be
it's a whole raffle. Yeah.
I'm gonna try to be more aggressive about adjusting the mic for people between speakers. That way, hopefully, if that doesn't interrupt the visual flow too much, so that people don't like kind of fall and it's like down here and I talk about others doing with it, or it's up here and it's much shorter.
Well, and that's kind of the thing is that like yesterday, when the mic's pointed like that, it's aiming right at the speaker. And then
So
that's,
it's like a conflict, right?
yeah, and then so you end up with a ringing. You're not going to get feedback, but
Yeah, that's part of the reason why we couldn't find it out 100%.
Yeah, I got it because it will be right into it.
yeah. But I think having the computer here is going to help force them to look here because now they don't have to train their eyes.
Yeah.
So, so you guys think we're going to start roughly on time?
I think so. Sure. We got
Alex has been.
No, let me get this. I'll get this under. I'm sorry.
You're good.
Yeah, you were correct.
It's
Do you need this from show? Already, this is just.
I might need one of those.
Kevin and Larry?
Keller, yeah.
Carolyn, sorry.
Do you need call straits? Do you need call straits?
Yeah, Daniel was
Yes.
for this.
I am co-host with that. I'm DJ and I'm like. You
I don't, yeah.
cameras, so you can see what's going on.
I can make you both. I can make you both. Both
That's-
co-hosts.
That would be great.
Yeah.
No, if you need to step.
So, Caroline, when you're ready, just make sure your mic is hot, and I'm going to be listening for you to tell people. All right, everybody, take their seats. We're getting ready to get started. Hand up.
I think I've been liking this one.
So one thing I did today is I increased all of them to the same level. So
Oh,
now they
perfect.
should all perform exactly the same. You can have a preference if you want to. We're gonna change them out.
Every day.
I'm gonna change them out every day, but
You can
if
still
they did
set
work
steps.
for.
Gotcha.
Okay, just go to a mic if you need us. All right.
Like I thanks.
Check 1 2 off.
Check 1 2. Oh, that's good.
Least James Stanley is getting too aggressive with his. Yeah, there's another one, geez. Test, 1, 2, test.
Okay, Rob, I am in the webinar.
Host.
Also, folks in the room, we're going to get started in about 2 minutes. If folks in the room could find their seats, please, we're going to go ahead and get started in just a couple seconds. Y'all, well, welcome to the Software Conference Day 3. Congratulations. It is our last day. I know we've gone through a lot of different presentations and we've learned a lot in just a couple of short days. And so a couple announcements. This morning, we have 4 different presenters and then we have 3 different sessions today. We're going to be wrapping up a little bit early today, but expect the same type of format as we've had the last 2 days. One announcement that I wanted to give for folks who may not have noticed this morning, DC is in an air quality unhealthy level. And so if you have sensitivities, just wanted to let you know in case you didn't see, just to take any caution that might be necessary. So to kick us off, super excited to introduce Dr. Brent Eldridge, who is an electrical engineer at the Pacific Northwest National Laboratory. And this morning, his presentation is titled Integration of DER Aggregations and ISO Scale SCUC Models. So thank you so much for joining us this morning and take it away.
Enable his microphone at the podium. Okay, can you hear me? Okay. Yeah, thank you, Caroline. And yeah, so she gave the longer title. The short title that I opted for the slides is SCUC DER integration. And this is work that we've been working on at PNNL. So I'll acknowledge my PNNL team members, Jesse Holzer, Ron Schweitzer, Rabiat Sednan, and Abhishek Samani. Next slide. So this is a DOE Advanced Grid Modeling AGM project. It's a 3-year project that we are in the first year for, so we're kind of starting it up. We have collaborators at the Stevens Institute of Technology and INREL, and some advisors from MISO, and then Mads Almasaki, who's at PNNL and UVM. And I also want to thank Gurobi for providing the solver software that we are using in the project. Next slide. So kind of the background and what a lot of people have been talking about in various talks throughout the past 2 days is FERC Order 2222. So what 2222 kind of two main things that it does is one, it allows aggregators of smaller resources to aggregate together and participate as a single resource in ISO software. And the idea is that they would be bringing together very small scale resources like, AC, load control, water heaters, demand response, rooftop solar, and these sorts of things. So aggregating them together, the second thing that it does is it lowers the minimum capacity requirement down to 0.1 megawatts or 100 kilowatts of total capacity needed to participate in the market. Next slide. Last year at PNNL, we wrote a little review or white paper on some of the potential impacts that 2222 would have. And what I've listed out in this box is just some of the software impacts that would be relevant to people at the conference. Our collaborators at SIT, they're looking a little bit closer at the oscillatory dispatch and pricing and then multi-node aggregations. What I'll talk about in this talk is one of the solution speed, self-commitment, and distribution system conditions. So kind of the idea with solution speed is these could be a large total number of resources in the SCUC model, but small in terms of capacity. Even though it's small in terms of capacity, it adds a lot of non-zeros to the optimizer, and that could slow things down. Similar thing happens today with virtual bids. Self-commitment is kind of like a self-commitment or self-dispatch is a way that you could avoid some of those solution speed slowdown issues, basically by sidestepping the centralized optimizer and having DERs participate by making their own decisions about whether to commit themselves or how to dispatch themselves. And then the distribution system conditions is important because a lot of these resources are connected at the distribution side. And so there's kind of a modeling gap between where they're connected and where they actually provide energy to the transmission grid. So that's not modeled in the SCUC software. And what we're going to try to do is see whether or not those various power flows in the distribution side could affect the amount of power that's actually provided by a DER aggregation. Next slide. Very simple outline for this. So I'll have a few slides of the methodology that we're using and the formulations, and then go through some preliminary results. Next slide. Okay, so on the formulation side, kind of one of the big issues that we're trying to deal with is so supposedly there's supposed to be this big influx of DER aggregations, and they're not really participating in the market today. So how do you come up with economic data that they would submit into the market? The way that we've approached this is we have a somewhat generic aggregator offer and dispatch model. So this is written in the slide kind of in text, but we have this model that's formulated with 3 different DER types. So we have demand response, solar, and storage. And the objective of the aggregator is going to be to minimize the total dispatch cost. So the cost of DER demand response is based off of a utility function calculation that we've come up with. So I'll discuss that in a few slides. Solar cost is comes in as a time series of capacity throughout the day, but all of those costs are 0. And then the storage cost is a basically price arbitrage, profit expectation. You negate it so that it comes out as a cost. And I'll describe a little bit more about that on slide 8. The constraints for these resources are fairly straightforward. So demand response is kind of the more complicated one. Complication being that you're, instead of measuring DR capacity directly, you have load, and DR is the difference of that actual load to some baseline consumption. The utility function that I'll describe in a bit is a function of what this load comes out to be. Solar is this time series of upper bounds, and then storage is essentially the standard storage model for optimization. So there's a round trip efficiency and state of charge management. These constraints, by the way, these are only seen by the aggregator, and the aggregator's job is to look at them in some way and then submit a simplified offer to the ISO. Next slide. So first, we have demand response, and there is some participation of demand response resources in the markets today, but it's not huge. And what we wanted to see is, if there's this huge influx of demand response, how are they going to bid into the market? And this is something that we don't have data for. So we developed our own methods for figuring out what that bid offer might look like. What we've done is we've implemented a Cobb-Douglas utility function with constant elasticity of substitution. And that function, so it's kind of shown on the right on the screen what it looks like. Details aren't too important, but those XIs are products. So there's 24 products, one for each time period. And then there's a 25th product, which is kind of the catch-all, all other consumption going in that the demand person would consider. So even though we have 24 energy products, it's not exactly defined as the consumption in each period. What we've done is created various bundles of energy consumption. So we're slicing consumption across time and kind of reorganizing it in a way. And the idea for this is that we want to be able to model what we've been calling boomerang effect. So the idea is demand response might be dispatched in one period, and that loss of utility by the consumer needs to be compensated by additional demand in other periods. So if we go to the next slide, I'll describe more about that. Okay, so we have we want to have bundles that are sliced across time. And as I said before, the idea of these bundles is, let's say that you dispatch 1 kilowatt hour of demand response in one period. That might be compensated by 1.2 kilowatt hours of additional load in the neighboring periods, or it might be compensated by even more additional load in periods that are farther away. So it's kind of as each period gets further away from the period that you're dispatching demand response, there's more compensation that needs to be, compensation becomes more and more difficult to get. So what we're trying to get to is basically this blue matrix square in the middle of the slide that is showing a matrix, values of a matrix that they have each row summing to 1 and each column summing to 1. And the idea is that this way, no matter how you slice and reallocate demands, at the end of the day, you're still coming up with the same amount of demand. And then the decay across periods is kind of consistent. So there's a consistent rate of loss per period. And then there's a little bit of boundary effects at the top and bottom corners that make this matrix a little bit more difficult to just write out right away. So to calculate this, there's a tridiagonal matrix that we've come up with. You can parameterize it with just one parameter B, calculate B based off of this rate of decay per period, and then you invert the matrix and you get out this really nice smoothing matrix. What this does for us is when we put that into the Cobb-Douglas demand function on the bottom right corner, we have a graph of the marginal utility of demand before and after demand response is called. And so in the blue line on the bottom, in each period, we assume the value of demand is the same. And then after demand response is called, we get the orange line. So you have much higher value of demand in that period that you're calling demand response. And then that also translates to higher value of demand in the neighboring periods, which is when you would have compensation for the demand response. And you can't compensate demand response, early in the morning or at midnight. Next slide. The second more complicated resource model is the storage model. So again, this is fairly standard storage model. It can be used either for batteries, which is the main use, but we're also looking at it as an alternative to this demand response model. We do that by adding a per period leakage parameter to model the same effective substitution across periods. Now, how do you take that storage primal formulation and turn it into a offer function? I think that can be a very complex question. So you're trying to get into, what are the opportunity costs of the storage? How does it view risk? How does it view forecast uncertainty? So we've started off with a very simplified, naive approach. So essentially, this is a kind of a two-step loop. You start off by calculating a forecast for prices. So we're using a convex hull approximation for SCUC to get the price forecast, and then using that price forecast to solve kind of an optimal storage dispatch over the 24-hour horizon. So that's kind of step one. And then step two is you go through each time period, you loop over the possible quantities that you could provide in that time period. And then you do this cost minimization. Once you figure out all of the cost for each quantity in that time period, you fix the quantity at your optimal level that you figured out in step one. And then you go back and or then you go forward in time and figure out the cost curve for the next time period. So at the end of this, you have various cost curves that might be different for each time period. And yeah, so what we basically have, if you're looking at comparing using this as demand response, this is kind of a primal formulation of demand response, and then the other one is kind of a dual. Those are kind of in a vernacular sense, not directly or strictly true. But yeah, so the idea is that one is explicitly modeling the amount of energy that could be substituted across periods, whereas the utility function is kind of an implicit value function approach. Next slide. So when we tie all this together, what we are doing is using it in a simulation of the day-ahead and real-time market. We're using Prescient, the Prescient software to do this, which is developed from various national labs. The main SCUC solver engine within Prescient is Egret. And what I'm going to show on some of the next slides is a comparison of, keep the previous slide, is a comparison of the schedule following behavior of a DIRA versus profit following. But yeah, so essentially we start the Prescient software. It has these plugin functions that are fairly easy to use. So it was a interesting learning experience figuring out how to do that. But before Prescient starts the first day-ahead market, we solve a relaxed SCUC. We get this LNP forecast that goes into this DIRA offer generation module, and then returns to Prescient, solves the day-ahead market, solves prices, and then it goes into SCED, which will dispatch the whole system, including the DER aggregations. We take that DER aggregation schedule and then we disaggregate it into the various DERs. And we use that to determine what the DERA is actually providing. So then this goes through the loop over the 24 hours of the day. Next slide. So I'll share some of the preliminary results now. Next slide. So first, we'll look at solution times. We are testing this right now on the RTS GMLC system. This is a system with 73 buses, 120 branches, and about 150 combined thermal and renewable generators. The way that we're testing solution times is we're starting with 0 and then gradually adding more and more DERA aggregations to see what's the trend. The DERAs that we're adding in this case, they're a mix of demand response, solar, and storage. So they're, component wise, capacity, total capacity is 0.3. I think the time series max capacity is a little bit less than that. And so this is being submitted into eGRIT as a thermal generator. For the initial runs, once you add 150 aggregations, they're basically doubling the number of resources in the model. We already have a 21 times increase in the solution time. It goes from 10 seconds to 200 something. And then once you go further and further, adding 1,000, 2,000 generators, it as a percentage increases quite a bit. And once you get around the 2,500, some of those cases are taking more than an hour to solve. So this is results on just a laptop computer. So it's kind of preliminary. These are first take, and we need to dig into them a little bit more. Next slide. This is the results of this schedule following versus profit following analysis. And these results were somewhat interesting. So as you go from left to right, we have aggregations that are combined of 100 kilowatts of demand response and 100 kilowatts of solar, or 250, 250, and then 500, 500. So going up to 1 megawatt total capacity. When you have the smaller aggregation, it starts off not even being picked up by SCUC, which was interesting to us. So, most of or half of the capacity is coming from solar, and it's bidding in at free. So there's a question there of why isn't it picking this up at all? Then as we increase the total capacity of the aggregation, the dispatch following and SCUC, the schedule following and the profit following behaviors start to get a little bit more close together. So that's kind of this inefficiency. Next slide. And then what we also have is some oscillation, which is, looking at this boomerang effect. It seems to be working in a sense that we can actually see behavior of demand response being dispatched and then compensated right away. Right now, it's not a very good way to have that boomerang effect because it's just creating noise, but it's good to see that it's actually working. Next slide. This is kind of the next steps that we have to do. So we're integrating the simulation with GridLab-D through Helix, and we'll be using this to look at these questions about how do the power flows on the distribution side affect what's actually getting sent up to the transmission system. Next slide. All right, so this is conclusion. I'm pretty close to the end. And so I think the main thing that I wanted to press upon everyone is that, we're trying to figure out how to get these aggregations to bid economic parameters into SCUC. And that's kind of a difficult question because there's not a whole lot of real data for us to go off right now. So we have a few different methods that we've proposed to go about that. And we've also have some preliminary results, at least, that show that indeed the dispatch or scheduling of these smaller resources is fairly difficult. And so kind of one of the questions we had is whether a large scale centralized SCUC is a good solution for dispatching small resources. And maybe it's not, maybe self-scheduling could be part of or a more efficient result, which is kind of interesting to find when that happens. We have various things planned for future work to increase the sophistication of our model. So you can read that there. Next slide is just some resources and references from some of our prior work. And next slide, and that's the end.
Thank you so much. Round of applause. All right, so now we're going to open it up for questions. Folks that are joining us online, if you have a question, please put it in the Q&A. And to start, is there anyone in the audience with a question? All right, see a couple.
Thank you very much for the great presentation. I have two related questions. The first question is, do you include the distribution network feasibility or congestion in your model? Second question is, I think on maybe the third slide, you mentioned that the aggregator or the resource doesn't have to be at the same node. So if they're not at the same node, which you only know the total, how do you know when in the network constraints where to put that injection or withdrawal in your model?
Yeah, so we're just doing single node aggregations right now. So straightforward. Once we expand to multi-node, we'll use distribution factors at first, just static distribution factors. And that's kind of the task of our SIT collaborators. They're looking into methods to do that more effectively. For your first question on the distribution feasibility, we're not considering it right now. And there's a few different, so yeah, without more I don't know exactly where your question was headed, but there's kind of two considerations that we have with that. So one is when you added DER to the distribution network, where should it go? Because potentially there's some interconnection process there to ensure that it doesn't affect distribution flows too much, or that it's at least feasible. And then the second level is when you've actually dispatched your DERs. Right now, we're not measuring that directly until we have the GridLab-D and Helix integration completed. But the idea would be our first step is look at how often do distribution side constraints maybe prevent individual DERs from being dispatched, so the utility might override it, and then what is the net effect on the feeder load?
Thank you.
Do we have a question in the back of the room?
Thanks, Brent. This is great work. Nikita Sengal from EPRI. I had a few questions. First question is around the increase in the computational time. How were these DER aggregations represented within the SCUC model? Was it just through offers, or did you have some binaries to included?
Yeah, good question. Thank you. That is definitely a very important thing for us to start comparing is, right, like you could offer in this model under the standard generator model, and it has all these complicated binary constraints that get added into it automatically. And maybe the solver goes through pre-solve and notices none of these are being used by the resource, and we can ignore those constraints. Maybe it doesn't. Or we can submit it as basically different slices of a renewable generator and a load, which will all be convex. Or we can look at possibly creating a new offer format or resource format in eGrid. Right now we're using the first approach, so it's all being bid in as a traditional generator. It has all of these extra constraints. None of them are kind of included in the market or in the offer. So it has no startup cost, no minimum runtime, none of these things.
So what kind of non-convex constraints? Because I mean, demand response, batteries, and renewables, all of them seem to have convex constraints in the traditional SCUC, right? Like, so what did you include for the time to have then increased essentially?
Well, yeah, so it's bidding into the market under a model that has constraints for those, but it's not using them.
Okay. I guess it's not using them as well because of the MIP cap and the size of the resource. So that plays a big role as well.
Yeah, we're also interested in, what's the size of the MIP cap that the SCUC uses and how does that affect the DER resources?
Thank you.
All right, Daniel, we'll take an online question.
Yes, Alva, if you could unmute and ask your question.
Hello, can you hear me?
Yep.
Yes.
This is Alva Svoboda at PG&E. Sort of following on the previous question, I wanted to clarify what you were talking about in terms of the increased time to run. Were you talking about the sum of the portion that's involved in generating the offer and then the SCUC run, or were you just talking about the SCUC run itself?
Yep, just the SCUC run.
Okay.
Yeah.
So I understand why your results would be, that doesn't really seem to me, in my mind, that doesn't make sense. So you're just essentially adding resources to that look like conventional resources to a SCUC problem. So the salience of them being DERs is not clear to me. I mean, it seems to me that you could have come up with the same result just by adding a bunch of thermal resources to a SCUC problem. And that would not be very, but that said, I'm not trying to, put down your results, because I think it's a really interesting market model, actually, where I would see the generation, this idea of generating the DERA offers using a relaxed problem is a really interesting way to try to integrate these resources into the market model. But I just I'm a little suspicious of that increased time to solve in the SCUC based on how you've described it.
Yeah, no, I agree. I think it's interesting so far. We haven't dug into it enough to know exactly why the increase is happening, other than, initial guess being that we're basically feeding SCUC a whole lot of data that it possibly doesn't need. And it's taking time to sort through it. But
okay, well, that's an interesting result too. Thank you.
All right, I think we, unfortunately, to keep us on track today, are going to have to go to our next presenter. So thank you, Dr. Eldridge. One more round of applause. Okay, and next we have Dr. Mojdeh Hedman, who is an assistant professor at Arizona State University. And today she will be presenting current voltage AC optimal power flow for unbalanced distribution network. Thank you
very much. Good morning, everybody. So this presentation today is a little bit different than what we saw earlier in this conference, mainly because it is focused on distribution system. But, as we know, as resource mix are shifting more towards distribution system, as the question came during the previous talk as well, it's very important to capture the characteristic of distribution system and plan for our resources accordingly. So here I will be presenting a novel AC optimal power flow model for distribution systems that captures the details of distribution system modeling. And then I will talk about two of the applications that we explored, but then I will connect it back, if we have time, a little bit to the market discussion as well. Next slide, please. So this work has been funded by ARPA-E. I want to focus here in one thing, that current voltage AC optimal power flow model was developed originally by Dick O'Neill when he was at FERC. He was the manager on the project that we had, and in one of the first quarterly review meeting, he brought up this conversation of why not to use current voltage formulation. We explored it and learned that it's a perfect fit for distribution system, and I'm excited to talk with you about it here. Next slide, please. So as I said, I will go just through first the formulation of the current voltage AC optimal power flow, and then two of the applications. Next slide, please. Next. Okay, so as you probably know, the distribution systems have a lot different characteristics than transmission network. To start with, the untransposed distribution lines, three-phase, two-phase, single-phase feeders, and there's now a lot of DERs, a lot of voltage fluctuation, highly unbalanced system with limited sensor and visibility. So we're talking about large amount of resources DERs, but we have limited visibility, right? So that's nerve-wracking, and it's important to capture those details to be able to make sure that the system is staying reliable. Next slide, please. So to just give you an overview of what we are doing, after I will be presenting the current voltage ACOPF model, I will be linking it to two generalized application in advanced distribution management systems. The figure on top is showing various modules of ADMS, topology processor, state estimation, DER scheduling, workflow optimization. And what I will be doing using this current voltage ACOPF model is I'm lumping some of these functions together and presenting two. One of them is simultaneous topology processor state estimation, and the other one is DER scheduling with workflow optimization. Next, please. Next. So just an overview of that what is this formulation doing? You know, we are all familiar with basic current voltage formulation on a line. However, when we are talking about distribution lines that now we have mutual impedances, we have to capture the effect of current and voltage on each phase on the other phases, if we want to be accurate, right? So to be specific, the formulation that you see here is linking the current to voltage across a distribution line. But as you can see with underlying variables and circle parameters, which are self and mutual impedances, current in one phase of a distribution line is not only dependent on voltages on the same phase, but also current and voltages of other phases. As the current voltage formulation in distribution, just current voltage formulation is a linear formulation, that property enables us to capture all of these details of mutual impedances by simply, again, expanding that linear formulation to a more detailed representation with mutual impedances and admittances, as you can see here. All right, next slide, please. While the current voltage formulation of AC optimal power flow is modeling the flow on the line as current, therefore that relationship is linear. Still, when we come to the node, at the secondary node, now we are dealing with measurement of load, which is power, active and reactive power, and that relationship is non-linear, of course. What we are doing here, we are using first order Taylor series approximation to linearize that equation. But I want to take a pause here and say that as they connect it for transmission system, I want to argue that it's very better to model the flow on the lines as a linear relationship, because that's what is linked to the all through the network, versus when the nonlinearity is isolated at the end nodes, the impact of linearization is isolated at that location, and it won't impact the overall system modeling as much. Okay, so again, to recap, the relationship on the lines is modeled as current voltage formulation linear, but then when it comes to the end node of the distribution system where DERs are, where load are, that relationship is non-linear, and we approximate it with first order Taylor series approximation. Next slide, please. So we tested this on an actual utility feeder, primary, secondary. Part of the results that I will show is only on primary, and part is on primary and secondary together. There are over 2,000 single phase nodes in this system. Next slide, please. And also should mention that there is a high penetration of DER in this system. So in fact, in one of the cases that I will show you, there is over 200% penetration of PVN injection back to the transmission system. All right, so just to validate the algorithm itself, before looking into the detail of the application of it, what we did is that we compared the result of distribution system modeling with a powerful result of OpenDSS, EPRIS tool, and also then compare it with this widely used linear distribution ACOPF model, Lindis-Fellow model. Lindis-Fellow model includes a lot of assumptions, and our model goes a lot more detailed, and I will talk about some of those in a few minutes. So what you see here in this table, the red numbers are the important one because we are validating all of these algorithms against OpenDSS to show the accuracy of distribution system modeling alone. Okay, so what I want to bring to your attention is for the convex IBA-COPF or nonlinear IBA-COPF, either in comparison to Lindis-Fellow model, as you can see, because we are modeling the mutual impedances, all the shunt elements, all the details of the distribution system in details, the model that we are proposing, IBA-COPF, current voltage ACOPF, is way more accurate in comparison to Lindis-Fellow model, particularly on reactive power as well, too, because the Lindis-Fellow model ignores the shunt characteristic, capacitive characteristic of the lines as well, but we model all of the detail of it. Next slide, please. Okay. So also the table was aggregated result. Here you can see the voltage, magnitude, and angle and accuracy again compared with OpenDSS. The top figures are comparing all the models. The lower figures are showing exactly just IBA-COPF with and without shunt modeling. One thing that we have captured here is that if we look into the these results, you can see that actually the capacitor characteristic modeling on distribution line is having a big impact as well in the accuracy of voltage calculation, both magnitude and angle. As if you look into the y-axis of all of these figures, you can see that in comparison to OpenDSS, basically our algorithm is almost matching it with very minor amount of difference from what OpenDSS is calculating. The two sets of figures on the right are showing the voltage angles. We are not showing Lindis-Fellow model angles here because Lindis-Fellow model has a very rough approximation and is not really capturing the voltage phasor to the detail that it should be for distribution system model. Next slide, please. All right. So far, to summarize this part, we developed an accurate AC optimal power flow model for distribution system, and we tested it on a utility feeder data, compared the accuracy with OpenDSS and Lindis-Fellow model. Now I'm going to get this algorithm and run with two applications that I want to show here. Next slide, please. So the first one is this simultaneous state estimation topology processor for unbalanced distribution systems. Next, please. Okay, so I went through some of the challenges about distribution system. Another challenge that I want to focus here, the sensors in distribution networks are very limited. The micro PMUs usually not widely utilized, so there is that, and the status of switches are not usually telemetered to the control room, which is terrible because we don't know, like, if there's an outage, which switch is open or not. So what we are proposing here, we got the formulation that I just showed you, and I'm expanding it to a state estimation, but also the topology processor to identify the status of switches correctly as well. Next slide, please. So overall, what it does, it gets the measurement data, mainly smart meters and PV meters, and substation measurement. That's all. No measurement needed at the feeder level in the length of the feeder, just those smart meter and substation measurement, and it identifies the status of switches and the system states accordingly. Next slide, please. Okay, so a little bit again touch on the formulation. The formulation in the middle is the current voltage formulation that I showed you. For the status of switches, now we are modeling a binary variable associated to the status of that switch. And then we are multiplying that binary variables associated to the terms that are related to that phase. So basically, if it's a three-phase segment of the line, we have binary variables associated to a status of each of the switch in each phase. And all of that is represented in this current voltage formulation. The lower equation, current voltage equation, the red ovals, those are the binary variables that we are modeling. So again, binary variables are for all the three phases represented on formulation for even a single phase. Next slide, please. Again, testing this for this particular application on the primary of the distribution system, we are modeling all of the measurement noises from all sorts of the devices. Currently, we're considering only one pseudo measurement, micro PMU measurement. I'm saying pseudo because there's actually no micro PMU in this particular feeder, but we are assuming there is one at the feeder head, modeling it, running power flow, modeling noise on it, and say that that one is available. I'm confident that even if that's not available, just a SCUC measurement at the substation can do this job. And then the rest of the measurement are the smart meter measurement with noises that are associated to that. And the smart meter measurement and PV measurements are actually the field measurements that are provided to us from the utility. So these are, we're just using the exact same snapshot with the exact measurements that they provided. Next slide, please. So there are 5 cases here that we will be looking at. The first case is considering a normal condition. There is no outage, but we are considering all the limitations. A smart meters only are measuring active power, no reactive power measurement is available. And the second case is that plus missing data of 246 out of 342 primary nodes AMI data are missing in the case 2. So let's go through the result of case 1 and 2 first. As you can see in this first, second and third column of the table, you can see that the topology of the network with 100% accuracy is identified correctly. And the maximum voltage magnitude and error is also very small, which means that the state estimation results for distribution system is small. Roughly it takes about 20 seconds to get this solved in a regular student laptop. And then case 3 and case 4 are cases that there are outages. Case 3, there are 2 outages, a small zone. Case 4 is a large outage, and case 5 is where there is a large amount of error in the measurement from AMI. That can be because of the device itself or the communication from AMI to the utility location. In all of these cases, you can see that the accuracy of the topology processor is almost 100%, and the state estimation results are very accurate. For case 3 and 4 that are outages, the accuracy of a state estimation is just slightly under 100%. That case I will show you in the next slide as well. Next, please. That one, a little bit of variation in the accuracy of estimation of the topology is because of the switch that is before the outage. That status is not identified correctly. And the reason is that there is no current on that, basically. And the model is not able to differentiate that. But also it doesn't make any difference because there's no current in there and there is no impact on the control of the feeder. Next slide, please. All right, so 2 of these cases, case 2, which had a missing data, and case 4, which was a large outage, these are the results for a state estimation. And this system, as you can see in the y-axis, this state estimation is pretty accurate for all of these cases and the 2 samples that are shown here. Next slide, please. All right, to summarize this part of the presentation, we developed the current voltage AC optimal power flow model, expanded it for a state estimation problem, combined it with a topology processor by modeling binary variables for the status of the switches, use the smart meter data and substation data to have observability in the distribution system. It's very important because it brings the situational awareness and reduce the outage management duration. Next slide, please. And next. So this one I will be talking about now, that IV ACOPF model and the application for DER scheduling, again in the distribution system, but I want to also show you the volt-var optimization and management from inverters in the distribution system. Then I touched a little bit based on how another work that we have done related this to the wholesale market as well. Next slide, please. All right, so with high penetration of DERs, there's a lot more voltage fluctuation happening in the distribution system. The traditional volt-var control devices are not necessarily able to cope with all of these variations. So what we want to do here, we want to identify the dispatch of DERs, active and reactive power, in a way to provide voltage support for the distribution system. And if, of course, is expanded, we can look into beyond that as well, but mainly the focus is feeder level voltage support and local voltage support by inverters. Okay, next slide, please. So if we just solve the scheduling with ACOPF and don't model any volt-var characteristic of inverters or any other volt-var controller devices, we will get the figure on the top left of this slide, where the reactive power, active power can be any of those dots based on the different locations of the DERs. However, in fact, based on IEEE standard 1547, where DERs are required to provide voltage support or support for the feeder overall, the volt-var characteristic of inverters looks like the curve on the right. There's a deadband zone, reactive power injection, reactive power absorption. So now I want to first, in this slide, I only want to focus the importance of capturing this characteristic when we are doing volt-var optimization or distribution, DER scheduling, right? The figure on the lower left is showing that if you do model that characteristic of the volt-var controller within distribution ACOPF, DER schedules would be the figure on the left where it is following the volt-var characteristic of the inverters based on 1547. Next slide, please. So, next, please. On that. So what we are doing here, we are actually capturing this characteristic of the volt-var controller within the IVACOPF, but we are also taking it one step beyond that. In the volt-var controller curve that you see there, the circles are the parameters of the volt-var controller curve, which within IEEE standard 1547, it can be set as a default value or it can change within an allowable range, right? So what we are doing here, we are getting these variables in the circle and modeling them as a variable and deciding the set point of the volt-var controller in order to achieve the largest amount of hosting capacity. Okay, next slide, please. And this is the, we model the constant associated to 1547, and this table shows the allowable range based on the standard. Next slide, please. Okay, so we look into the default setting of 1547, optimized setting, and also if when there is no volt-var controller. If there is no volt-var controller in this particular feeder with high PV penetration, there is overvoltage issue. But when we then optimize the volt-var, consider the volt-var controller and optimize it, the voltage or voltage issue in this case is mitigated, and in both cases voltage is within the acceptable range of ANSI standard, but co-optimized setting is doing a little bit better. Next slide, please. I won't go through the top figures, but just the lower figure. The lower figure is showing you how the volt-var controller characteristic is shifting after it is optimized, right? Basically, the short message here is that because we are identifying the set points of the controller, given the operating condition in the system, the controller can be adjusted, the volt-var controller can be adjusted such that it can provide more reactive power support and voltage support for the feeder as well as the local level, right? So the blue curve is showing how the group characteristic of the volt-var controller is changing and shifting. Therefore, the inverter is where needed, the inverter is able to provide higher amount of reactive power support. Next slide, please. So interesting thing, if we limit the voltage based on ANSI standard at 1.05, basically for management of voltage in the distribution system, there are two ways we can control it with the reactive power in the distribution system, adjustment from all the source of resources, or alternatively, there can be active power curtailment due to the higher R2X ratio in the distribution system. That also helps with the voltage management as well. So what we are observing here, the summary, I will just talk about the last column. When we do optimize the set points of the inverter controllers, we are able to get better reactive power support from them to achieve the voltage management. Therefore, less need to PV curtailment. Okay, so and the cost saving and the last column is showing that. That when we optimized it, we were able to manage the voltage with reactive power support from the inverters and have less active power curtailment. Next slide, please. We check the stability of the controllers, and that's what it's showing here. Next slide. So to summarize this, we Model the voltmeter controllers within IVAC optimal power flow, optimize the set point of the controller. We're able to utilize more of the PV injection, active power injection as a result of this better voltage management in the distribution system. Next slide, please. We do have a US provisional patent on this technology. We are in the process of tech to market transfer now. Next slide. And here's a list of publications. I want to touch base on one last item here that wasn't included in my presentation, but what we did is that we also used this capability of the distribution modeling and voltmeter controller modeling and developed an algorithm based on machine learning where based on the substation measurement, we can qualify or disqualify how much services from DER should be should be scheduled from the DERs to not violate distribution system limits. Okay, because the back engine is accurate, we were able to achieve that accuracy. And with that, I conclude. I would be happy to answer any question.
Thank you. All right, folks online, if you have a question, please put that in the Q&A and we'll start taking questions in the room.
Hey, nice presentation. This is Swaroop from EPRI. Probably I missed, but so is the IV ACOPF, is it a one-step solution or is it an iterative process?
So we're using Taylor series approximation for the nodal power balance constraint. Our observation was that a lot of time the first iteration or second iteration is accurate, but the only iteration is to update of the Taylor series parameters.
I see. Okay. And like, have you compared like the time between OpenDSS and your model? I know LinDist is like one-step solution, but with less accuracy, have you compared the time?
Yeah. So OpenDSS is a power flow tool, so we didn't really compare it in terms of time. But with LinDist,
Microphone. Can you just speak on the mic? Thank you.
Yes, thank you. So OpenDSS is a power flow tool, not OPF. So we didn't compare the time with OpenDSS, but we compared with LinDist flow model. It takes longer than LinDist flow model, but like I think it's LinDist flow model in this system solved in 1 second, and ours was in 3 seconds when it is only ACOPF model, not the topology processor. But one thing that is that if we have a better approximation of the Taylor series parameter, which can come from OpenDSS itself, then the simulation, it would be just one shot basically, and would be way faster, comparable to LinDist flow.
Okay, What one last question is, so since you're linearized approximating, do you consider all the components available in the or in the distribution system, like shunts or some other devices, or is there some devices you need to compromise?
No, we're modeling capacitor banks and everything detailed.
Okay, thanks.
Are there any online questions?
No. One just came up. Alva.
Hello. This seems like really exciting work. I wanted to ask your slide about the state estimation, the distribution state estimation indicated that you could have a fairly degraded quality of data and still get a good state estimation. At least that's the way I'm not this is not my area, but I was wondering if you'd sort of evaluated where does the tool break down? I mean, how bad can the data get before this does not work well?
So we did model missing data on like 246 out of 340 nodes, aggregated AMI nodes. So I think it's pretty robust to that. One thing that additional item that I'm interested personally to look into, what if like we just use the select smart meter location, so we don't have to deal with the communication bandwidths or anything like that. But yeah.
Thank you. Exciting work.
Thank you.
Hi, I'm Jesse Holzer from Pacific Northwest National Lab. I have questions about the formulation. So I guess the first one is with the QV characteristic curves. What kind of model does that result in?
So there are 5 different zones, and we model 5 binary variables for each zone, and then we said the model has to choose only one of them. We added a constraint to say that only one zone can, of course, be chosen. but otherwise it's a slow, it's linear. The binary variables are identifying because there is breakpoints of where it can be. Yeah.
Okay, so there is no I don't know, no quadratic expressions there?
No.
Okay, that's interesting. Also, in the beginning of your talk, you said that the IV formulation with a linearization at the nodes of a linearization of the power it tends to have a lower error. Or I didn't quite understand what you said. Are you saying that it has a lower error than a linearization of, say, a standard, a cosine sine formulation, basically?
Correct. So the thought is that because the linearization is isolated at the end nodes, the impact of that errors doesn't get accumulated as much, as opposed to when the linearization is happening on the lines, and then there is an error there that impacts the power balance basically on all of the nodes. So that's the thought process. But beyond that, also, if you use like power angle, power voltage formulation, because that's a highly nonlinear formulation, modeling the details of like mutual impedances, for example, on distribution lines becomes very complex. Versus simply because it is linear, IV formulation is linear on the line, modeling that complexity is much easier. And then, of course, there is that claim of isolation of the nonlinearity at final nodes.
I think that's plausible. Has that been demonstrated numerically that there's a lower error?
No,
okay.
we have not demonstrated, but just theoretically, yeah.
I would be interested to see that.
Yeah.
Are there any other questions in the room? Or any online questions?
No.
Awesome. Well, thank you so much. Another round of applause. So next we have Dr. Yu Lin, who is a postdoctoral associate at the Massachusetts Institute of Technology. And today she will be presenting, and her title is Empowering Electricity Markets Through the Distributed Energy Resources and Smart Building Setpoint Optimization, a graph neural network-based deep reinforcement learning approach. Thank you.
Thanks for introduction. Good morning, everyone. My name is Yolin. I'm a postdoc in the Laboratory of Information and Decision System at MIT, and I'm working with Dr. Alden Bottrod. And next slide, please. And it's my I'm really happy to introduce this essential topic that stands at the intersection of energy efficiency, intelligent design, and AI technology. And today my topic is about the grid integrated setpoint optimization in smart buildings. And because our focus today will be the overview of energy efficiency and also the need for demand flexibility. And I will introduce the concept of building setpoint optimization, and then I will introduce the framework of our proposed optimization algorithm. And later, I will introduce a case study based on MIT campus building for this proposed optimization model. And then is a summary of today's topic, and after that, I will take questions. Next slide, please. And as we can see in this figure, that the global energy consumption has been increased exponentially in the past years. And because of this increased demand, there will need this increased demand has led to the escalating carbon footprint, and also the mounting environmental concerns. Therefore, this increased demand has created an immediate requirement or need to improve the energy efficient technologies, especially in the energy consumption or in building sectors. And demand flexibility which is the capability for adjusting energy usages in response to the electricity prices or grid signals to improve the energy efficiency is a potential option to improve our energy efficiency usage. And however, in order to improve the demand flexibility, we will need the technology we will need the energy efficient technology such as the technologies used in smart buildings to improve this flexibility. And can we move to the next slide, please? Yes, as we can see here, the buildings accounts for a considerable proportion of energy consumption worldwide. Around 40% of energy worldwide is consumed by buildings. And in both commercial and the residential sectors, among all the CO2 emissions in the building sectors, around 30% to 40% of the CO2 emissions are from the space heating, cooling, and also the ventilation system. As we can see in the buildings in New York, the buildings carbon emission accounts for approximately 70% of the city's total CO2 production, and this number is not slowing down. So it's essential to do something in the building area. Next slide, please. Yes, although we have a good awareness of the energy conservation, but there is still a large energy waste in the building sector because of the outdated equipment, the bad insulation, and also the unoptimized usage in the buildings. So, and the traditional building control strategies are not optimizing the energy usages in buildings. This is the main reason for the energy waste in the traditional buildings. And in future, for the smart building concept, and the buildings can respond to the grid signals or prices that changes and all the price changes and automatically adjust their energy usage. This will enable the buildings to reduce their energy usage and also keep some levels of thermal comfort. And if we can see from the figure in the right, and it shows that from the traditional commercial building, there is a high demand in the noontime. And but if we use the grid interactive building with energy efficiency, such as load flexibility, we will be able to shift this load based on the grid price or other signals that and the smart building will be able to shift the high demand to the low demand times, or will reduce their usage based on the high price signals. And the next slide. Yes, the traditional here I show an example of the traditional traditional building control strategy, and the traditional building control strategy are based on the static or constant set points. If we see the right figure is an example for the MIT campus building set points example. Usually for the set points in the rooms, we only have constant set points in the daytime and also the nighttime, and based on either it's holiday or not holiday. So so no matter whether we have classes in this classroom, or whether we have some researchers or people in the labs or some other areas, we will keep these set points and that means even there's nobody in this room, we will have to maintain this set point. This is a lot. This results in a lot of energy waste in the building. And so that's why we want to develop a optimized temperature set point in the buildings, and by responding to either the electricity prices or energy consumption. In the next slides. Yes, this work is based on our project at MIT to design a scalable occupancy weather-driven system that can automatically adjust the temperature set points in the campus buildings, such as the rooms, office, also as well as the labs. And this is a 2-year project, and we are in the first year to develop a day-ahead, that is already day-ahead set points optimization algorithm. Our primary objective is to adjust the set points of each room, each space in each building separately, instead of regarding the whole building as a one value set points. So because as I said, even in one building there will be some occupancy in specific rooms, but there will be no people in other rooms. So that it makes no sense if we regard this building as as one set point. So our objective is to optimize all the set points in this building, in each room and each space. And so the next year objective is to do a real-time adjustment based on the some comfort feedback from the occupancy in the room or labs, and will scale up to the whole campus buildings. Next slide, please. Yes, this is the framework of our a optimized day-ahead temperature set point prediction system. And first, we will need the set point profile and the weather profile, and also the building information such as the in-room indoor temperatures in the classrooms, labs, or the zones. And based on this information, we need to develop a zone model that will estimate the dynamic temperature changes in the future 24 hours, and also the energy consumption in the future 24 hours. And based on the estimated energy consumption, and also based on the forecasted grid prices, we will be able to calculate the energy cost for this space cooling and heating in this building. And so in this framework, we will need to develop forecasting models and as well as the optimization models in this whole system. Next slide. Yeah, here we review the forecasting models, both in classic methods as well as the modern learning methods. As we can see here, the classic forecasting models includes linear regression, exponential smoothing, and also autoregressive moving average models, as well as dynamic linear models. And the more modern machine learning models based on neural networks are developed in current years. And most of these methods are widely used in both industry and also the academic research. And because our project has tested the classic model based on autoregressive and moving average, it has the advantage of the easy calculation and high interpretability. But its problem is that it doesn't have the ability to deal with high complexity in the future nonlinear system, and also it's very difficult to get high accuracy based on different scenarios, such as different buildings or different rooms. And therefore, we use the neural network models to deal with the high nonlinear patterns in the set point optimization problem, and also the forecasting problem. And the neural network models will be able to scale up to a more complex scenarios based on other buildings. Next slide, please. And here, as we said, we need forecasting models as well as optimization models. So here we review some optimization models in the control, optimization and control models that are widely used in the industry. One of them is the model predictive control. And this model has a high accuracy in short-term scale, and it has low computation cost if it's based on linear approximation. And another widely used optimization model in the industry is the linear optimizations. But this optimization has disadvantage because it is not able to deal with a high nonlinear problem in future optimization. And another is the reinforcement learning model that is based on the currently famous neural network structures, and it has the ability to deal with high complexity scenarios and also highly nonlinear problems. And but the problem is it will take long time to train this model, and so we will deal with this problem in our optimization. Based on the comparison of the classic optimization models in both industry and academic, we choose the reinforcement learning. But we developed a model predictive control optimization in the past work, and as I said, the problem is not able to scale up to a long term and more complex scenarios. So we are developing reinforcement learning control models in this optimization. And as I said, because our requirements in this project is we want to scale up to we want to use this Setpoint optimization model in the whole campus. Is around almost 100 buildings, and in each building we will have 50 or 60 rooms or zones in each building. So finally, we will need to optimize around thousands set points in this campus. So we will need the algorithms to scale up to a more complex scenario and deal with the non-linearity and also the complexity. So that's why we've choose the reinforcement learning model. Next slide. Yeah, as I said, we based on the comparison of the classic models and also the modern used machine learning models, we choose the forecast model based on the graph learning, and also we choose the optimization model based on the reinforcement learning. The whole framework of this algorithm is that because, as I said, in the existing researches, either in industry or academic, we regard the whole building as one set point, and but the problem of this existing strategy is that we didn't consider the occupancy of each room, and we will still have energy waste in if we regard the whole building as one set point. Another is if we optimize each room individually in this building, we will not consider the thermal exchange between different rooms, because this will be a large impact for the set point optimization. So in our solution, we will regard the whole building as a graph. How we can extract the graph is that we have a floor plan of this building, and we have the connections of each room and also the shared zones. Based on this floor plan, we will extract a graph, and that's the spots in the graph will represent each room or each zone, and the connections between the spots will represent the thermal connections or thermal exchange between different zones. So based on this model, we will be able to consider the thermal exchange and also consider the information in each individual rooms in each building, and to optimize the set points of each room, each space in this building. And yes, as I said, we based on the floor plan, we can extract the graph, and based on the graph for each zone or a spot, we will have the information for the indoor temperature or the outdoor temperature and solar readings, as well as some other indoor informations, such as occupancy and others. And so yeah, this graph will be used in this graph convolution neural network and to do the forecast of the thermal power consumption, and also the information we need for future optimization, such as the occupancy information. And also this graph will be used in the reinforcement learning. This is a graph-based reinforcement learning optimization, because in the past or existing reinforcement learning model, they didn't consider the spatial and temporal informations in the building set points, and especially the thermal connections and the zone connections between different rooms or labs in this building. Here, based on the graph, this is the main. This is the main essential idea for this optimization based on the compared with the previous work. And as I said, for the reinforcement learning or other learning models, the problem is that it will take a long time to train this model. And because we are optimizing the day-ahead set points and based on hourly resolution, that means we will need to train this model in less than 1 hour. So, but traditionally for the reinforcement learning, we will need hours to train this model, especially when you expand this problem to a more complex, more buildings. And here we use the transfer learning to solve this question, to solve this problem. Because for, as I said, for traditional machine learning, we will need a lot of historical data and a long time to train. But for transfer learning, we can pre-train this model based on historical data records, and also transfer this model to new scenarios, such as the future death site, or train this model based on one building and transfer this model to other buildings and do a continual training in a very short time. So this based on this transfer learning plus graph learning and plus reinforcement learning model, we will be able to solve this problem. Next slide. And the input information here is the weather data, and also the people counter data for counting how many people in this room. These are the sensors installed in specific rooms. And also we consider the class schedule in this campus, and also the indoor information such as temperature set points, temperatures, and also the CO2 in density, and also the grid price from the ISO, and also, as I said, it will be imported to the forecasting model, and also the forecasted information will be used in this optimization. And the objective is to minimize the thermal load over the total electricity cost. In the next slide. Here we show some results of the thermal power estimation, and we want to show the importance for the occupancy data, because in some rooms we installed the sensors for counting how many people in this room, but in other rooms we have the CO2 records which can indicate the occupancy. And but in more rooms in our current status, we don't have any sensors to indicate the occupancy data. So we test the flexibility of our estimation model with and without occupancy data. The accuracy showed that it has reasonable results even with limited data. Next slide. And here is the set point optimal set point estimation results with the occupancy. Here in this figure, we can see that the blue lines are the people count results in the room, and the optimized set points is shown in the purple line, and it shows that if we don't have any occupancy in this room, we will not. We will. I mean, we will have a new set point optimization result instead of keep the constant set points. This will reduce the thermal consumption in this room, and this is a result for one room. We will our results will optimize all the rooms in this building. And next slide. And here is a result for the optimal set points estimation with the price signal. As we can see, the price signal, the forecasted price signal is shown in the yellow dashed lines in the right y-axis, and we can see that during the 17 o'clock, from 17 to the 22 o'clock, the grid price is very high, and based on this signal, we will optimize our set points to be a larger range. So we'll so less power consumption will be consumed. In the next slide, please. And in summary, we in this project we develop an automatic set point optimization tool for either commercial or residential buildings in response to occupancy or electricity signals. And our future steps will consider the grid carbon intensity signal, and also also quantify the thermal comfort based on the set points, and scale up to the more buildings in the campus, and also will explore its capability for providing operating reserve in the electricity market. Thank you.
Thank you, Dr. Lin. Are there any questions for Dr. Lin in the room?
And Zizou from Argonne National Laboratory. And so for your control and strategy, so what is the frequency you do the control decision? It's every day or every hour? What's the
it's every hour update for the future 24 hours.
For the next 24 hours?
Yeah.
Okay. So next question is about the temperature forecasting. So at what spatial resolution? Is building level, room level, or larger?
It's the room level.
Oh, so you do the temperature forecasting for every room?
Yeah, every room.
Okay.
And because we want to adjust the set points of each room in the building.
Okay.
Yeah.
Thanks.
Thanks.
Any other questions in the room?
Alex Rutkiewicz, Newton Energy Group. Do you have an estimate of the savings in energy relative to the status quo if you implement this technology?
Do you mean how much we can save for the energy consumption? Yes, we estimated for one room, because for that room we have the measurements of the power consumption and also the thermal consumption based on the set points and the temperature. And for that room, the reduce the percent is 10% based on our optimized set points.
10%.
Yeah.
Wow. Okay. Thanks.
Yeah, because this is a lot, because as I said, in some rooms there are occupancy, but in other rooms there is no occupancy. In our traditional set points strategies, we remain the same set points no matter we have students or we don't have students in this room. So that will waste a lot of energy.
Okay. Thanks.
Now we're going to turn to an online question.
Joseph Franz, if you could unmute and ask your question.
Yeah, just wondering, did you also consider any of the demand response programs, either bidding the extra capacity in or those kind of monetization efforts?
We haven't considered the do you mean how much capacity we can bid in the electricity market?
Yeah.
We haven't considered this problem yet, because our primary objective in this project is that we want to reduce the carbon emission. First, this is our first our objective. But because as a aggregator, we can optimize the set points based on the price signal. We haven't considered how much we can bid yet. But the reason is MIT has our own power generation, and most of the electricity are consumed are provided from our own generation. But because we talked to the power plants people at MIT, they said if the grid price is lower than our cost, we will consume the grid electricity. So that's why we want to develop this problem, but we haven't considered how much yet. But the whole capacity, energy consumption for the MIT campus is around 25 megawatts.
Thanks.
We have one more question online. Pedro. Let's see.
Hello. Hi.
Hi.
Thanks for the presentation. So my question is, what is the learning algorithm that you used for the reinforcement model?
Actually, we use two learning models. One is based on the WDQN, another is based on the PPO. Because the first one is a discrete optimization, and the second is a continuous optimization. And we want to test both of the algorithms.
And do you remember how many steps you have to train the model for it to converge? Like, did you have to reuse some of the data that you had, or you had enough steps to have it converging?
Do you mean how many steps I can for this algorithm will converge, right?
Yeah, I mean, how many steps you had to run the training of the algorithm for it to converge?
It will
stabilize.
Yeah, it will be more than 500. 500.
300.
Yeah.
1,000 or 300 steps.
It will be more than 500.
Okay. Okay. Thank you.
All right. Are there any other questions in the room? Oh, here we go. One more.
Yeah, thank you for the presentation. This is Bing from the Chester Institute of Technology. So I have two questions. The first question is related to the energy consumption. So I was wondering, you only consider terminal like devices like air handling units, or you also consider like also chillers and cooling towers?
Yeah, we're considering the chillers and also
the cooling towers.
Yeah.
So you consider like all the energy consumptions related
Yes.
to. Okay. The second question is related to the heating part, space heating. So you always mention like that's electricity cost, right? But for the analysis part related to heating, most likely we consume gas. So how do you handle this part?
Yeah, because for the heating problem, we convert the thermal load to the power consumption based on some equations, and yeah, this will be a equation from how much electricity we will consume.
Okay, so it kind of essentially convert this kind of natural gas consumption to electricity.
Yeah.
Okay. Yeah, thank you.
But this is an approximation.
Yeah.
Yeah.
Okay.
All right. Thank you so much.
Thank you.
For the folks that are with us in person, I'm going to direct your attention to your nearest TV. We have a virtual presentation by Jubeyer Rahman, who's a PhD student at the University of Texas at Dallas. And can we do a sound check before I read your presentation title? We can't hear you if you're speaking. Can we do a quick sound check to make sure we can hear you in the room? Okay, we can't hear you. Let's see. On your side, can you just double check to make sure that you're not muted or that the audio is connected correctly? It's not showing on our end that you're muted, so it might be on your side.
Yeah, I'm not seeing his microphone as being hot.
On our side, it's not showing that your microphone is on.
Jubeyer, do you want to disconnect and reconnect? Yeah, Caroline, he was actually in here before the conference and we did a mic check. So
okay,
let's give him a second just to disconnect and reconnect.
Thanks y'all for bearing with us here.
We were getting his video, so I think that would go first, but it just stopped right. We're also not on the same Wi-Fi that's here. All right, Jubeyer, can you do one more test?
Yeah, can you hear me now?
We can hear you, but you're very quiet.
Okay.
Okay. All right, we can hear you, and whenever you present, if you could just try to project as loudly as you can. His presentation today is titled Multi-timescale Operations of Nuclear-Renewable Hybrid Energy System for Reserve and Thermal Product Provision. Okay, now it sounded very muddled. It's still pretty muddled on our end. How is your internet looking right now? Because we can hear you. Okay, well, we just lost your audio again, but maybe could you try presenting without your video on in case it's a bandwidth issue? All right, if you are speaking, we cannot hear you anymore. Rob, are you seeing his mic on right now, or does it show audio?
Yeah, I'm guessing from what I see, he's struggling with his internet connection because his microphone pops on briefly and then it dies down.
I mean, he's done the best thing he can in terms of killing his camera. But
Is it possible to call in using the Zoom number?
Yeah. So what I don't know is if Jubeyer can hear us. If you can hear us, what would be the best thing to do? So Jubeyer, if you can, I have a copy of your presentation that I can run. And if you go to the original Zoom invite, there should be a telephone link that you can try. And then if you do that, then we can promote you, and I'll follow along with your slides. So if you can hear me, what I would say is go to the original Zoom invite that we sent you, and there should be telephone call-in information. And if you use that, then, like I said, I can bring up your slides for you and then advance them as you need.
So for folks that are in person, it looks like he's left and he's going to try calling in, hopefully, fingers crossed. Thanks for bearing with us.
Because yeah, that's true. Be like optional.
Caroline, do you want me to load the karaoke slides in the meantime?
I say, I promise y'all we practice these things, but I think things come up and you can only prepare for so much. So thank you.
So Caroline, I still see Jubeyer in the panelist. So my concern is that he may not have heard what I told him. I know, Alex, you tried to send him a message, but
At this point, we've emailed him and messaged him, and there are 2 phone call-in listeners, but we can check right now to see if one of those is his.
so one thing I'm going to do is I'm going to go ahead and remove Jubeyer from, let's see here. Let me remove him so that he can rejoin. Oh no. Okay.
And for folks that are joining or hanging on, we're still trying to get a hold of our next presenter. Thank you for bearing with us. Okay, so Rob, it does look like he's phoned in. If you could promote the number ending in 82.
All right, I just sent him a link or a request to join.
Or actually, as co-host, can you allow that number to talk? And just to see if, because he doesn't actually have to be a panelist.
Okay. Jubeyer, can you now speak? You should be unmuted on our end.
It was 3082. Oh, there we go. Yep, now we can hear you. Brilliant.
Oh,
Yeah, I'm really sorry about the hiccup. I'm not sure what's going on actually. So should I share my screen and go ahead, or like you will run it on your side?
Yeah, so right now I've got slide 1 up.
All right. Okay, so I'm Jubeyer Rahman. So I'm a PhD student at the University of Texas at Dallas. So today I'm going to present my work on multi-timescale operation of nuclear renewable hybrid energy systems for ancillary reserves and thermal products. So can you move to the next one? Okay, so the motivation comes from that there has been widespread installation of the hybrid energy systems over the past few years, and especially the evolution of power-to-X technology actually has made it possible that other than storage, we can produce a lot of different diverse products from those hybrid energy systems to increase their revenue. So basically, in my work, I'm going to present two actually tasks that we have been accomplished. One is actually we'll be exploring the potential of the tightly coupled nuclear renewable hybrid energy system in a multi-timescale energy and grid ancillary service market while serving a district heating network. And another one is actually we'll be exploring the benefits of electrolytic hydrogen generation from the hybrid energy system, energy systems. Next one, please. So here is a brief outline. So we will be actually starting with the hybrid energy system description and district heating network. And then we'll be discussing a little bit about how multi-timescale simulation framework has been set up for this hybrid energy system simulation. And then we'll discuss about the operational strategy. It will be followed by the system description of the electrolytic hydrogen generation and the process modeling and how that has been integrated into the multi-timescale simulation framework. And eventually we'll conclude and discuss about a little bit about the future work. Yeah, next one. So what we have done is actually we have taken the NREL 119 bus test system, which is actually a renewable intensive test system. And we have attached this hybrid energy test system on the bus number 12, and there has been some reasoning behind that why we have done it. So basically, what we have done is actually we have done some simulation on the unit commitment model while we are placing those hybrid energy system package at different places, and found out the best converting results and in terms of production cost and convergence speed. That's how we have picked up the location. So our hybrid energy system has mostly 3 components. One is a nuclear plant, about 320 megawatt, and the wind plant around like 150 megawatt, and there is a district heating network of 100 megawatt thermal. So we have, in terms of the ancillary services, we've limited our scope in looking at 4 types of reserves: the regulation, spinning, non-spinning, and replacement. Next one, please. So the district heating network, to feed in that, so we have actually chosen a gas-cooled reactor, a small modular reactor. The model is like GTH-TR300. The thing is that what it releases the waste heat at a very high temperature compared to the regular pressurized water reactor. So for that we don't need to change the Carnot cycle. So we don't need to raise up the the cold temperature so that we can we don't have to inversely impact the efficiency of that cycle of that nuclear plant. So what we have done is actually the auxiliary electric consumption of that district heating network, we have ignored that. And we have considered a very simplified district heating network. Next one, please. So here is how we have integrated this district heating network in our multi-timescale simulation framework. So we have been used the phase-step simulation framework developed by NREL, so which is actually a multi-timescale simulation framework. So on the right side, you can see that the time step settings, and on the the left figure, you can see that we have used a open source tool called Panda Pipes to include our district heating network model. So what we have done is actually we are just getting the lumped thermal dispatch from the the optimization model of this multi-timescale simulation framework of phase-step. and we are actually just verifying that, whether our results make sense or not. Next one, please. Yeah, so actually, basically, what we have done is we have explored different types of optimization model to find out which one serves the best for this hybrid energy systems. So we have this net reserve export maximization model, which you can see here, and we eventually using that one. There is this sequential optimization model. So we have just made the injection from the hybrid energy systems as a free variable, and we find out that what the maximum contribution that it can make on the system. And then eventually we have looked at this augmented epsilon constant model, which is actually a multi-objective optimization model. In fact, what happens is actually the multi-objective optimization model performs the best. But in terms of the computational expense, the net reserve export maximization model is the best performing one. And since we'll be performing a very long simulation for 1 day, so we have chosen that one. So what we have done is actually we have deducted the reserve cost from the objective function to try to encourage that ancillary service export from that a hybrid energy system. Can you move to the next one, please? Yeah, so here is actually brief overview of what the results we have got. So here is the ancillary service reserve profiles that we have got. We see that there has been a significant contribution from the hybrid energy systems, especially for the nuclear is contributing to the replacement reserve and the spinning reserve. Whereas we don't see any participation in the regulation reserve, and we have actually made the wind plan to provide the regulation reserve. So if we look at the thermal load profile and how that has been satisfied, we can say that except some few hours in the month of January, that has been mostly satisfied. So the next one, please. Yeah, so here is actually the locational marginal price profile in different time scales. So we can see that when we have peak hours, the locational marginal price goes up, and as long as when the hybrid energy system is injecting more power, so the locational marginal price is also going up. Can you press the next one? Yeah, so here is actually what we are seeing on the Panda pipes, the pressure and temperature profiles. So we can see that we are within a very reasonable range. Next one, please. Yeah, so here is actually a comparison of how the revenue comes out. So in most of the time it's very much close to the phase one, which is without that HES system, without the district heating network. So, but when we are using this reserve maximization from strategy, it kind of enhances the revenue from that HES system. Next one, please. Yeah, so the next work actually kind of explores that how this low temperature steam electrolysis and high temperature steam electrolysis is used to produce hydrogen and how that benefits the operation of the hybrid energy systems in the multi-timescale framework. Next one. So we have modeled the LTE process. So we have this electrolyzer, fuel cell, and the hydrogen storage. So we have modeled this electrolyzer, and fuel cell is electrolyzer is a dispatchable load. Fuel cell is actually a regular generator whose generation kind of depends on the inventory of the storage. Next one. Yeah, here are some regular constraints that we have considered: the capacity constraint, ramp up, ramp down constraints, minimum up and downtime constraints. Yeah, next one, please. Yeah, next one. Yeah, here are actually some constraints regarding this small modular reactor. So we have considered this, the ramp up constraints, ramp down constraints, and capacity constraints. And eventually the dispatch is kind of restricted by the storage inventory for the fuel cell and the electrolyzer. Actually we don't implement the the initial and the end hour equality constraint for the storage because it's not like a regular battery storage. So there should not be any like charging or discharging depreciation for that. Next one. Yeah, so that's how we have actually included that on the multi-timescale framework. So the dispatch of the electrolyzer and the fuel cell are there, as you can see from the framework. And there are some actually parameter specifications that we have chosen from some existing literature. And since we are using a small modular reactor, we have chosen some of the specifications from the new scale specification given on the online. Yeah, next one. Yeah, so that's how we have actually modeled this HTSC process. So, the whole process is kind of complicated. So we are kind of adopting the parametric optimization approach. So we have just run a dynamic model in the Diavola software. And then we have seen the relationship and try to linearize the relationship between the nuclear output and the turbine steam input. And we got the, the relationship from there, and we just kind of like integrated into our constraint formulation. Next one. Yeah, so this we need to calculate that how much steam we are bypassing because the HTSC process requires some steam to be fed in. So we are kind of like try to build a relationship between this electrolyzer consumption to produce hydrogen and how much bypass steam it is consuming. So it's kind of like non-linear, but we try to kind of like use a piecewise linear relationship to model that one. So I'm going to make sure that one single segment is activated a single time, and that's we are kind of like building the relationship between the steam bypass quantity constraints with the generation of the electrolyzer. Next one. Yeah, so here is kind of like some profiles, the dispatch profiles from the nuclear, wind, fuel cell, and electrolyzer. So we can see that in the most of the time they are pretty similar, but the HTSC is kind of like restricts the dispatchability of the nuclear plant. So we see more like less headroom there in the day-ahead cycle, and so we can see that the electrolyzer is operating more on the real-time cycle because there are some the more headrooms for it to operate on that for the additional hydrogen that it gets on the the inventory. So if we look at the LMP profile, we can also see that the peak hours it goes up, at the off-peak hours it goes down. So it kind of explains that why the pattern of this electrolyzer and the fuel cell is operating. Next one, please. Yeah, so here is kind of like how the bypass steam is bypass steam flow is going over the hours. So you can see they're mostly in the day-ahead cycle and the real-time dispatch cycle, so it's mostly flat. Whereas in the real-time unit commitment model, so it's kind of like showing some variability. That's because of actually the headroom is there available for the electrolyzer to operate. So if we compare the renewable energy curtailment, we can see that the HTSC is more restricted in terms of operation. So it has higher renewable energy curtailment, whereas the LT process has a less amount of renewable energy curtailment. So we can see that overall the revenue that comes higher for this HTSC system because the fuel cell operates more there, so it earns more. Whereas the SMR actually generates more revenue for the LT process. Next one, please. So in conclusion, so yeah, I mean, what we have done is actually we have tried to find out, what the additional benefits that this facility for generating hydrogen and this district heating network can bring into the picture. Potential future will actually involve modeling the nuclear plant in more details, like considering some of the real life characteristics like xenon poisoning modeling in that model to get a complete picture of that. So I would like to thank you all for having patience. And if you have any questions, I'll be happy to help.
Thank you. I think we have time for one, maybe two questions, if there's any questions in the audience. And if you are joining us virtually and you'd like to ask a question, please do put it in the Q&A. I have one question in the room for you.
Yeah, thank you for the presentation. It's great, like eventually we can get you back. So my question is related to hydrogen. Can you comment on like the benefits of the hydrogen? Because right now it's kind of a hot topic. So essentially here, you use hydrogen as a kind of a storage system, right? Can you comment on the kind of future benefits and also kind of applications? Because if we have hydrogen, it can also be transport in a long distance.
I'm sorry, can you just say the question just because I could not hear it very well.
Okay, can you comment on the benefits of hydrogen? So right now in your project, you consider hydrogen like kind of a storage system, but we know for hydrogen, it can be transported in a long distance. So can you comment on the future benefits of hydrogen?
Yeah, I see. Okay, thank you very much for your question. So the thing is that here we are just using the hydrogen as an arbitrage. So in the future, what we are planning to do is actually we will probably add some like hourly demand or like time specific demand for hydrogen, and we'll just to try to satisfy that. So we will try to include some hydrogen trading in our picture. So currently we are just using as an arbitrage, so to see that how much benefit it can add to the grid services. But rather than currently our scope is very limited, but eventually in the future we will try to integrate the hydrogen market in our electricity market and to try to calculate the revenue in total.
Yeah, thank you. Yeah, I can imagine there'll be a new market for hydrogen. Thank you.
So, thank you very much.
Thank you so much to our speaker. And with that, let's give one more round of applause. And with that, we are closing our first session of our last day here. As a reminder, we're going to start back up at 12:30. For H2, it'll be in this room. And for folks, I think I saw a couple new faces today, but for food options, there's Union Station that's that way. There's Phillips around the corner, and then down further on First Street, there's places like Roti and Potbelly. So enjoy lunch, and we'll see you back here at 12:30.
Yes, yeah, thank you.
You did. It was like
We're trying.
All right, we're back.
We didn't do anything.
Hi.
Hey, Monica, I don't think your microphone's hot.
No, it is.
Yeah, you're good.
I'm just not speaking. Sometimes that's everyone's preference. Anyways, welcome back from lunch, everybody. As everybody starts to file in, I wanted to thank you guys for sticking with us. We know it's tempting after lunchtime to go hit the snooze button, but we appreciate you coming back. And a quick reminder for our online attendees that you can enter your questions after this next presentation in the Q&A online. So our first presenter is going to be Fatnan Janpiwat, and that's a doctoral candidate from the University of Maryland, College Park, and Aalto University in Finland. They will be presenting on optimizing standalone battery storage operations, scheduling under uncertainties in German residential electricity market using stochastic dual dynamic programming. Take it away.
Hi. So I share my slides, or someone will play my slides from that side?
Yes, since you're virtual, you can share your own slides and have control of the progression there.
Okay, sure. Okay, give me one moment. Hello, I hope everyone see my slides. Can
Yes,
everyone
we see
hear
you
me?
and we see the
Ah,
slides.
Great. So, hello, my name is Fatnan Janpiwat, and this is a work between myself and my two advisors, Dr. Fabrizio Oliveras and Dr. Stephen A. Gabriels, and Dr. Fabrizio at University at Aalto Universities, and Dr. Gabriels is at University of Maryland, College Park. So let's get started. This is the topic about optimizing this standalone battery storage operations schedule under the uncertainties in a German residential electricity market. So agenda will be why we're doing these projects, and then we go over what is the our models, the stochastic duals, dynamic programmings, and we will compare that with the deterministic versions, which is the lit LP versions. And then we have the case studies about the Southern German residents, and we show the results and conclusions at the end. So background and motivations. So why is Abbey also knows that the battery storage could help for the demands, flexibilities, and integrations of the renewable energy into the grid. And the goal behind these projects is we want to have models that could learn from the environment and implement it as the open source software that could optimize the battery storage usage at the residential areas levels, such as we tend to deploy that algorithms that is less memory intensive and could run in like Raspberry Pi. And we select to use the SDDP because it's avoid the discretizations. Like for example, if we predict 12 hours into the futures and each hour have 3 scenarios, it's going to be 3 to the power of 12. So that could be 500,000 scenarios. And so the work is based on the STDP of the Para and Pinto that they use to approximate acoustical functions of the stochastic dynamic programming using piecewise linear functions to avoid the state discretizations. And I will show in the later slides what this look like. And the thousands extend these SDTP algorithms to be able to use in these continuous states and control variables. And we can map it, use the policy graphs. And the downward et al. Use extended further to have taking care of the uncertainties that is state-wise dependent in the objective functions, and which could have the coefficients or models as stochastic process. So talking about the resource objective and contributions. So we models our as battery storage plannings using the stochastic dual dynamic programming that could solve the linear multi-space programming in the context of electricity market. And we was looking to schedule the residential battery storage. And in part of the models, we have taken into account uncertainties in the electricity prices, PV generations, and demands. And giving everything together, we want to develop the algorithms that work with the limited computational resources. And for the part of captured uncertainties, we have the predictions models that's based on the 3 main predictions. So we use the exponential smoothings, we use the local level cycles, and we use the seasonal auto-regressions integral smoothing average, or SREMA. And we will use test with the case studies from this using informations of the residential households in the summer of 2016 in southern Germany. So what is the model look like and why we use the SDDP? I want to bring into attention that SDDP here is more like a Bender decompositions where we could divide this problems into the smaller subproblems without discrete states. So that could reduce the memory allocations and improve the overall solve time. And this is the well-established SDDP methods that have been used in the hydropower generation schedulings or similar fields in many years. And this is also provides us trackabilities. So what is the SDDP in the very high levels? So if you look on the left, that is, if you want to consider the stage, which is the X in the X directions. So if you want to determine the functions of the cost functions giving the stage. So if you want, you could discretize the X into smaller multiples, but that's going to take a very large number of X to capture all the range. But if you know that we use the piecewise linear approximations, you could capture just the border part of the linear, because we know, like from the simplex methods, that we move from the point of the boundary to the next point. That is moving from the large number of X to just a subset of X. to capture what we want to consider. So next is, this is a picture. So if you have a really large number, you can fix the first stage problems, and then you solve the sub problems. And at the end, you combine the solutions and see what is the best for the overall pictures. So how is compare with the linear programmings if you want to consider just like the SDDP subproblems versus the linear programmings. And the reasons why we bring the linear programmings into the picture is if we want to use the LP as the benchmark to see how much or how far off the solutions we got using the SDDP. So if you look on the right hand side here, there's the diagrams where the first decision point is, do we have access to the future uncertainties, or if we know the future data. So let's say in the context of the research, if we know like a perfect foresight, we could easily use the LP to do the optimizations of the better source scheduling for us. But in reality is that we would not have the perfect foresight. That's why we propose the SDDP approach, which is on the right hand side. So start on the right hand side. So if you don't have accessibilities to the future uncertainties, so what is the uncertainty in the future in this research? I consider the first uncertainties is the spot market electricity prices that we don't know. The second one is the amount of the previous generations of the solar panels. And the third one is the residential electricity demands. So moving to the next levels is we learn from the past. Let's say we use a 120 hours historical hours before the decision points for 5 days period informations. And we learn from that and we use 3 predictions models to project 12 hours into the future. What are those 3 models? The first one is the exponential smoothing. The second one is seasonal auto regressions integrated moving average. And the third one is local level cycles models. Why we use 3? Because it's allow us to be more robust to the range. And so those 3 predictions become 3 scenarios in the future. So that is how we captured uncertainties, and we map that uncertainties into the SDDP. So SDDP we learn from that uncertainties and makes the best estimations of the expected future cost. So moving to the left hand side, what if we use the LP and how's the LP result? So those uncertainties become known values because the LP receive perfect foresight and we optimize giving those as parameters. So at the end in the yellows is we compare 2 solutions together and I show at the result sections. Now, what is the SDDP in terms of what is informations inside the model? So in these figures, it shows the linear Percy graph in the SDDP models, where you start with the R is the root node, where the X is the state variables, where you start with the XR from the information from the root, get into the first period or the first node, and the XP that getting inside the like incoming stage, and the XP prompts that's the outgoing stage. So basically you learn what is for each stage you have information getting in and decision getting out. For that, before you make the decisions, you have omega, where omega is the uncertainties that you realize. So you have uncertainties of a price, electricity price, demands, and previous generations. And in each of those 3 parameters, you have 3 scenario each based on our 3 predictions models. So, and then once you know that, you learn to train your policies, and you can make decisions giving the best actions you could take. Then you calculate the price for that node, and you repeat the same thing if you move to the second stage, where you carry on the stage variables. So in our case, is we optimize the way we use the battery storage. So we carry on the energy LNG balance stored in our battery storage. So from hour 1, 2, and 3 period, so forth and so on. So what is the decisions we could make at this stage is we could inject or extract the battery store, the energy into or out from the battery storage. And we could see if we make the surplus in terms of power generations from the PV. If we make more of that, we could sell it to the grid, or if we don't have enough power, we could purchase from the grid. And that is the SDDP in the big picture. So in terms of the optimizations, what we want to do, so the net energy is here in the green. So let's say we have, what is the net energy in each of the period? So the energy that purchased is become the plus, the PV generations is a plus, and battery extractions is a plus. So just to subtract the energy out is the energy sold, demands, and battery injections. And this is the figures of our residential communities, where we have each house may have PV, and these 6 households have 1 standalone battery storage that connected to the grid. So in terms of the optimization problems, that we try to minimize the total cost to use the power. So if we have more power, we could sell back. If we don't have enough power, we could buy from it. So this is how the decision process is framed. So we try in each row is at we call it planning horizons. That is 12-hour planning horizons. And before that 12-hour planning horizons, let's say from row 1 or 1, we have 12 hours as the decisions we need to make. But before that, 120 hours, that is what we learn as the historical data to make the future predictions. So to connect from row 1 to row 2, that's you sort of move 1 hour ahead. So
Hey, Patanan.
yes.
I just wanted to let you know you have 5 minutes left.
Yeah. So going to what is the information look like? So this is the historical data that we use in 2016. The first figure here is the amounts of energy consumptions. The second one in red is the PV generations, and the third one in blue is the price. So we use C3s as the parameters, and this is how we predict the result. So we have in each color, the first color is the exponential smoothing, it's ARIMA, local levels, and the green is the historical data. So we compare 3 predictions models versus the historical data. And this is the information based on the raw data, and you can see the distributions of those predictions, and this is time series. So if they align together really well on top of each other, as you can see from here, that's a good predictions. And we have stage 1 to 12 of like how far we predicted out. So moving, that's for electricity price. We do the same thing for the electricity demand, and we do the same thing for PV predictions. So talk about the result. And we have 4 models, which is a SDDP with battery storage, SDDP without the battery storage, and the LP models with and without battery storage, just to benchmark. So result here is, you can see from here, we have those 4 models, and this is the distributions of the first stage objective functions values. So you make these zeros where you make some profit based on sending back to the grid. But if you see some positive number, mean you buy more from the grid. So in this picture, you see the distributions that pretty much align together, and we do analysis here. If you want to see the effects of the battery storage to how the battery storage affects the SDDP models. So we run the grouped, we compare the population's means between those two. And if you look at them together, you see that some of the battery storage has a better objective function values. And if we compare how the means differ or not between those two, so from here, between the models with and without battery storage, compare the p-values. So if you say 95% confidence, you can say that they are technically equal to each other. But if alpha equal to 0.1, they're not equal. So, but it's depend on how we see it. But at least you see that the objective function values from without battery storage, if you allow to have the battery storage, is improved about 32%. And this is just to show that these two, the LP versions and SDDP versions of the models that have the battery storage has, they operate the battery storage differently. And now if you see the SDDP models with the battery storage versus the LP models, which is a deterministic versions with the battery storage, you see if this is the objective function values. And the LP use like, this is when the LPs know the perfect informations in the future, they buy power more to store to sell it at the later price, at the higher price. So you will not, you see that with the LP, but you will not see that from the SDDP. And then we compare if this LP and SDDP or the means are equal or not. And you can say that they are more or less equal. And if you see how far off between the differences to the delta, which is a 30, and then the deltas become the 30% from the LP. So the differences between SDDP and LP is about 30%. And that's go down to our conclusions where this is the new variations that we use in terms of applications of the SDDP to solve as a multi-state linear programming. And we compare the SDDP with the LP models, and we found that it's about 30% differences compared to the deterministic LP. And we are aware that this magnitude of differences is huge, but we're still exploring the possibilities of enhancing our predictions abilities that could reduce these disparities between these two models. So that concludes our my presentations, and this is the reference that we use in these studies. And thank you very much.
Thank you so much. Now we're going to turn to the Q&A portion. Are there any questions in the room? Anybody online?
No.
Oh, great.
Hi, this is Jesse Holzer from PNNL. You motivated the use of SDDP by explaining how if you had a 12-stage optimization problem with 3 scenarios, 3 branching nodes in each stage, then you would have 500,000 scenarios. So I understand how how a 12-stage 3-branch model gives you a better hedge against uncertainty than a deterministic model does. Is there something like an intermediate stochastic model that might give you most of that hedge, but without so many stages? So for example, how would a two-stage model with branches just at the first hour, which I think is a common way of doing stochastic optimization, how would that compare in performance relative to a 12-stage model? And how much is the extra benefit that you get from having such an extensive scenario tree?
Thank you for your questions. So just to rephrase your questions, how's the number of stage and scenarios affects the performance? So first of all, this is still ongoing projects, and we used 3-stage just to sort of hedging, but also try to capture, because when we use the predictions models, and we can see from the means absolute errors, mean square errors, and each models is doing better. For sometimes one models do better in terms of price predictions, and the other models doing better in terms of the PV prediction. So we use 3s just because it's the simplicities, and we want to capture those plus and minus in terms of performance, and in terms of speed. And I'm sure that 2-stage, 2 scenarios may be more easily to solve, but we still need to explore more in terms of how much benefit or how far off the solutions is going to be. Thank you for your questions.
Great, and I believe we have one online question.
Yes, Alva, if you can go ahead and unmute and ask your question.
Hi, this is Elvis Svoboda from PG&E. Very interesting model. I'm coming at it. You appear to be showing a possible control model for a community-owned battery, essentially. And one thing I was curious about is how sensitive this kind of approach would be to discretionary use by members of the community. I mean, is it fairly robust, do you think, if community members don't actually act the way that they say they're going to act, or are there ways of making it more robust to that kind of consideration?
Okay.
Really on the demand side, in other words, the demand is not really just following kind of a standard curve. It's a bunch of customers who are deciding what they want to do over a period of time.
Yeah. All right. Given this context, is we think about the communities consists of based on this test based on the six households, and we assume that everyone together makes one decisions, and giving this one decisions, and if we could control the battery storage using that one identity, and this is how we see it, and it's based on the number, we can see that its benefits about 4 cents per hour that could have saved if we use it correctly in average. Yes.
So they would look at the savings essentially and see that as an incentive to stick with their plan, basically, to get those savings.
Yes.
Thank you.
Okay, thank you so much for your presentation. Next, we're going to have Dr. Nikita Singhal from Electric Power Research Institute, and she will be presenting on the integration of hybrid storage resources in wholesale electricity markets.
Thank you. While they're pulling up the presentation, I wanted to mention that this is work that we've done in collaboration with Lawrence Berkeley National Lab.
Could you bring the microphone a little bit closer? Brilliant. Thank you.
This is work that we've done in collaboration with Lawrence Berkeley National Lab and through funding that was provided by the US Department of Energy. And I'd like to thank all of you for sticking around since it's almost the second last session of the amazing conference and coming back after lunch on time. Thank you. So today I'll be talking about integration of hybrids into wholesale electricity markets. Next slide. So the motivation of this work is essentially there's a lot of hybrid resources that we've started to see in interconnection queues, especially in the US and even globally. There's a lot of uncertainty around efficient and reliable ways to operate these resources and what impacts these hybrid storage resources may have when we start to see an increased penetration of these resources. By hybrid storage here, I mean storage co-located with any renewable plant specifically. So this project, our goal primarily was to provide the industry with metrics that quantify the advantages and disadvantages of different ways to represent these resources within market clearing software, and basically identify what their implications may be on a certain set of metrics. And here we chose to kind of analyze the impact of different ways to represent these resources on economic efficiency, reliability, and asset profitability as well. I'll be showing a few more metrics as well, and then I'll be concluding the presentation with a few recommendations for further examinations. On the next slide, we show 4 different ways. Next slide, please. So as some of you may be aware, FERC actually requested for information from all the US ISOs and RTOs regarding what they're doing in terms of, first of all, defining what these resources mean, and then market participation of these resources. How can these resources be represented within market clearing software? A lot of different options have been discussed across the industry, but we've proposed 4 different ways of representing these resources. What you might hear often in the industry is what is referred to as the 2-resource model and the single resource model. On your upper left corner, you would see the 2R ISO managed co-located resource model. In this specific model, essentially, the individual components of the hybrid resource are represented separately, and what the ISO can do is use existing participation options for storage and the renewable component that they may already have in place. The asset owner can also share information regarding renewable forecast information, and also state of charge telemetry with the operator. So the arrows essentially signify what information is being exchanged between the developer and the ISO. Option B refers to the 1R self-managed hybrid resource model. Here, think of the resource as the individual components of the resource lying within a black box. So no information about the forecast or the state of charge telemetry is shared with the ISO. The only information that the asset owner can share with the ISO is bids and offers. That's the only way they can interact with the ISO. So this provides them with a lot of bidding flexibility as well. Whereas in option A, the ISO would manage the resource. Option C is similar to option B, but now the resource owner also shares the telemetry of the resource and the forecast information, just so that the ISO has situational awareness about where the state of charge of the battery component may be, so that they can, ensure feasible and reliable schedules of the resource in critical conditions. Option D is very similar to option A. Here we refer to this model as the 2R co-located linked model. Now, this was important before the IRA announced the storage tax credits, but there was a condition that if the storage component were to charge from the co-located renewable resource more than 75% of the time, they qualify for ITC credits, right? So that's something that links these 2 individual components together, as a result of which that can impact how they operate. So we refer to that as a linking constraint. Both the components still share information with the ISO. When I say information, state of charge telemetry and forecast information again, and the ISO is managing these resources. The only thing is that there's this extra linking constraint, which limits the fact that the resource may not be able to withdraw from the grid on all times of the day. On the next slide, I wanted to just introduce briefly about the study process. So our main idea was to compare this 2R participation option and the single resource participation option. We've used a software called Power System Optimizer to run the case studies in this study. So we have modeled a multi-stage production cost model, essentially, where we do model day-ahead participation and then also model forecast errors and uncertainties occurring in real time. We've used an ISO-sized test case system, so a lot of system data to do with different hybrid resources goes into the 2R case. Outcomes a certain set of metrics. For the 1R case, we use the prices that we receive from the 2R case, just so that we can be as accurate as we can with respect to price forecasting the prices. And also the renewable components forecast information, we feed it into an offer module. So I think many of you may have attended Brent's presentation as well, where he discussed about an offer module for DER aggregation. So this is we had our effort to also understand how could hybrid resources potentially bid into the electricity markets. Giving this information into the offer module, I won't be going into the details of the offer module and the math behind it, but just for your information, it's a stochastic program. We do maximize the expected profit. And then the output of this offer module is essentially the offers that the 1 hour resource could use to submit to the ISO. These 1 hour offers and bids are then used again as an input to PSO, to where all the hybrids are represented using a single resource model. And then we compare the results that we get from the 1 hour case with the 2 hour case. On the next slide. Yeah, just to give you a brief idea about the simulation tool and what went into these multiple stages that we're representing in the study. In the day-ahead market, we do include a day-ahead security constraint unit commitment and an economic dispatch. We use that to commit the long start resources, schedule these hybrids based on the bids and offers in the 1 hour case, and based on the ISO scheduling the battery, it's using a central dispatch in the 2 hour case. It also uses day-ahead forecast information for renewables and loads. In real-time operation, we model real-time security constraint unit commitment and economic dispatch as well, where we do take care of imbalances that may occur by committing quick start resources. We also dispatch the resources that may have been committed in the day-ahead stage. We can redispatch them. And then hybrid resources are made to follow one of two real-time operational strategies. So just so you know, we don't re-optimize the hybrids based on new bids that are coming in real time, but rather we use two real-time operational strategies, which I will elaborate in the next slide. But before that, another point to note is that these hybrid resources were qualified just to provide energy. So we did not qualify them to provide ancillary services, although we did model an ancillary service market. We've used a zonal model for New York ISO. So all the nodal details are there. We don't enforce any of the intrazonal line constraints, just to simplify the model. On the next slide. So I mentioned two different real-time operation strategies. What are they essentially? In real time, we do model the forecast error that can happen from the renewable component of the hybrid resource. Along with that, we do also enforce state of charge limits. So we are ensuring feasibility, and we are respecting the physical and operational characteristics of the individual components as well as the hybrid resource. But we model something in one of the operational plan, we essentially model something called a storage follow. So what we say is let the renewable component have its forecast error happening in real time, but the storage component is to essentially follow its day-ahead schedule, as long as the state of charge is feasible and it can feasibly follow the day-ahead schedule. So we refer to that as the storage follow. In the other operational strategy, we refer to that as hybrid balance. What we do there is essentially we make the storage component do whatever it can in its capability to meet its day-ahead hybrid schedule. So let's say the renewable output were to decrease, then the storage has to increase to match its day-ahead output. Think about it as you're firming up the hybrid resource. So you're firming up the storage, the renewable component of the hybrid resource. Updating bids in real time was sort of out of scope of the study because it's really complicated, and we do plan to do that as part of future work to re-optimize the hybrid resources. But the current focus is on day-ahead participation, although we do represent real-time operations through these two real-time strategies. On the next slide. Yeah, just to give you a feel for the New York ISO test system that we've used, this is not a New York ISO specific case study. We just wanted to use the system due to availability of the test case. We modeled two different resource mixes, a current renewable resource mix of New York ISO and then a high renewable mix. The high case, we essentially retire a few fossils. We increase the penetration of wind and solar and also battery penetration. This is in line with New York's 70% renewables by 2030 plan. And we have run two different penetration levels of hybrid resources. In this case study, in one case, in the lower renewable case study, we have about 500 megawatts of hybrid, that is hybridized with 1000 megawatts of co-located renewable. So essentially any storage component is rated at 50% of its co-located renewable component, and the interconnection constraint that is connecting the hybrid resource to the grid is rated at the renewable plant's installed capacity. In the high hybrid case, we consider about 1,500 megawatts of storage coupled with around 3,000 megawatts of wind and solar. Thanks. On the next slide, we ran a lot of different case simulations just to just to give you an idea. We've run two different simulation months, and a low load period and a peak load period, two different renewable penetration levels, two different hybrid penetration levels. And when it comes to participation options, we've simulated the 2R co-located model, the 1R self-managed hybrid model, and then that linked model that I'd mentioned where we don't allow for grid charging. And also the two different real-time operational strategies that I briefly described before, which is the storage follow and the hybrid balance. On the next slide. Next slide, please. Just to start off with the study results, the first set of metrics were to do with the economic efficiency implications. One main idea was to get a feel for what participation options could potentially lead to maximum societal benefit, and which participation option may be more advantageous from the assets perspective, which may have the highest profit for them. On the next slide, I won't be showing the results for all the different case simulations because, as you can see, there were about 15 cases. We will be releasing a report within the next 2 weeks where we are essentially summarizing the entire study. But just to kind of elaborate on a few results, here on this slide, I've included the simulation results for the month of April and the month of July for the low renewable penetration case and the high renewable penetration case on the right side. There is a base case, the 2R storage follow case, 1R storage follow case that I've included here. As you can see, essentially granular models like the 2R models where you explicitly represent the physical and operating characteristics of the resource components in the market clearing software results in savings when compared to the base case, whereas in some cases the 1R model can result in increase in costs. 2R options also results in a more efficient utilization of the hybrid resource and also the traditional resources, because in 1R you may be bidding aggressively and you may schedule something in the day ahead, but you may not be able to meet it in reality in real time, as a result of which you'll have to rely on quick start decisions that tend to be more expensive. Although the savings here are almost comparable, I do want to mention that this was a test. This is really highly dependent on the system. We did do similar studies on other test cases, including the IESO system, where we saw about a 1% difference in the savings for a year. The MIPCAP set was about 0.01%. So you can see that there is comparable, almost the two are having a little higher savings. On the next slide, I wanted to talk about the profits. I've included two specific graphs here. On the left side, you would be seeing the low renewable penetration, and the right graph is on the high renewable penetration. And this is the month of April. The green bars essentially signify your day ahead revenue. The red bars, the real-time revenue, and then the small line charts are essentially the two settlement payments, which is typically used in the US. So I'd like for you to focus in the two settlement payments. The 2R model tends to give higher profits for the resource when compared to the 1R model, and we saw this consistently. And the reason for this is that given the feasibility was ignored in the day ahead because you're using offers and bids, there's a high chance that the resource may not be able to follow what they promise in day ahead in real time, as a result of which they're going to be buyback purchases. So this results in a lower two settlement payment in general. Note that these results do not include any ITC benefits and any extra costs that may occur due to degradation or operation and maintenance costs. Also, I'd like to mention that you see consistently that there are negative payments in real time. This is because anytime you have a forecast error, you're going to have to pay back, right? Pay back what you got already paid for in day ahead. And in the hybrid balance plan, because you're forcing the storage to follow or to basically meet the uncertainties from the renewable component in one time period, it may be you may land up in a situation that in a future time period you cannot meet the hybrid resource schedule because of the state of charge coupling, right? Because you're deviating away from your day ahead schedule in one time period, it affects what can happen in the future. On the next slide, when it comes to feasibility, we also wanted to see what happens with the feasibility of these schedules. The way we've measured feasibility is, can these resources follow these real-time plans while respecting all the physical constraints? Now, there are a number of instances that we observe that they're not able to follow the real-time operational plans, storage follow and hybrid balance, because of either having insufficient discharge capacity from the storage, or either having insufficient charge capacity or insufficient SOC or maxed out SOC. Any of these reasons could lead you into a situation where you cannot follow your real-time plan. On the next slide, I just included a few graphs to show you what could potentially happen. I realize that the audience here has a very small screen to see this, but on the left, I've included the charts to do with the 2-hour option, on the right with the 1-hour option. The topmost graphs are to do with the hybrid resource dispatch, followed by the renewable components dispatch, followed by the storage components dispatch, and the state of charge level. For the purpose of this discussion, just focus on the state of charge level on the right bottom corner. The lines in blue essentially indicate your day ahead state of charge, and in orange, it's the real-time state of charge. The yellow signifies the max state of charge limit. So you can see that the 1-hour option, the state of charge in the day ahead, is exceeding the bounds. And this can potentially happen because the ISO is ignoring the state of charge limits, right? You're just including offers and nothing to do with the physical constraints of the resource or the individual components. Whereas in real time, we do respect these constraints. So that's why you see that the orange lines are bound within the bounds, the state of charge level. So in those periods is when you're not able to follow your schedule, as a result of which you'll deviate from your day ahead plan. And we saw a much larger instances of these occurrences in the 1-hour option, essentially. On the next slide, I've included the total number of intervals that we saw these violations of these real-time operational plans. The 1-hour option, as you can see, have a higher count of insufficient state of charge and maxed out state of charge instances when compared to the 2-hour, that's significantly low. But the main crux of this is that I wanted to leave you with the fact that you will be seeing a lot of these infeasibilities, and if you don't have enough quick start capability on your system, you'll run into a reliability situation. If you have enough quick start capability, you can recover and turn on a quick start to take care of what the hybrid resources may not be able to provide. On the next slide, with the hybrid balance plan as well, we saw the same. On the right bottom, you'll see the bar chart for different renewable penetration levels and hybrid penetration levels, wherein the 2-hour had a much lower count of these intervals with infeasibilities when compared to the 1-hour option. Note that in hybrid balance, because you're deviating your storage schedule from day ahead, there are instances where you could have insufficient charge and insufficient SOC, both. And that both such infeasibilities could occur in an interval. But to avoid such instances of double counting, we've only counted one instance of that. And that's why we're showing the cumulative metric here. And even if the cumulative metric, we see that the 1-hour option has a higher intervals of these infeasibilities occurring. On the next slide, we did not notice any reliability implications for this test system because we had sufficient quick start capability to recover from any infeasible schedules. But like I mentioned before, if you have insufficient reserve requirements, if you have insufficient quick start capability, you could run into a potential situation in the future where you may have a reliability concern with the 1-hour option. On the next slide, I've included another metric just to give you a feel for what happens from the loads perspective. And throughout all the different case simulations, we kept the day ahead load consistent across all the different simulations, and we also kept the deviation in the real-time load when compared to the day ahead consistent. So the only thing that can potentially change when it comes to load payments are the prices. Now, given that the hybrid resource under the 1-hour option is submitting bids and offers, it is more aggressive, that the way we've seen that they could land up clearing more in the day ahead than it can potentially provide. But a larger amount of energy being cleared from the 1 hour resource in day ahead results in impacting the prices. Given the nature of storage that shifts energy, the prices get flatter in day ahead. And because the prices get flatter, the load payments get impacted and the day ahead load payments become significantly lower. Now, day ahead load is a big chunk of the two settlement when it comes to load payments. So what we noticed is that the 1 hour options had lower load payments, but the 2 hour option had higher load payments because of the impact on prices. So this is something that we do want to understand. In future as well, the price formation impacts of these different participation options. That's part of what we plan to do in the future as well. On the next slide, I think that's one of the last metrics that I've included is around computational efficiency. Given that the 2 hour option, you're modeling a lot more detail, you're representing each individual resource in detail, be it the state of charge constraints of the storage, be it the max charge, max discharge limitations, renewable component constraints, and also the coupling constraints when it comes to the linking constraint, right? So that's bound to impact your computational solve time. Whereas in the 1 hour option, you are only interacting with the ISO through offers. The ISO is not representing anything to do with state of charge or anything otherwise to do with the individual resources. As a result of which the 1 hour option in general, we saw that the day ahead solve times for the 1 hour option was much lower for 1 hour, whereas it was much higher for 2 hour. But we have come up with some tricks to enhance the computational solve time of these of state of charge constraints through something called the wrapper energy constraint. That's some additional work that EPRI will be putting forward very soon on how an ISO could potentially manage the state of charge of batteries in a computationally efficient manner as well. On the next slide, I do want to acknowledge the fact that there are a lot of modeling difficulties when it comes to representing these offers. We, of course, couldn't account for the fact that there will be a human in the loop. In reality, when hybrid resources are bidding into the market, there could be a trader who just doesn't take the output from your offer modules and changes it because of their engineering judgment and submit something that makes sense at the very end, right? So that could impact the hybrid resource schedules under the 1 hour option. So in that sense, our results could be somewhat conservative. But I think in future, we'd like to see some empirical evidence with greater participation of these resources that are beginning to come onto the grid to substantiate these results. We did do a lot of changes to the production cost model as well to make sure that we model these resource hybrid offers accurately. As an example, in reality, these hybrid resources submit a bid every single day, right? The day ahead market is clearing every day. But when you run these kind of simulation studies for a long time frame, what happens at the end of day one carries through to day two without any person kind of like intervening in between because you're running it for long simulation. So we essentially had included additional, we worked with PSO to include something called state of charge dependent bands. So depending on at what level the state of charge of the battery component is, choose a different level or choose different sets of offers. Think of it as kind of like a lookup table. So we can more accurately model their behavior, but even then there's no comparison to having a human in the loop and changing these offers on the fly. On the next slide, I've just identified some recommendations for next steps. We do want to evaluate a few more additional sensitivities. For instance, what would happen if we were to change the ratio of the storage capacity to the renewable capacity? What would happen if we were to have a different point of interconnection constraint limit? We do want to extend this to analyze what happens if we were to start updating these bids in real time as well. So participation in real time explicitly rather than using these two operational strategies that we had to use for this particular study, and enhance the participation models to representing degradation and as well the computational efficient techniques to manage the state of charge of a battery under the 2 hour resource is something that we want to do. We do also want to study how the different metrics would be impacted if hybrid resources start to participate in ancillary services, which is pretty much already happening. So that's a very important piece as well as the capacity contribution of these different participation models. And I think that on the next slide, I think that's my last slide. Yeah, thank you.
All right, thank you so much. Do we have any questions? Okay, that was quick.
I'm afraid you left out the most interesting part for me, the advanced computational capability. What do you mean?
Advanced, sorry.
You had the very last box was advanced computational capability.
Yeah. So with state of charge, you have to essentially model a constraint that models state of charge as a variable through these multi-interval optimization problems. That's what makes these problems computationally complicating, right? So what we are thinking there is to...
Why?
Well, because of the intertemporal nature of the constraints, when you have to determine the schedule in any period, it can impact the schedule in any future interval as well. So similar to ramp rate constraints, they do tend to introduce complexities.
No, I understand, but
Yeah.
if you have ramp rate constraints, I don't know, is there such a big difference to actually put a state of charge limitation between stage to stage? That's the part which is a bit puzzling to me.
Oh, yeah, it is. The many ISOs have even mentioned that's one reason why they don't want to offer explicit management, because 1 hour is much simpler, where the onus is not on the ISO but on the developer to kind of just submit the offers. It does add computational complexity to the problem.
Thank you.
All right, anybody else? Of course.
Thank you for the presentation. This is Bing from RIT. So I had 2 questions, could be very naive. So the first question is related to time horizon and time resolution. So we know NISO has 3 markets. The first one is day ahead with 24 hours and with 1 hour as time interval. And then the second one is a real-time unit commitment problem. And then that last one is a real-time dispatch problem. And then for the last 2 problems, they use 15 minutes as time interval, right? And then for the real-time unit commitment problem is for next 2.5 hours, and the real-time dispatch is for 1 hour. So how can we handle this kind of difference between time horizon and also time resolution? That's the first question. And second question is related to like kind of state of charge. So in the day ahead, so we know we have like full forecasting all the information. So we may want to like hold the battery and use it during peak time. So to discharge the battery during peak hours. But in the real time, we only have like 2.5 hours or just 1 hour information. So if we want to minimize the cost in the real time market, we may just fully discharge the battery at the end of this time horizon, right? So how can we handle this problem?
Thank you. These are great questions. Pretty much the most pressing topics on the topic of storage, essentially. I think they're both related, your questions. I'll answer the second one because it may help get context on the first one as well. In real time, you're right, the horizon is smaller, as a result of which you may land up emptying your battery. There are ways that you could essentially model your real time so that you don't do that. For instance, you could use information from your day ahead within your real time. You have the best forecast of real time is nothing but your day ahead, right? So you know what your future value of storage is at any given interval if you were to use that information from day ahead. In your day ahead, you are modeling state of charge constraints. The dual of those state of charge constraints represent the value of the energy in that interval, the future value of the energy. So you could essentially say that let's say you're at 12 a.m. in your real-time market and you're ending it at 2. Let's just assume that it's a 2-hour optimization horizon. You could say that the end state of charge at 2 a.m. should be the same as what I saw in my day ahead solution. And there could be an opportunity you could assign an opportunity value to not deviate from that. You could model it as a soft constraint as well. There are many other things that you could do as well. I think, for instance, in KAISO, they use something called a minimum state of charge constraint tool to essentially make sure that they have adequate state of charge for the critical time periods, which is what happened in the heat wave last year. They use the information from day ahead to ensure that they save up enough state of charge. They hold back state of charge for those evening hours when there is going to be a need for storage.
I see. Okay. Thank you.
You're welcome. Yes, Ras.
Do we have a question online?
Alva, if you can go ahead and unmute and ask your question.
And then we'll get right back to you.
Yes, thank you. A wonderful presentation, and it's really great to see you creating this kind of a comprehensive model. I sort of doubt your conclusions, however, on the revenues that would potentially accrue to hybrid resources. It just seems inherently a hybrid is a resource that has more flexibility in terms of how it's going to arbitrage between day ahead and real time than a state of charge constrained battery will. I mean, essentially, the state of charge constrained battery is required to provide something that is going to have more relation to physical reality than a hybrid. And so just having more degrees of freedom, it seems, and I'd like to read the paper more carefully, but it seems inherently a hybrid can get more revenues, and maybe it's your policies in terms of how the hybrid is adjusting its schedule that are the source of the conclusion that you're coming to.
Yeah, I think we did not show comparison of a standalone storage, the revenue earned by a standalone storage versus hybrid resource, Alva. We were showing the revenue comparison of representing the hybrid resource as a single resource versus representing a hybrid resource as two independent resources. Right. Yeah.
Right,
so,
but I mean, the variable energy resource component of the two is just a fixed load in both cases, right? I mean, it's the same load.
If you're thinking of net load, yes, it is. We don't allow for curtailments. Yes. But
so to me, it's the same.
But it could be the plans too. You're right. It could be the real-time operational strategies because we're forcing the storage component to follow the day-ahead hybrid resources schedule. So that can impact. But I'd like for you to focus on the difference in the revenues between 1 hour and 2 hour rather than thinking of it as the storage. I mean, quantitatively, those revenues do make sense.
Okay, well, I'll try to focus on that, and I'm looking forward to reading the paper in more detail.
Thank you.
Thank you.
Okay, we're extremely over time, so if you have more questions, please.
Thank you.
See Dr. Singhal after. All right. Next up, we're going to have a virtual presenter, a PhD student from the University of California, San Diego, Yuejing Bian. And he will be presenting, or they will be presenting on predicting strategic energy storage behaviors.
Hi, can I be heard clearly?
Yeah, we can hear you.
Okay, thank you. Okay. Hi everyone, I'm Yuejing Bian and I'm from University of California, San Diego. Today, I'm really glad to present our work, learning strategic energy storage behaviors. And this is a work in collaboration with Columbia University. Today, I will also cover energy storage behavior and prior works predicting the energy storage behaviors and also the problem formulation and the proposed algorithm. And next, I will introduce our case study and the future works and our conclusion. Energy storage behavior denotes that when the system operators will design the price signals for the electricity, and the energy storage system will adjust their electricity usage in response to the different time variant price signals. And the grid operators can design the price to meet the grid needs to avoid the system emergencies. And this is an illustrating example. When the price is really high, the energy storage system may decrease their demand, so it will not exceed the grid capacity. And in this work, we aim to learn the energy storage behavior given time-bound price signals from historic data. That is, given any price signals, what will be the energy storage behavior of a given energy storage system? And in this work, we consider the energy storage agent as price taker. The strategic behavior denotes that they will making decisions to earn its own profits. The decision-making process of a price-responsive battery agent can be modeled as an optimization problem. The decision variable is the charging amount and the discharging amount of energy. And the objective is to minimize energy cost plus battery degradation cost subject to the system constraints, for example, the physical device constraints. And this is an example. The battery agent model will take the price signals and decides the charging power and discharging power to minimize the cost. And here is the written formulation for this optimization model knowledge. The decision variable is the discharging power and charging power. And this term is the energy cost. And we also want to minimize the degradation cost for the battery health. And it will also subject to the power constraint and the energy charging constraint, where eta is the charging efficiency. There are limited works to predicting the energy storage behaviors, but there are a lot of works predicting the demand response applications. So I will introduce the mainly focusing on the works predicting the demand response behaviors. And this work can be separated to categories. The first is the model-free approach, and the second is a model-based approach. The model-free approach usually related to the statistic methods and deep learning methods. They use a data-driven model, which can be deep learning architectures like MLP, RNN, and also the like linear models in statistic methods. And their goal is to mapping from the price signal to the demand behavior. The advantage of this category of approach is that they're easy to adapt to different demand response applications or like different energy storage models. And the disadvantage is that they will require a large amount of data to achieve reasonable accuracy. And the second type is a model-based approach. This work will encode the demand response model knowledge, and usually they use the inverse optimization. And their method is to build a second level optimization. The higher level optimization is to minimize the difference of the predicted demand response and the true demand response. And the lower level optimization is the optimize model knowledge with unknown parameters. And they use this second level optimization to find the unknown parameters within this model. The advantage is that because you are encoding the response model knowledge, so you will achieve data efficiency. And the disadvantage is that it may require different formulations, and it can be computational inefficient if you have a really large data set. And the motivation is that, can we combine the model-based approach and model-free approach to achieve the benefits of the both? That is, we can easy to adapt to different form of the battery agent model, and it can also be robust to the noisy data. And also we can encode the battery model knowledge to achieve higher accuracy. And in this work, we propose a novel data-driven approach encoding model knowledge. And our work significantly improved the battery behavior forecast compared to black box data-driven method, optimization method, and also simple heuristics, which indicate that when the price is high, we can discharge to money, and when the price is lower, we can charge to in energy. And this is the framework of the whole proposed algorithm. This is an illustrating example. The energy storage system, like EV charging energy system or solar energy system, given the price, they will decide the storage response. And this is the energy storage model knowledge, where the Y is the decision variable, indicating the discharging and charging. And we want to minimize the energy cost and also the degradation cost with satisfying the storage physical strength. And green box denotes the parameters we want to identify, which is U theta, A, B, G, H. And this is the proposed algorithm. Given the history price, we can first initialize the model and solving the model and get predicted response y hat. And since we have the history response y, we can evaluate the loss and update the parameters in this model. And this is the problem formulation. We first consider the quadratic agent model, where y is a decision variable, lambda is a price, so lambda y is the energy cost. We model the battery degradation cost as the quadratic term with regard to the response, and subjected to the AY is equal to B, GY is less than or equal to H. We assume we can get access to the history price and history observation lambda y. And our goal is to identify the model, which is to estimate the unknown parameters alpha 1, alpha 2, A, B, G, H. And we formulate the identification as a optimization problem. The goal is, the objective is to minimize the difference between the true response and the predicted response, where the y hat, which is the predicted energy storage behavior, is a solution to the energy storage optimization problem. And this is algorithm part. We propose a gradient-based approach to identify the agent model. First, we will initialize the model parameter theta. And given the price lambda, we can solve in the energy storage model and get y hat. And since we also have the energy storage behavior y, so we can evaluate the loss using the true norm difference of the y with y hat. And then we can update the parameter theta with a gradient. This is a joint agent model identification and energy storage behavior forecast, because using the gradient approach, we can get theta. And once we identify the model, we can get predicted response by solving this model. And the challenge of this gradient-based approach is that this rat term, which is the gradient of the solution with regard to the derivative of the parameters within this optimization, dy d theta is not trivial to get. And our work is motivated by OptiNet, differentiable optimization as a layer in neural networks. The gradients can be computed by differentiating the KKT conditions of the optimization. And this is a procedure to get the gradients. Since the energy storage system model is a convex optimization, so we can write KKT conditions of the agent model, which guarantees which is the necessary and sufficient condition for the optimality. And then we can write the derivatives of the KKT conditions and write it in the matrix form. Since we can write the derivatives of the KKT conditions, and remember that we want to compute the rat term dy d theta, we can divide both sides with the length parameters, with a derivative of the length parameters, and multiply both sides with the inverse of k. Inverse of k. For example, alpha 2 is the coefficient of the degradation cost, and we want to compute dy d alpha 2. Then we can divide both sides with d alpha 2 and multiply both sides with inverse of k. So dy d alpha 2 is the first row of the right term, and computing other gradients are really similar. One will naturally ask what's the convergence performance of the proposed gradient based approach. And in this work, we prove that for a class of quadratic model with equality constraints, we have the gradient dominance property. That is, we will have the linear convergence rates. This is the theorem. And if the Y is the solution of this quadratic agent model, where we model the degradation cost is only the quadratic term and subjected to the equality constraints AY is equal to B. For this agent model, we can guarantee the convergence to the true parameters. And then we will introduce the generic energy storage model. That is, if the system operator don't have the model knowledge of this energy storage system, or the true model of the energy storage system is not in a quadratic term, then we have to actually identify the energy storage system model where the objective can be an unknown form. And since this is the generic function, and directly solving this generic model can be difficult, so in this work, we propose to use sequential convex programming, SCP, to solve this generic model. The idea is to first initialize the solution Y0 and to approximate the convex approximation of this generic model, which is to approximate the objective as a Taylor second approximation around the solution at each iteration. And this is procedure. We can first initialize the solution and approximate the objective as a second order Taylor approximation around the solution at each iteration, and solving this approximate convex model and until convergence. If the solution at iteration I+1 is really close to the Y at iteration I, then we denote it converges, and we denote Y star is equal to YI+1. And then it comes to how to compute the gradients for the generic model. Suppose we have Y star is equal to Yi, and to obtain the gradients of the energy storage forecast with respect to the unknown parameters in the objective function, we can, sorry, this is a typo, we can use a chain rule. And dy star d theta is equal to dy dq d theta plus dy d capital Q d theta. And the Q is a first order gradients of the U with regard to the solution, and capital Q hat is a second order Taylor gradients of the U with regard to Y star. And since we don't know the form of this degradation cost, we propose to use the input convex neural network when we have no knowledge of the diffusivity cost. And it also guarantees the second order approximation Q hat is always positive semi-definite. And this is the main procedure. The main difference with the quadratic model is marked in this orange box. First, we can initialize the model parameters, theta. And given the price, lambda, we can use the SCP to iteratively solve the model. And given the energy storage behavior, we can evaluate the loss and use the chain rule and the differentiable optimization methods to get the gradients and update the parameters in this model. And now we come to the case study. We consider two synthetic energy storage system model. The first one is to minimize the energy cost and also the quadratic storage degradation cost. C1 and C2 is a degradation coefficients of the degradation cost. And we have the energy constraint and also SOC constraint, where the eta C and eta D is the efficiency of the charging and the discharging efficiency. And second, we consider SOC dependent storage degradation cost, where the degradation cost is dependent on the SOC. And we have the same constraint as this quadratic storage degradation cost. And case study 1 is that we want to identify the quadratic energy storage model. If we assume the quadratic model, we denote that we're just using the proposed approach to find out C1 and C2. And for the generic model, we use the input convex neural network to model this degradation cost, and we want to find out the parameters in these neural networks. And this is the test day case. We can see that our approach using both generic model or quadratic model can accurately forecast the energy storage behaviors. When the value is a positive, we denote we want to charge, and when the value is a negative, we denote it's when it's negative, we denote it's discharge. And the gray curve is the price signals. It can be seen that when the price is really high, we can discharge to earn money, and when the price is low, we can charge to gain energy. However, both deep learning models, including RN and MLP, fail to forecast this energy storage behavior, but only approximate the rough pattern. And this is the model parameters identification value. We can see that if we have the accurate model knowledge, which is a quadratic model approach, then we can proposed approach can converge to the true parameters. However, even if we use a input convex neural network to model this degradation cost, we can also compute. We can also converge to the true parameters and accurately identify this model and perform a really accurate energy storage behavior forecast. And case study 2 is that we want to identify the SOC dependent energy storage model. And still for the quadratic model, we want to identify Q and capital Q. For the general model, we want to identify this unknown form of the degradation cost. And this is a test day. We can see that the true is the true energy response. And we can see that our approach using the generic model can forecast the behavior better than the quadratic model and RN MLP. It indicates that for a more complex model, using a generic model, using the convex neural networks to model the degradation cost will have better performance than worse model knowledge, and also it's better than the deep learning data-driven models, including RN and MLP. And this is the test MSE. It indicates that the generic model achieved the lowest MSE compared to the quadratic model, MLP, and RN. And the case study 3 is we work on the real-world data set. We further demonstrate that the applicability on a real-world data set. University of Queensland, Australia installed a UQ Tesla power pack. And in their report, they said they are currently using a quadratic programming for this decision-making process, but we don't know the what's the optimization formulation for their Tesla battery data set. And in our approach, we assume quadratic model and generic model using input convex neural networks. And we compare our approach with MLP, RN, and a simple threshold-based approach. The simple threshold-based approach uses a training data set to estimate the activated price ratio for charging and discharging. That is when the price is high, when the price is higher than the activated price, we will schedule the discharging, and when the price is lower than the activated price, we will schedule the discharging. And this is the model performance on a test day. The true is the true response in observation, and our generic model, quadratic model, is also better than MLPRN and the threshold-based approach. And in this table, we show the training MSE, test MSE, and the test correlation. It indicates the quadratic model is better than the generic model, threshold-based approach, and MLPRN. It may due to that in the report, they said they use a quadratic programming, so the quadratic model may have a more accurate model knowledge than the generic model. And also in their report, they said their forecast price is not that accurate as the real true price, but we in this data set, we use the real price and the real behavior. And however, we achieve a really reasonable high accuracy for the energy storage behavior forecast. For the future work from the system operator side, our work can be extended to the price design based on the identified energy storage model to achieve the certain system level objectives, such as reducing the peak demand power or reducing the carbon emissions. And thank you, everyone. And this is the related works to this presentation.
Thank you so much for the presentation. Looks like we already have a question in the audience. It's okay, I need my steps.
Very good. Hi, interesting presentation, but your differentiability with respect to parameter holds only when you don't have inequality constraints, right? So I'm talking, right. So what did you, I'm not sure if you talk about it. What do you do what do you do with inequality constraints when you're trying to do the identification?
Actually, we proved that the convergence guarantee is only for this equality constraint problem. But for the practical scenarios, for example, the 3 examples cases in this like case study, it shows that even if we have the inequality constraint, we can like converge the two parameters.
No, and there's a good reason why. So this is so in the 2000s, there was a lot of what you're solving is a bi-level optimization problem where you have the KKT solution at the lower level and then you have the matching function at the upper level, right? Those are actually not as hard problems to solve as people believe. In the 2000s, there was a lot of work in solving them as mathematical programs with complementarity constraints. For example, Nitro can do it, right? So a lot of people, use Nitro as a solver, Nitro and ITOP, right? So you actually, so the trick is actually, you can actually show that you can get, if the problem is solvable, you can get the right solution just by relaxing the complementarity constraints, and you still get the same solution as if you don't. But you do get an algorithm that converges. So there are easy iterations in the 2000s, which allows you to, send me a message. My name is Mihai Nitescu from Argonne. So send me a message and I'll give you the reference if you want. But there's people, there were even benchmarks for these problems. Like the problem has not, it's called mathematical program with complementary constraints. There were benchmarks for it in the 2000s, and there's a lot of software you can use to actually exactly to that point. Anyways.
Thank you for this question. And also, like if you have like resources, like we can maybe
there's quite a bit of work. There's even websites to that. So I'll send me a message and I'll be happy to tell more.
Okay, yeah. And also like in our paper, we also try to compare with the like optimization of your solver to solve it directly. And
all right, but you have to transmit to IPOP that it's looking at complementarity constraint. When you have the complementarity constraints on the KKT, IPOP has to know that it's a complementarity constraint, so it relaxes it properly. That's actually the point, right? If you just feed it to it as a nonlinear program, it's not going to know that necessarily. You have to annotate that it's a complementarity constraint you're giving it. It does a very special relaxation, which works.
Okay.
I'll tell you more. Just send me a message and I'll tell you more. Thanks. Bye.
Oh, okay. Okay.
Anybody else? Okay.
This is Nitin Padmanabhan from EPRI. So thank you for the presentation. I have a couple of quick questions. One is when you say you're comparing two models, right? The quadratic degradation model and the generic model, right? Is the generic model the same as the SOC dependent model which you had mentioned in one of your case studies? Or is it a linearized model?
The generic model actually can be applied to any energy storage model, and we apply the generic model approach both based on the quadratic energy storage system model and also SOC dependent model.
So even the generic model is a quadratic model, right?
Yeah.
Okay, both are quadratic. And then have you made any comparisons when you have this quadratic model and a linearized degradation cost model on computational aspects or the other parameters which you have? Did you find if there is any considerable difference?
Yeah, like for the quadratic, if the true energy storage model is a quadratic model, and in this case, if you assume a quadratic model, it will perform better than the generic model. But if the true model is in a more complex form and the degradation cost is not a quadratic form, then the generic model will perform better than the quadratic model.
Okay. Anyway, I'll go through your paper and then I'll get back to you if I have more questions. Thank you.
Thank you.
We have a question online. Maxwell Danku. Maxwell, are you there? All right, moving on then probably.
Okay.
Thank you for the presentation. This is Bing from IT. So I have two questions. So one is related to your future work. So you mentioned you want to consider non-convex cost and also non-linear constraints. Can you elaborate more what will be the non-linear constraints for battery?
Yeah, because the gradients can only be computed through differentiating KKT conditions. So we still should approximate the nonlinear constraints at around the approximate solution and trying to identify the constraints. But I thought it is a really interesting future direction to also identify the model with the nonlinear constraints.
Yeah, let me clarify. I'm wondering what are those nonlinear constraints? Physical constraints for battery. So usually what we model right now, they're all linear. So I'm wondering what are those nonlinear constraints?
Sorry, can you
I mean, for the kind of traditional models for battery, they're all they're all linear. Right? It's like SOC or limits for charging and discharging. So I'm wondering what are those nonlinear constraints?
Actually, in this work, we only model the linear constraints.
Yeah, I mean, in your future, you mentioned nonlinear constraints, right?
Nonlinear constraints.
Yeah.
Sorry. Currently, I cannot come up with an example, but at least for this UQ Tesla model, battery model, in their report, they said they use the quadratic nonlinear programming with a nonlinear constraint. So actually, their optimization also includes the nonlinear constraints for this decision-making process for the battery.
Okay, yeah, thank you. The second question is related to the model. So right now, it's kind of we assume the minimum charging and discharging level, they are all zero. So we don't need any boundary variables, right? So if we assume they are not zero, so what will be the corresponding strategy here?
We don't make an assumption for the discharging and charging to be zero.
No,
actually,
So you have the limit on charging and discharging, right?
Yeah, we have the limit.
Yeah, so you only have the upper limit. It's because you assume the minimum charging and discharging, they are zero, the requirement. Yeah, I'm saying for certain batteries, so maybe they're not zero. Under that scenario, we may need battery variables to identify the state, either charging, discharging, right? So if we have battery variables, so what we're going to do here?
I thought if their minimum is not zero, we can still make a variable of this lower limit, and then trying to identify this lower limit. Is that like is that answer to your question?
Yeah, we can set lower limit, but then we need battery variables because then there's a charging or discharging, the value is not continuous because it could be zero, right?
Oh yeah, that should be a mixed integer programming.
Yes, yeah. Yeah, so then this approach will not work, right? With modifications, you can still apply this approach.
Yeah, I think so, because the follow-up works for this OptNet is also the mixed integer programming, differentiable mixed integer programming. So if the decision variable includes the binary variables, we can we may also compute the gradients of the solution with regard to the parameters in this model. So if we are given the history data set, yeah, there is a large potential to identify the model with the binary variables.
Sorry to cut off a good discussion, but we do have one more presentation, and I do know that people want to go to break. So lastly, we're going to have Dr. Brent Eldridge from Pacific Northwest National Laboratory and presenting on energy storage participation algorithm competition.
Thank you. Yeah, thanks again for putting together this FERC conference. I think the software conference is really a highlight of a lot of people's research calendar. And so we're waiting on the presentation.
Could you talk into the microphone?
Oh, okay. Is this good? Okay.
Thank you.
Yeah, so today I wanted to introduce a kind of a pilot project that we have going on at PNNL that's called the Energy Storage Participation Algorithm, or ESPA-Comp competition. So this is joint work with some colleagues at PNNL, Jesse Holzer, Brittany Tarafelli, Kostas Economou, Lihi, and Abhishek Somani. Next slide. So stepping back a little bit and giving more praise to the FERC software conference, a lot of very important things happen here. And one of those has been various discussions over the past decade or so that have eventually led up to the grid optimization, or GO competition. So if you're not familiar, this is a competition on optimal power flow and unit commitment problems, security constrained, yada, yada, yada. And this kind of the beginnings of it started about 10 years ago with the ARPA-E Advanced Bulk Power System Optimization Technologies Workshop, where they wanted to have some type of competition to figure out what is the best computational approach to solving a lot of the problems that we've been talking about the past 2 days. And the answer that they came up with was, well, first we need data. So they went through a few years of funding various ways of getting synthetic data sets, how to formulate or how to generate those, which eventually led up to competitions 1, 2, and now 3, plus the Monarch of the Mountain competition. But I bring all of this up just to say that, you know, this approach of using a competition to figure out the best approach, you know, of the various problems that we're talking about has been shown to be a very successful way of, you know, kind of settling various debates that we might have. Next competition, or next slide. Okay, so if we wanted to come up with the next type of competition, I was thinking maybe a good area for this would be storage. And so Padanan and Nikita and Yujin have all, given really nice presentations to lead up to this. That kind of describe a lot of the problems that you have with, what is the correct way to integrate storage into ISO software, in particular ISO market design. And so the different ISOs, they're all coming up with very different approaches to this, different trade-offs of complexity versus, maybe more internal optimization that's being performed by the storage owners themselves. We go to the next slide. So what I wanted to discuss today, I'll give kind of a broad overview of what this competition is going to look like. Then I'll have some details that I'll try to go through very quickly and briefly. And then what I really want to get is, well, first is get people interested in participating, but also to get feedback and suggestions that kind of, as we're putting together this pilot, there's a lot of opportunity to see what can we do now and what kind of plans should we have for this type of a competition in the future. Next slide. Next one. So this slide kind of comes from our proposal. The internal project name for this project is Project Weasel, which is the wholesale analysis via simulation and learning experience. I think it's an appropriate name for a pilot competition where we're trying to have a little bit of fun. But basically the idea is, we're a national lab, we should run experiments. We want to know what's the right market design. Let's run an experiment on market design. And so that's going to be kind of the upper level goal of this competition. Next slide. Okay, now one of the reasons why I'm going to be describing the competition format the way that it is my proposition is that the way that people submit offers, or storage devices submit offers into markets, it's mostly opportunity cost based. It's a very wishy-washy area where there's differences of, how should you be formulating the model? What should be your view of future uncertainties? What should be the way that you handle risk? And all of those things are too complicated to accurately simulate in a production cost model. Or if you are, then you're kind of over specifying the behavior of individual market participants. So on the left here is kind of a view of traditional production cost modeling, where kind of everything goes through the system optimizer, and a market design and a market clearing model. Those are one and the same. In this competition, we'll be looking at kind of separating that system optimization into a market design and a market clearing problem. And then we're also separating resources into the participant and what types of incentives the participant sees, and then a simulation of the actual devices that'll be, a highly nonlinear, complicated model that is too complicated to throw through the system optimizer. Next slide. Okay, so the way that the competition will work is we'll be asking competitors to submit algorithms via GitHub or something similar. Those algorithms will take in market data throughout the simulation. How have I been dispatched? How have I been priced? What is the actual performance of my device? And they take that data, they take the kind of primary data about what the device attributes are, and then they figure out how they want to translate that into offer data that gets sent to market clearing. And so there's this open loop simulation going between calling different market clearing problems and then iterating with competitor algorithms. One of the other advantages of this is that the competitor algorithms, we're not going to restrict at all what type of methodology they use. So if you want to use machine learning, reinforcement learning, that's great. If you want to solve a big impact, you can do that. If you want to do this game theoretically, you can do that. And then on the market clearing side, this will be used to set up experiments on various discrete market designs that we want to study closer to see which one is able to induce storage devices to submit bids that lead to more efficient market operations. Next slide. This is the kind of a sketch of how the competition divisions and scoring will be set up. So we have different divisions which correspond to different market designs. I'll explain those on a later slide. And then each market design will be sent through the same set of scenarios. So potentially, having base case, high renewables, and something in between, and hopefully seeing, how long can we, or how many simulation runs in each of those scenarios could we possibly run. The score of each participant is going to be determined by the sum of the profits that they earn in the simulations. And so ideally, we would be able to award prizes that are proportional to those profits. With this being a pilot competition, we're trying to figure out exactly how those awards will be set up. Turns out to be kind of complicated. And if we go to the next slide, we have these different scenarios, and those will be designed so that we can better understand, basically which market designs are best suited under various assumptions about the underlying resource portfolios. Next slide. Okay, so these next slides will be some detailed slides that will probably be too small to read in the room, but that's okay because we have all of this written up in some documents that we will be making available publicly. So here are the 3 market designs that we are planning to test. So on the left, there's the 2-settlement market. This is the standard typical ISO market design, or the day-ahead and real-time market. We're solving day-ahead market with a 36-hour horizon, 1-hour increments, real-time market with a 3-hour horizon and 5-minute increments. And those models are all set up so that you have both advisory periods, financially binding periods, and physically binding periods. And this also offers, kind of the widest range of ISO state of charge management for storage devices. Then the multi-settlement market is kind of like an intraday market. We're using the same setup as the 2-settlement market, with the change that the real-time market will have additional opportunities for basically settling financial forwards on the next over the next 2 hours. So you'll resettle each of those 5-minute positions throughout the real-time market. And then the last one is kind of a pie in the sky type of market design. This is the rolling horizon forward. This is a completely convex market with time separable bids. So basically highly simplified bidding structure, but the idea is that there's a whole lot more trading going on. And so if you're a storage device that's trying to manage your state of charge, then you have lots of opportunities throughout the day to change where your storage level is so that you can position yourself best for price arbitrage. Next slide. Here's the market clearing model. We have a generic market clearing model that gets set up different ways depending on what the horizon of the next market is. There's not a whole lot to describe there. It's very standard: nodal power balance, DC power flow, ancillary services, and then resources for different constraints for thermal, renewable generators. We'll have price responsive demand and virtual bids in the model. And then on the next slide, we'll describe the energy storage constraints. Next slide. So this is taken from the document that we have been working on. And yeah, I'm not going to go through all these different constraint descriptions, but the idea here is in the 2-settlement or multi-settlement market, you have fairly good flexibility of how your storage bids into the market and what type of SOC management or not you want the market to use. Whereas in the rolling horizon market, a lot of those more complicated features are deactivated. And so this is kind of getting at this trade-off of model complexity versus retrading or trading frequency. Next slide. So that is for the market clearing model. You also have to have kind of a ground truth model. And so we'll have a fairly detailed evaluation of how the storage device actually performs. You get your dispatch quantity from the market clearing engine. Okay, and that has, you know, your energy and ancillary service schedules. And you can, you know, you could choose if you wanted to only participate in the real-time market, or you could also participate in these various day ahead and other forward markets in order to hedge your position. Then the actual dispatch that your device takes goes through kind of a more complicated model that I believe gets described on the next slide, but it has various more complicated constraints for state of charge, the device temperature, and degradation costs. All of those we're hoping to be complicated enough that you're not going to be solving them directly, but you'll be figuring out what types of approximations or assumptions you should be using to participate effectively. So the profit at the end of the competition is, right, your revenue from LMP payments, from ancillary service payments, minus imbalance costs if you're not able to meet your schedule, minus degradation costs based on these various degradation components. Next slide. Okay, so this is the formulation for the device simulation for storage. And you can see we're taking account of Ohm's law and KVL inside the battery. There's a 0th order equivalent circuit model that we're used to model the battery. Current going in and out of the battery leads to resistive heating and losses. So that gets taken into effect. So you can tell, you know, if somebody wants to run their battery into the ground, they can do that. And then it should show up in high degradation costs. If they want to be very conservative, then they can do that as well. Next slide. Yeah, so this is the degradation model. This uses a exponential decay function for state of health of the device, and then that gets decomposed into cyclic degradation, thermal degradation, state of charge based degradation, and depth of discharge degradation, all going into that. These equations on this slide and the previous both come from a review paper from David Rosewater at Sandia that goes into fairly good detail about the physical modeling of the storage devices. Next slide. Okay, so almost at the end. So go on, one more slide. We're basically at the very beginning of this competition experiment thing that we're trying to put together. So basically, we just want to have something that's simple, show proof of concept that you can run a competition this way, and then hoping to run future competitions at a larger scale to kind of tackle maybe bigger questions that need to be addressed. So we kind of have plans for the future for larger spot market competition or kind of a long-term planning competition. Next slide. All right, so if you're a graduate student, or if you know graduate students, maybe you're a professor and you want to have your class do a nice little project. If you have some energy storage participation algorithm sitting around, or if you just want to ask ChatGPT to make one for you, this would be great. And we'll be launching a website soon that has more details about exactly how you participate and the steps to take. Our schedule right now is to have that available in September, to open up a sandbox environment to test things in November, and then to run the actual competition during the spring semester. So contact me if you're interested. Email is brent.eldridge@pnnl.gov. We have, I think, one more slide is our team of advisors that have been helping us with some of the questions here. And I think that is it. So, thank you.
Sorry about that. Does anybody have any questions or comments or inquiries? Just compliments?
Yeah, thank you for the presentation. I think it's a very interesting computation. I have a quick question. So for system level, you say we're going to consider DC power flow, right? But for the battery models, it's very complicated, even with the current and voltage and even temperature. So I was wondering why we need to consider like that complicated model for the battery, and at system level we use DC power flow. So how we're going to like coordinate between system level DC power flow and for the battery with current and voltage?
Yeah, that's a good question. I think the reasoning for modeling it this way is we're kind of like, well, more background, but throughout the, I don't know, starting maybe in the 80s, 90s, there have been various economic experiments testing different auction designs. And that's kind of the area where this idea is coming from. Those experiments used very, very, very simple settings. And so maybe, I think the most complicated for power systems that I've seen so far is maybe a 3-bus network that has constant susceptance in each branch. So I don't think the leveling of detail at the system level, if we were going to go down the route of AC power flow, it creates a whole host of additional issues that we don't want the competition to address with how does the system operator keep enough generation online to provide reactive power? How do they, all of these manual actions that we don't want to deal with right now. So we're just kind of trying to keep that part simple.
Yeah, I understand that part. So I understand why we want to use the DC power flow for system level. The point is related to the battery part. So why we want to consider like the voltage and also the current, even the temperature. So because as we, in the previous presentation, several presentations related to battery, we consider kind of like simplified models related to SOC and then also limits for charging and discharging. And for the even degradation cost, we consider kind of quadratic or even linear. So it seems here the degradation cost is also related to temperature of the battery. So this part, because I assume this algorithm will be used by ISOs or RTOs, right? So at that point, when they develop models for battery, we want to consider this voltage and current.
Consider voltage and current in the battery? Yeah, so those would be constraints that the competitor needs to consider within their own battery. And if they're trying to meet the schedule that the ISO is trying to meet, the ISO is not modeling battery temperatures or resistive losses in the battery to an extent. Right, so that's just part of the battery's delivery risk and degradation costs that they have to consider.
Okay.
Russ Filberg, Polaris. I can see that this could be a good learning activity for the students in various programs. And I'm speculating that one of the objectives of the project is to understand how some of the different market designs might help improve getting value out of storage. What are the main goals that you have from the outcomes?
Right, exactly. So under the different market designs, we're hoping that different types of market designs induce different offer behavior of the storage devices. And we'll be evaluating, maybe I missed this in the slide, but we'll be evaluating changes in market outcomes based off of changes in those offer functions. Mm-hmm. So, I guess the idea is, maybe if your real-time look ahead is 3 hours and you have this issue with discharging too much storage because your look ahead window isn't long enough, if that's the thing that's holding you back, then we have another market design that has a longer window that could potentially solve that. And
one thing that I may have missed, but I didn't see it addressed, was the how are you looking at participation in the markets by storage in terms of bidding parameters, and what will the market operator solve versus what the participant is responsible for figuring out that on their own?
Yeah, so the storage offer format, that includes, so there's options for ending horizon state of charge, beginning horizon state of charge, offer function for charge or discharge in each time period. That's kind of complementarity, or well, you could either do that or provide a offer curve for state of charge at the end of the horizon. And those are available for the two-settlement or multi-settlement market. The rolling forward horizon market, you only provide energy injection or withdrawal offers and bids.
Okay, so you are looking at explicit state of charge optimization for the day ahead. Okay, thank you.
All right. I
do have a question online. Do we have time for one?
We are already over time. But yeah. Well, how's the audience feel? Is everybody okay? All right. Then let's do it.
All right, Bolin Zhu, if you can go ahead and ask your question.
Yes, thanks, Brent. Very good presentation. So just a little bit clarification for the market design part. We are just so for the participants, it's submitting algorithm for batteries, right? Not the market design.
Right, right. So we are interested in market design as the competition runners, and we're setting it up as an experiment on market design. The competitors are not interested in market design, except for the fact of how it might influence their bidding strategies.
Okay, sounds good. Okay, thank you. Thank you.
Mm-hmm.
All right, guys. Now we're going to take a break. So we will see you guys back at 3. Thanks for being patient, and have a good break.
Check. Yeah,
What?
that mic works.
Maybe Rob just has the room muted. I'll just wave.
Test 1 2 test.
Wow.
Yeah, we're ready. And okay, now we're up.
Thanks, Rob. Yeah, we're ready to get started if you want to switch off that screen. All right. And you have the first presenter slides loaded or up at least. All right. So let's begin the final session. Thanks everyone for sticking around. Means a lot. So first, in this session, we have congestion mitigation with transmission reconfigurations in the Eldridge footprint with Dr. Pablo Ruiz from New Grid and Ann Brattle.
Thank you, Dan, for the introduction. It's a pleasure to be here and provide an update of the work that we have been doing at New Grid and Brattle over the last year on topology optimization. Next slide, please. The agenda is very simple. We'll start with providing the background on congestion management and topology optimization. Then we'll discuss the high level the applications of the software technology, as well as some high level case studies to illustrate benefits. And then most of the time we'll spend about a pilot with a partner utility in the SPP footprint, looking at both normal system conditions as well as conditions during the winter storm Elliott, looking to illustrate in general the impacts during extreme events. Next slide, please. In terms of the congestion management, the traditional approach to congestion management treats the transmission grid as given, fixed or effectively not controllable. I mean, it may be varying due to outages, but a given, and relies mostly on a redispatch. So the equivalent in a transportation network would be to say that you increase the tolls until enough people decide not to drive that day. So that approach, of course, if you only rely on it, has significant cost implications. It also limits travel in the transportation network. In a power system, it limits transactions, and therefore it has implications in terms of reliability as well as resilience of the power network. And I will say that the impacts are actually worse on the transmission network given Kirchhoff loss and the lack of control and flows. So if you effectively, congestion will impact any transaction and the entire interconnection, except those that are on radial lines. So next slide, please. Thankfully, in transportation, increasing the tolls is not the only congestion management approach. You can take a driver can take a different route and avoid a bottleneck if such route exists, and especially if they are guided by GPS applications. So very similarly in the transmission network, the redispatch approach is not the only one available. Operators can and do reconfigure the grid to reroute flow around congestion to increase the ability of the system to handle those transactions. Finding those reconfigurations can be done using topology optimization software, which will be the equivalent of the GPS apps or Waze or Google Maps in the analogy with the transportation system. The reconfigurations are implementable today by opening or closing existing circuit breakers, using existing infrastructure for communications. Is done reliably and at minimal cost, almost no cost. And you can see some figures on this slide. Next slide, please. Reconfigurations have been used for a long time. The value added, as I mentioned before, is in the identification of the few beneficial reconfigurations that meet all of the reliability criteria. That's where the advanced software provides additional value. This is a very complicated, very complex search process that can really benefit decision making in transmission operations and planning. Next slide. Of course, reliability is paramount. So it's key that the software accounts for all of the specified contingencies, all of the material contingencies, be those N-1 or any other criteria, depending on the particular application, and that do not radialize load beyond the user's needs. So those are two important criteria for the topology optimization software. Next slide. In terms of application, too fast. In terms of reconfiguration types, they come in different flavors. They could address one or multiple relevant constraints. They may be developed for implementation in preventive or corrective mode, and they can consist of different types of actions, opening or closing branches, lines, transformers, or reconfigurations of the substation itself or the arrangement, such as splitting or merging buses, or changing the configuration of the substation such that the implications of a contingency would vary. So there's a number of different types. Next slide. In terms of the applications, it could be the technology can be used for any business process for which mitigating transmission limitations can have material impacts. Those go from real-time operations all the way to operations planning and long-term planning. In this presentation, we'll focus on adapting the grid to emergency system conditions, relieving N-1 flow violations, and mitigating congestion costs. Other applications include support in outage scheduling, coordination, development of operating guides, and even in long-term planning, increasing the benefit to cost ratio of new projects by rerouting flow to those new high capacity transmission lines. Next slide. In terms of impacts, the impacts can be quite significant. Some of you may have seen this slide showing the before and after with an SPP real-time system snapshot. We did a study with SPP a few years ago, where this case comes from. On the left-hand side, in different colors, you see different prices, and we see a variation of color that denotes congestion on the grid. So in this case, there were 3 binding constraints. One of those was leading to curtailments. The other one was significantly overloaded. It was a reason for SPP selection of the case for the particular study. And there was another constraint at Texas Panhandle. So that's on the left-hand side. On the right-hand side, you can see what would have happened with 3 reconfigurations in that case, 1 per constraint. That's of course not necessarily that maybe sometimes more may be needed, but in that case with 3 reconfigurations, all wind curtailments could have been avoided, and there wouldn't have been any breach or any overload. And that particular solution was actually used in SPP for about a year until the necessary reinforcements were put in place the following year. So this provides an illustration of the type of impacts from a market point of view. Next slide. So in general, we've done studies in a number of jurisdictions for a number of applications, and we see that adapting the configuration of the grid provides a number of benefits, both on the economic side, physical side by increasing transfer capability, and also improving reliability and resilience. And on the next slide, we'll start talking about the specific pilot that we will focus on for the rest of the presentation. So next slide, please. So we're conducting a pilot with a partner utility member of the SPP system. In a few words, the partner utility selected 10 significant constraints in their footprint. Those constraints were selected due to both their relative relevance. These are difficult to manage and expensive, so have significant impacts both on the economic side as well as reliability. We jointly develop and analyze reconfiguration options to mitigate these constraints. And I will note that not every constraint can be mitigated by a reconfiguration. Sometimes you don't have enough degrees of freedom. So in this case, for most of the constraints, there were solutions, but not for all of them. The partner utility discussed the reconfigurations with SPP staff for implementation. And SPP, gave the approval or denial at any point in time. And then ex post, we evaluated the impacts, both of the reconfigurations that were used and the ones that were not used, relying on state estimator cases, following similar type of studies as those conducted in outage coordination and scheduling studies that SPP or other RTOs and transmission operators would perform. So a few words in terms of challenges and lessons learned during the pilot before we go into the results, since they would inform some of them. So in SPP, as in other regions, transmission operations historical practice has been to rely on redispatch, as I mentioned at the beginning of the presentation, and to only approve topology changes when constraints breach. So it's effectively first redispatch and then reconfigure when no alternative options are available in terms of a redispatch. So this made a proactive implementation of the reconfigurations difficult. Most of the results, as you will see, come from last year. So as a result, or in part inspired by this work as well as the work of others in the region, SPP has been working on a standard requirement for implementing reliability reconfigurations for reliability applications, and that was approved recently in this year. And SPP is now currently exploring creation of a process that also accounts for applications for market congestion mitigation. So keep that in mind as we walk through the results. Next slide, please. The next two slides provides a high-level summary of the impacts of the reconfigurations on those 10 constraints over a period of 5 months last year, both in terms of reliability and congestion cost savings. We start with the reliability aspects. The high-level finding is that the topology optimization could reduce the risk of transmission overloads on those 10 specific constraints by 98%, meaning a reduction in the number of constraint instances or hours by that amount. The different colors in the chart indicate whether the overload risk was actually mitigated during the pilot. Most, as you see, most of the bars have blue prominently, so 82% of the opportunities were captured by these reconfigurations. There was additional room, 16% of the opportunities in orange. Those were foregone, meaning that the reconfiguration was available or wasn't used, but the vast majority of the opportunities were captured. And the black means the unresolved overloads, meaning after the reconfiguration, sometimes there are still overloads. So additional means need to be used to mitigate those. So 98% reduction in the risk of overloads. Next slide, please. So when looking at the market impacts, the findings are that by using topology optimization, 85% of the cost of congestion associated to these 10 specific constraints, and specifically for this partner utility, could have been saved. over the 5-month period. Now, in this case, you see that the fraction with the foregone opportunities in orange is much more significant, reflecting the normal or the traditional procedures in SPP of first redispatching, and therefore incurring the congestion costs, and only as a last resort reconfiguring. So that's consistent with the historical practices in what the ongoing efforts are to reduce that. The cost savings are very significant. Over 5 months, we are talking a $53 million in potential savings, of which 14 were realized. So the ratepayers save a significant amount of costs. Going to the next slide, please. So that was a summary of use of or impacts of reconfigurations during the pilot under normal conditions. The rest of the presentation will discuss the use of reconfigurations specifically during Winter Storm Elliott. In this winter storm, which impacted a very large fraction of the Eastern Interconnection, congestion had a significant impact. So it was one of the key drivers, other drivers being unavailability of resources, high load due to the extreme low temperatures. So in this chart, you can see the count of congested events per hour for the whole week. The storm was in place between late December 22nd, but perhaps early December 23rd through December 24th. You can see the very significant increase in the count of the constraints binding. This is consistent with Seth's presentation the first day. With more complex system conditions, you usually increase the count of congestion. SPP declared energy emergency alert 1 twice during December 23rd. What this means is that all of the available generation resources were committed, and the balancing authority was concerned about sustaining the required reserve or carrying the required contingency reserves. So everything that was available was online during these events. Next slide, please. The constraints, so three constraints analyzed during the pilot were binding or breaching during the storm. So we focus specifically on those three, and we analyzed on an exposed basis the impacts of the reconfigurations during the storms. Next slide. This chart shows a schematic of how frequently these were binding. Next slide. So one constraint, the first constraint will show in green. Reconfiguration was not implemented. Going to the next slide. This one, it was interesting. The constraint was binding for 25 minutes. The reconfiguration was then implemented, and the constraint did not bind for the rest of the event. So just illustrating the impacts. Next slide. And the last one, constraint number 3. This one has actually 2 complementary reconfigurations. One was used. The constraint was still heavily binding, almost every interval for the entire event. The second reconfiguration was not used. Next slide. So we'll go quickly through a look on the flow of constraint 3. You can see that without any reconfigurations, there would have been 36 hours with overload on this particular constraint. Next slide. Historically, there was a constraint, a reconfiguration implemented, so as indicated in the chart, which provided a lot of relief in reducing the number of overload hours to 12 from 36. So next slide. And the following. Had the second reconfiguration been implemented, the flows would have been reduced further. And I failed to mention that the vertical scale shows the percent loading on the constraint emergency rating. So 100%, that's the limit. Next slide. Of course, once you reconfigure, then the market dispatch would increase loading on the constraint, taking advantage of the additional transfer capability, and some of the flows will increase, and that's what the hatched area indicates. Next slide. So the previous slides take a look at the flow, the flow situation with specifically with constraint number 3, and this slide summarizes the impact in terms of making available to the system additional generation by relieving congestion. And in a few words, the 2 implemented reconfigurations released up to 845 megawatts of generation during the extreme event. To put it in context, that's 1.8% of the peak load in SPP during the storm. The 2 other reconfigurations would have released an additional 600 megawatts of generation. These were units that, as mentioned before, were already committed due to the EA1 event, but were behind a bottleneck, so they could not be fully dispatched without relieving the congestion. Next slide. So I'll wrap it up with 2 comments. In my opinion, the RTOs should leverage reconfigurations and use them consistently under all system conditions, both normal and extreme events similar to the winter storm that we discussed, and should prioritize low cost, reliable actions that deliver more generation to the system and provide increased reliability and increased resilience over using costly actions that limit such deliverability of resources. So with that, I'll be happy to take any questions.
Any questions for Pablo?
Russ Forward Polaris. You showed that that there were a number of the recommended configurations that were not used, and that and those happen to also have a very large portion of the value of what would have been achieved if they had all been used. Can you describe what is the nature of those and why they were not used, and why they also had such a large amount of the value?
I would say most of the reason is lack of established processes, and so that was the comment about the processes being established this year. So I would see, I would expect that things would improve, or the frequency of implementation would improve over time once the needed processes are in place. So in terms of the value, so it depends. So if you look at the market impacts, the fact that most of the value was lost just means that under most conditions, when the constraints were binding but not overloading, the reconfigurations were not used, and only when the situation get beyond a given threshold, then the reconfiguration would be used. So what those figures reflect is that the implementation was rather limited in time to the extreme type of congestion conditions.
Okay. But when you say there were process limitations, why are the process no limitations for some but process limitations for others, or something to distinguish those 2 sets of operations?
There's no difference in the nature of the different reconfigurations. It's mostly about I would say the appetite of an operator to employ a reconfiguration under certain system conditions and not others, and also the traditional practice that we were talking about before. Good question.
Thanks. We have one over here.
Zoe from DRW. A very interesting talk. I just have 2 questions. The first one is I'm just wondering what's your policy in terms of this reconfiguration. For example, let's say SPP has a scheduled outage and that outage caused a binding constraint. In your model, will you consider to put it back? my second question is, from your study, how many percentage of the binding constraints can be resolved by one single reconfiguration, and how many can be, resolved by, let's say, putting 2 lines out or putting 2 lines back? Thanks.
Yes. So the approach we took in this study was to not necessarily change the schedule outages, but rather look for adjustments in the overall system configuration to improve congestion, during those outages. So that was the approach. The second question is very, very much situation dependent. Sometimes a single reconfiguration can relieve only one constraint. At times we've seen perhaps 4, 5, 6. So it really depends. But there are situations where you reconfigure one part of the network and then the multiple constraints are relieved.
Great. I'm Hal from Princeton. I think I have 2 follow-up questions regarding the previous questions. First of all, it's like Ross mentioned, your some parts you can reconfigure, some parts you cannot. Can I understand that your system has like a lookup table to choose as preventative or corrective actions, so that which can kind of like speed up your optimization process? And the second question is like, what is your objective when you do this topology optimization? Like, because from your presentation, there are something like you are saying there is historical reconfiguration and redispatch, and then you are saying there is additional reconfiguration. So can you be more clear about that part?
Yeah, good question. So all of these were preventive reconfigurations, meaning they could be deployed prior to any outage occurring. In terms of what was the second question, real quick?
This another question is like, what is the objective? Yes.
The objective function on these ones in particular is to reduce loading on constraints of interest. It could be one or multiple, without increasing loading on other constraints at the times when the constraints of focus are binding, so are heavily loaded or overloaded.
So your dispatch, So in that sense, it's the generators. Your variables will only be the topology, without changing.
In this particular pilot, yes, that's right.
Yeah. We have one quick one online.
Yeah, we have a question online. Richard O'Neill, could you unmute yourself and ask your question, please?
Am I unmuted?
Yeah, we can hear you.
Okay. Pablo, a great presentation, but I think I didn't see a gross cost savings or a gross curtailment avoided, renewable curtailment avoided. Do you have any estimates of that, or is it just too hard?
Good questions, Dick, and thanks for the question. We didn't calculate those metrics. We were working under a specific scope, and so we quantify those particular metrics. These are very, as you can see from the results, these are heavily binding constraints. So the impacts would have been very significant, more significant at the regional level than for a single.
You have measured those for some of your other studies, though, correct? And do you have a references slide at the end of your presentation?
I don't think, but we can add references.
There you go. Dick, I did see those in some of the other studies, previous studies that Pablo's presented at the software conference or published elsewhere. So with that, thank you very much, Pablo. And let me run over here and get. Next, we have optimal transmission expansion planning with grid enhancing technologies. Swaroop Srinivasrao
Yeah.
Kugalam?
Yeah.
All right, well done. Thank you.
Thank you. Thanks everyone for sticking around. Okay, next slide, please. Yeah, from this presentation, I want to focus on these 4 aspects. So these are the 4 key takeaways I want everyone to take after this presentation. First of all, like what and why are grid enhancing technologies being discussed recently a lot more? Why do we need a software tool to analyze these technologies along with some other existing or traditional way of solving problems? Validate some of these things we have done at EPRI through this tool, some case studies I'll be sharing, and then finally talk about some of the challenges that are still need to be addressed and where we kind of part of future research as well. Next slide, please. So grid enhancing technologies are being addressed. One of that was topology optimization as well, which Dr. Pablo presented just now. A few others which I'll mention shortly. Some of the advantages being mentioned around is, they are kind of fast, reduce installation time, or they're fast, quick to implement, their modularity nature, like you can move some of these devices from one location to another. If the use of that device at certain location is kind of completed, how do you identify that? So it being portable, these devices or these technologies can also be used sometimes for short-term solutions, so you can defer some long-term projects or capital requirements, and it can also kind of help solving to redirect some of your transmission flows, making sure that you increase the utilization of the existing transmission asset you already have. So some of the advantages, there could be more, but just want to recap and build upon some of the presentations others have talked about. Next slide, please. So we at EPRI, we categorize this into kind of 2 categories. One is grid enhancing technologies. It has something like advanced power flow control, the adaptive line ratings, which have been recently, for example, AAR, which is FERC order, where they want utilities to implement that in operations. Then they're also trying to consider and start building up or analysis for dynamic line ratings, topology optimization control, which we just heard. We also do include this another category because we are trying to build like a robust software which kind of allows all these different technologies to be analyzed or considered together. So in non-wire alternatives, we categorize like the battery storage, demand response, and other things. But I have like grayed out some of this because the software tool we have developed currently supports the green ones, which is advanced power flow control devices and the battery storage. We just started this year to implement or start analyzing the implications of AAR and DLR in this aspect. And we do believe like the battery storage can be used, also can be analyzed, and some of the states have actually already enforced that for long-term planning expansion, the utilities also must perform a non-wire alternative or battery storage study along with the traditional solution of installing new lines or things. That's why we started modeling or including this. And again, it's not the focus that GET would completely replace the traditional approach or everything out there, but we do believe that the non-wire alternatives and these GETs can complement strongly with the conventional transmission expansion projects and increase the utilization of the transmission asset we have right now. Next slide, please. And there are 3 aspects with all these technologies, right? One aspect is we want to clearly understand what these technologies are, how they operate, what are their pros, cons, control options, kind of in-depth knowledge before we start implementing these things. So we want to have a better in-depth understanding. Second aspect is to have tools to model these technologies to perform all those different analysis we do for various studies, right? Reliability, stability, lot of different analysis. So how do we model these things into our tools or softwares or mathematical formulations to perform those analysis? And then third aspect finally is to perform those studies, analyze those cost benefit analysis, and how the implementation actually behaves, or how do this translates into real practical implementations. So these are the three aspects, and EPRI, we are trying to answer all these three aspects right now. Next slide, please. In terms of technology understanding, we do annually publish our technology reference guide. Then the software which I will be talking about today in the coming few slides is cPlanet to address that software gap. And then finally present some case studies we have done so far and what are some of the future stuff which we need to do to address those research gaps and keep moving forward. Next slide, please. So it's an important question, right? We need to understand why do we need this software? So let's imagine you have one transmission overload in your system for one particular scenario, and you are trying to mitigate that overload, and you have few options, like you can install a new parallel line or reconductor the existing line, install a battery, put a phase shift transformer, or the new advanced power flow control technologies like smart wires maybe, and few others. So if you have just one overload, one scenario, you can probably do this a sequential way, all good. But that's not how it is, right? We have many scenarios. Next slide, please. We have many scenarios, many technologies to consider, and there could be multiple overloads. That's where it gets difficult to do it manually. And that's why it's important that we do have these software tools which can minimize that manual analysis time or reduce that manual hours for all the different operators or utility members who are trying to perform this analysis. Next slide, please. So based on this, we kind of develop our problem formulation. The objective here is to consider all these different traditional technologies, grid enhancing technologies, non-wire alternative solutions. Take all these solutions, can we identify the best fit in an economical sense, and also at the same time resolving those transmission congestion overloads across all the scenarios. And it's a difficult problem. Next slide, please. So that's where this tool comes in, which we are developing, called cPlanet. It takes these inputs of all these different technologies, all those different operating scenarios you want to consider, and it does offer both. Like if you want to analyze a preventive solution, corrective solution, you can choose that control options. The output of this whole tool is identifying the location of some of these devices, identifying the ratings or what should be the size of these devices. And along with that, it's also important, because you have multiple scenarios, it may not be needed that all the devices are operating at its maximum or minimum for all the scenarios at all the times. So this solution or this software also provides a solution or the control operating set points for each of these devices under consideration. It could be batteries or power flow control devices, but it does provide location, rating, and operating set points for each of those scenarios. So that's what this tool does. Internally, we are considering DC power flow for keeping it MILP, considering the complexity. So we do have some binary variables in there, but at the end, we do perform full AC power flow verification. Basically, it solves the optimization problem, takes that solution of the devices and location and size and set points, install it into those scenarios, perform the whole AC power flow to make sure all those overloads have been resolved. Next slide, please. So we did some case studies. I'll present a couple of them. Next slide, please. So this one is with air grid system. Here we had 8 different operating scenarios operating scenarios, you mean they can have a difference in the load, generation dispatch, or some contingency kicking in, all those different operating conditions. And for the choice of input technology or candidates, here we considered a mix of new transmission lines, phase shift transformers, batteries, Smart Valve devices, multiple different choices. Next slide, please. And one of the solution which it identified was to install new lines, those green highlighted areas, and have one phase shift transformer solution. The advantage of this tool is it has all the customizable user option, like you can just analyze considering only PST device. You can analyze considering only new lines, and then combination of both. So you can see the difference between all those three different alternative solution, and then pick the best which one suits you, your needs, or because there could be some physical limitations as well, which we do not model into this, but then you can you can think of this as kind of minimizing from those million options to a few where you can then perform more detailed analysis. Next slide, please. This one we did with Great River Energy. The one I was talking about, like in Minnesota, for example, they need to have a non-wire alternative solution analyzed along with their traditional solution method analysis. So they wanted us to perform, they gave us 3 cases, summer and winter. We kind of inputted 30 different bus location choices as where the batteries could be installed. Next slide, please. And here are some of the solutions. In one where we did not put any restriction, we allowed it to pick any number of batteries of any size. It picked 3 new batteries of total 44 megawatts. And then we started adding the restriction that, hey, what if only 2 batteries can be installed? Or what if I want to focus only on one location? So that's the extreme end, where for one battery, it picked the size of 66 megawatt. And in all these solutions, all the overloads were always resolved. And it depends again on the utility case and your needs, which solution do you want to pick? The 3 batteries may be economical, but maybe physically handling just one location is more easier. So the choice is dependent on you. What this tool allows is to perform all those different alternative analysis. Next slide, please. So those were about phase shift transformers, batteries, case study. This one we worked with NYSERDA, where we wanted to analyze more of this new advanced power flow control technologies, which are like modular and scalable, and to see how can we model this technology if we want to perform some analysis and have better understanding how this could be implemented in the physical real grid. Next slide, please. So we implemented this. We used the New York ISO case study, summer peak case. Next slide, please. So consider this. So let's say if you have one future which you are expecting, and we made some modifications to the base case to design this future. And then we consider 40 different locations where you can install these new devices and just perform the optimization analysis with the tool which I just mentioned. What the solution gave us was it picked up 11 different locations where if you install these devices at this 11 different location, it could resolve all the overloads. Next slide, please. And now imagine if you have future 2. The goal of this objective or this case study was to understand that redeployability feature of these devices, where you can redeploy some of this existing devices to some other location if they may not be needed there. But that problem is challenging if you think about it, right? You don't know which device you don't need. You need a good, proper techniques to determine which devices are actually needed and which can be relocated and which can be expanded, or all those different questions you want to answer. So in future 2, again, made some different operational changes, same problem, 40 different locations, and it identified 10 different locations to solve that problem independently for the future 2 itself. But here is the interesting question, right? You don't know which future is going to happen. So how do you design? or how do you plan? Next slide, please. So the question here we are trying to answer is, let's say you start implementing changes, you start planning your things from future one perspective. But what if future two happens? So how do you transition from future one to future two? So what are the changes you need? So we tried to analyze these changes from future one to two in two different things. One, if we cannot move or do anything with existing devices already. And then second, what if we allow that redeployment of some of these devices? So those are the two different analyses we did. Next slide, please. So the first case where I said the redeployment is disabled, so it needed to install one more location, 3 devices, because these are modular, it gets installed per phase. So that's why you see I keep mentioning across 3 phases or 3 devices, 1 per phase. And here the adaptation cost from future 1 to 2 was around approximately $2.5 million. These numbers are for reference. These does not mean the exact cost. There could be more parameters, but the objective here was to show the importance or show that yes, the redeployment feature can be helpful in cost reduction. Next slide, please. So the next solution is where we allow all the existing devices in the future one to be redeployed, because some of those locations may not be needed for the future 2 scenarios which are actually happening. And it did help, like instead of choosing a new device and new location, one of the device got picked up that, oh, okay, we don't need this here and can be relocated. And so the adaptation cost was approx $0.6 million. So the goal again is not to show, okay, quantifying this thing, but to show that, yeah, the redeployability feature that can be helpful in cost reduction. Next slide, please. So to conclude, basically, a combination of all these different technologies could provide and may provide the robust and cost-effective solution in terms of reducing all the overloads in the system. And this tool kind of identifies that feasible optimal solution, but as mentioned, it's using DC power flow model. So we're not saying like, oh, take this solution, get it live, and you're good. No, we do need to perform some more studies. But as I mentioned, there are millions of choices for these technologies and consideration. So this can be used as a screening tool to minimize that millions of choices into few, and then perform that in a more in-depth analysis. And we do need to analyze more for this redeployable or modular new technologies. For example, what should be the operating conditions for in terms of voltage? We are not considering that here because we are focusing here on thermal overloads. But there are many questions which still need to be answered, which we will be working continually. But that's definitely, this is a starting direction. Next step, please. So some of the remarks which we have started working and we would need to, or some research gap, maybe others can get involved. One of them, as I mentioned, we will be start looking into AR and DLR implementation or its risks involved if it is considered for long-term planning. Then recently INL did some study where they show that PFC and DLR in combination provides better solution than individual consideration. So we would like to also extend that, considering all these different grid enhancing technologies in combination, how they make an impact and how they can be useful. And for example, in the redeployment, the third segment, we consider that the whole module which is installed has to be moved. But as I mentioned, these are modular, so there are a lot of bunch of modules. What if only some modules need to be moved? How do you model that in the software? So those are some of the questions which we are trying to look into in the future. I think that's my last slide. Next slide. Thank you.
Thank you so much. Very interesting presentation. Thank you. Any questions?
Russ Fuller, Polaris. Yeah, you did a good job explaining why you need a software tool. I wasn't quite clear on why you think you need a new software tool. And the only thing I saw in your presentation initially was that you said AC. And so I needed to understand why you thought AC was important. But then towards the end of the presentation, I think you said it was DC. So I guess that's the first question. Is it AC or DC?
Yeah, so to clarify, the optimization segment we solve using DC power flow equations to keep the whole optimization problem at MILP, mixed integer linear problem. But then we take that solution because eventually you want to implement these devices in your actual full grid, right? So we just as a post optimization verification, we take that solution, put it into your all the scenarios and perform the full AC power flow analysis, just the power flow, AC power flow analysis to verify whether all the overloads have been mitigated. So that's the DC and AC part, just for verification. And if suppose there are on AC side of solution, there is still some percentage of overload because we have been ignoring the reactive power component, we do go back and adjust some parameters which like the power factor adjustment to make sure the DC solution reflects appropriately on the AC side.
Okay, that makes sense.
Yeah.
But I'm now more confused because what are then the software gaps that you think have required you to develop a new software solution? Because there's commercial tools out there, you're using some in-house that I think have all the functionality that you already have and that you want to have.
Or at least I'm not, pardon me, my knowledge, limited knowledge, but we haven't seen a software tool which does all these technologies together. Like if you want to consider traditional solution plus batteries, plus PSTs, plus smart valves, or all these different technologies together to find a combination or best combination of these projects which needs to be installed. So that's why we started developing this to have this integrated version where all the models can be analyzed together, not just individually and independently.
Well, like I was saying, you actually have a tool in-house that does all those things all together in co-optimized fashion for both operations and capacity expansion. You should talk to Aidan Tui's group and find out about that.
Yeah, but yeah, that's right. But that's from resource adequacy point of view. I think that as far as I'm aware, but yeah, we can discuss.
It's everything across the board: resource adequacy, production cost modeling, and capacity expansion.
Sure. Yeah.
Hi, this is Hao from Princeton. Yeah, I think overall, I think when I was a student, I want to have a software to help me to design the network to achieve some goals. But I mean, for researcher or for like stakeholders, we probably want to have more flexibility on the software, and that comes to my question. Like, will your software provide the capability, let me to incorporate it with different objective functions? Like, it's not just increasing the capacity, because now we want to the reason we want to increase the capacity is to make the system more resilient, which may, like on the topology side, maybe we want to make the network more robust, or we want to make the flow more like make equally distributed so that it can anticipate functional contingencies. So like my first question is like, can your software allow me to incorporate with different optimal objectives to optimize the design? And then the second one, I think, is more about your prelim research or something like the example about the Great River. You are saying, okay, you choose one battery over 3 batteries. I kind of don't understand why, because on the cost, on the capacity, for me, I feel like it seems like the 3rd battery is a better option. It costs less. The capacity is similar. And from my perspective, my experience, it gives the system more robustness, which means when contingency happens, 3 batteries may make the system more reliable or resilient.
Yeah, great question. So to answer first question, yes, this software, we have flexibility to add any new constraint, new objective function, because the whole tool has been developed in-house, including the power flow solver and everything. So it's not like we are using other commercial tool engines that we don't have control over. So it's completely in-house customized. So we do talk with utilities if they have some special needs. We can add more objective functions or more constraints, all of those.
So is that we have to contact you, or you have API for us?
No, this is actually not like a open source public software yet, but yeah. The second, to answer your second question, I'm not saying, we are not saying that you need to use the one battery solution. My point was that you can add those restrictions to understand and analyze different possible solutions. So you can go from unlimited spectrum to more restricted spectrum and pick the solution which best suits you. Sure, if you think that 3 battery locations would be more robust flexibility for you and easy, it depends on utility. We don't enforce any solution to be implemented. The point I was making that if you just have one battery location, it may be easier to control to just visit one location or to do installation, things like that. So the cost difference, because every time you pick a new cost, there could be location or other fixed cost and things. We don't know there could be some physical limitations, but yeah.
But maybe I'm too picky about the numbers. But when you were saying like the installation costs and everything, the number you gave us.
Yeah, it accounts for that, and that's why I'm saying the physical limitation. Okay. We don't know.
Okay, that part you are not including to your model.
Yes, because we don't know how the area looks like or how that. So that we would need to take feedback from the utility, and they will see. Oh, okay, this 3 solution looks good, but this may not be suitable. So let's go with 2 solution. Maybe not 1, maybe 2. So that's up to them.
Okay, 2 more. One here and one online, but
yeah, thank you for the presentation. Being RIT, actually I have a similar question related to number of batteries. So you are using a fixed cost like 2.2 million per megawatt for the battery. If this cost is fixed and doesn't change with the size, then that means like just cost-wise, like 2 smaller batteries are the same as 1 larger battery. So do you provide the kind of flexibility for the cost, let it vary with the size?
Right now, as you notice, we do not go into megawatt hour, so it's not energy. We just kind of consider the aggregate. So that's the total size you will need at that location. How do we want to disaggregate that or perform more detail? We do that as a next step called cost benefit analysis, where you can pick your type of batteries, rated batteries, and those things. So that's why this kind of acts as a screening tool rather than like take a final solution. But the focus here was you may have those million choices to analyze, right? So that's the goal here, is to reduce that to few and then focus on next more detailed analysis from these things.
Okay, so if here only the total capacity is considered, then in your example, the 3 batteries, they are at different locations?
Yes, they are different locations. Yes, definitely.
Okay.
Yeah.
Okay, yeah, thank you.
Yeah, it's 3 locations versus 1 location.
And quick one online.
Hi, yes, Austin Anderson. Can you please unmute yourself and ask your question?
Hi, question about the tool capability between choosing between different technologies for transmission line, AC, DC, multi-terminal, DC, voltage source converter technologies, or how those different technologies are realized within the tool?
We are not considering HVDC technologies yet into this right now, because as we are trying, the power flow side is the DC power flow. So what we do is from the DC power flow perspective, we kind of convert that HVDC into a fixed power transfer with a high impedance, just for DC power flow representation. But in terms of technology that it supports right now is new transmission line, new substations, reconductoring the existing line with a better conductor material or higher rating, the smart wall devices, battery storage, reactors, phase shift transformers.
Okay. And just a follow-up, when you said reconducting, is it like reconducting a current corridor or perhaps adding a parallel line in an existing line? So is this like also an option you have been considering?
Yes, yeah, thanks. That's a great question. Yes, the tool allows both to install a parallel line, or you considering option where you remove the existing line and put a better line. So tool has that both options being considered. Like as a user, you can put both of those options.
Thank you.
Yeah, thanks.
Thank you so much. Let's give him another round of applause. All right. Moving on to the next presentation. This one will be virtual. We have Rupa Matha Vidarama with Smart Grids. The presentation is entitled Key Role of Extended ACOPF-based Decision-Making for Supporting Clean, Cost-Effective, and Reliable, Resilient Electricity Services. So can we just, while the slides are coming up, can you test your audio?
Sure. Sure. Can you hear me?
Yes, if you could speak a slightly louder, that would be great.
Okay, I'll try my best to
Sounds
speak
good.
louder.
And 1 more minute for the slide. Oh, are you sharing your screen?
Yes.
Okay, great.
Are my slides visible here?
Yes, we can see them. Thank you.
Okay. Sorry, 1 moment. Okay, let me get started. Good afternoon, everyone. Firstly, thank you very much for giving me this opportunity to present here today virtually. Yeah, my name is Rupa and I work at Smart Grids. It was previously actually called NetSyn Corporation. At Smart Grids, we work on developing improved software solutions to utilities and other stakeholders with an objective of providing clean, efficient, and reliable electricity services. Today, I'm going to talk about the key role of utilizing AC optimal power flow in meeting these objectives. So we'll begin by briefly summarizing the ever-evolving objectives of sustainable electricity service. We'll then briefly describe fundamental challenges to using today's software for meeting these objectives. We'll then make the case that these objectives can be overcome by utilizing our core software called AC Extended Optimal Power Flow. We'll explain how it works and how it is capable of resolving often contradicting objectives of providing energy services. This core software is embedded into a general tool called iTroops, which stands for Implementation Aware Tool for Reliable Operation of Power Systems. We illustrate the potential capabilities of using such a tool in solving several open problems that are faced by the industry. Objectives of sustainable electricity service are basically threefold. Ideally, we'd like to achieve lower carbon emissions at a cost as low as possible while ensuring reliable operations and resiliency during extreme events. Meeting low carbon objectives entails having to replace fossil fuels with renewable resources, integrating demand response, and also beginning to utilize storage to manage intermittency of renewable resources. Implementing these new technologies, however, raises serious concerns regarding generation adequacy, ability of the grid to deliver the power for qualitatively different types of power flows while meeting customer preferences. Similarly, these new resources are supposed to be added and utilized in a cost-effective manner. This requires co-optimization of planning and their flexible resource utilization while reducing the delivery costs created by adding new infrastructures. Many new open problems arise as we do this, in particular with respect to valuing short-term and longer-term uncertainties, and planning for the least cost deliverable reserves to manage these uncertainties. Notably, planning and operating these changing systems so that the resources are used efficiently while at the same time having their costs recovered in such an uncertain environment is a major open challenge. An entire set of new engineering problems further emerge when we talk about providing reliable and resilient service. Previously unseen or non-dominant grid operating problems now show up. This is mainly because the grid was previously designed for implementation of power delivery for vastly different types of power flow patterns. Relevant for the conference is that today's software does not lend itself in a straightforward manner to supporting flexible resource planning and their utilization in a highly dynamic environment. Listed here under these tabs are several potential problems and which must be solved on the way to decarbonization. Under these different tabs here, we've also listed the ways in which the problems are addressed through existing software solutions and some of the challenges that these existing software face as they try to solve these problems. Without going through each of these problems one by one, we observe that using today's software has two major problems. First, most of these tools are still DC power flow based and as such are not physically implementable. For the solution to be physically implementable, all the physical constraints will have to be met. As a result, if one were to use DC power flow based tools, it becomes necessary to perform excessively time-consuming if-then scenarios to find solutions which would be physically implementable. This is truly a major roadblock to moving forward. And the second thing is that most tools are analysis-based and they operate under the assumption that no other controllable equipment can be simultaneously utilized to meet the given performance objective of interest. For example, when assessing power transfer limits for wind power integration, today's approach is to incrementally increase the wind power in one area and increase the load at the receiving end. The increment at which power flow begins to fail is deemed as the limit for how much wind can be utilized. The rest just gets spilled. To avoid these two deeply rooted industry software problems, that is utilizing DC power flow based solutions and lack of optimization tools to support power delivery, we propose to utilize our AC extended optimal power flow software for planning and operations. In contrast to typical AC power flow tool, the key features of ACOPF include utilizing all the available grid control equipment for optimizing voltage profile. If the system power flows are infeasible, the tool automatically detects the reason for infeasibility and the means to eliminate them. Software also has comprehensive error checking tools embedded and has already been validated against multiple utility software solutions. Software also has the capability of accommodating different optimization objectives. For instance, it can optimize real, reactive, or apparent power flows, but also the software's main capability lies in it identifying the grid operating bottlenecks through the activation of the other objectives of optimal branch flow or voltage management or optimal load distribution in an automated manner if and when it witnesses congestion or other power delivery problems. The software simultaneously determines the optimal resource allocation and any other grid control actions that will have to be taken, all while observing the physical limits and resource constraints. So the software has its own graphical user interface through which the users can interact and perform any type of analysis. Alternatively, scripting languages can be utilized to invoke the optimization engine for automating the sequence of different ACOPF runs for different operating or planning problems of interest. This is specifically how the tool iTroops is developed over time. iTroops basically allows commonly utilized inputs such as the PSSC format files. In addition, the user has the ability to select the available control equipment or the performance objective of interest. And on top of that, the user could select either corrective solutions as the system operating conditions change, or preventive solutions to plan for resource sufficiency, especially for deviant operating conditions often created by outages or unplanned renewable penetration. In the end, iTroops outputs files that include the critical constraints to optimizing the performance of interest. It further provides advisory combination of optimal set of adjustments to improve the performance of interest. Just to give a sense of this tool, here is a prototypical GUI of iTroops. It has the means for feeding PSSC type input files. It can also take reserve designation files with the ramp rates and other types of time varying inputs such as the load data or the renewable data. Through the permissible control panel here, the user can select the different control equipment that's available for use and their settings. The scheduling approach panel here allows the user to select preventive or corrective dispatch strategy. It also has embedded several contingency screening tools to perform analysis for the preventive strategy. Alternatively, a known set of critical contingency events can also be provided as another input file. Many different optimization objectives pertaining to different operating or planning problems of interest have been incorporated into this tool over time. They include the objectives that I already mentioned earlier while talking about the performance objectives for the ACOPF software, but it also has additional performance objectives such as minimizing the number of actions needed or minimizing the megawatt redispatch, or the user can also select a combination of several of these objectives. The outputs finally can be accessed through one of these tabs. They include identification of critical bottlenecks and advisory set of actions that the operator or planner could take to improve the performance. To summarize, listed here are the unique features of iTroops, which basically strive to overcome all the fundamental deficiencies of today's software. Since iTroops is fundamentally built on top of the very well-tested, robust ACOPF software, it models all physical grid and resource constraints, and therefore it results in physically implementable solutions. And it also results in much better performance than what is achievable with today's software. Different capabilities of iTroops are listed here. They include actually several different open problems that are faced by the industry today, some of which I'll talk about in the rest of this presentation. At the beginning of the presentation, I mentioned that we'd like to be able to address the main objectives of sustainable electricity service, that is to lower carbon emissions, second to lower the costs, and third to ensure grid resiliency. Let me begin by showing the estimated benefits of using iTroops for the first objective of equipping more clean energy resources. Here are some real-world examples that we have worked with. So on the left, we have shown here the Azores Islands in Portugal, and the objective was to integrate 100% renewable energy with our iTroops software. We were able to accommodate 100% renewables, and in doing so, we have also seen that the prices could be reduced from about $200 per megawatt hour to $88 per megawatt hour. We have also shown different levels of penetration of demand side response with electric vehicles and also with HVAC systems. more of these studies can be accessed in this link that we have provided here. We have actually published a book on several of the cases that we studied on Azure Silence. And on the right here is the German grid that we have studied, where the objective was to transfer wind from Northwest Germany to Bavaria. We showed that with the usage of our software, the wind spill can be minimized drastically. These two case studies demonstrate the role of using advanced software and supporting wind or solar integration to thereby reduce carbon emissions. Next, for demonstrating the efficient utilization of resources, we turn to an early study that we conducted on NPCC system. It basically comprises of systems that are coordinated by different owners. It involves 3 ISOs and many TSOs. We concluded from this study that with the usage of grid control equipment, we can heavily influence the economic dispatch outcomes. In this table, we have activated different grid control equipment and showed how the voltage support becomes essential for having larger amounts of cheaper renewable energy exchanged across the different coordinating areas and thereby reduce the generation cost. Also, we have acquired much knowledge through simulations and interactions with utilities in the Northeast US. We've also concluded that one could deliver 1 gigawatt power from Niagara to New York City on a hot summer day beyond what is being done today. So the takeaway here is that the same grid with minor enhancements at right locations is all what is needed to accommodate the transition in the energy mix that we are envisioning. Next major objective of interest is to ensure reliable and resilient operation. So on the left, we show a study that we have conducted on Eastern interconnection. So from this study, we have seen that all the blackouts from 1970s through 2003 could have been avoided if one could have used ACOPF-based solutions for optimizing voltage profile. At the same time, we have also shown on Puerto Rico system, which is shown here, a representative bulk power system is shown in the sketch here for the Puerto Rico system. Here are the demonstrations that we have conducted using iTroops for serving end users, especially when there is a hurricane event. So when there is a hurricane event, managing N-K where K greater than equal to 2, it becomes a major software challenge because many different equipment fail simultaneously. So we have shown with our software that dramatic improvements can be obtained wherein higher critical load could be served by the usage of our software, where individual islands could serve the load by themselves through the usage of our software. No other software, to our knowledge, is capable of identifying the most effective actions to reduce loss of load for these types of N-K type catastrophic events. Basically, in summary, iTroops can be used as standalone software, and its various different capabilities lead to radically new solutions to several different open problems that some of which I have discussed briefly. But also iTroops can be used interactively with, say, legacy tools in use by system operators or planners today. Shown here is an example of the information flow between iTroops and the existing utility tools for this study was basically conducted to verify 10-minute reserve deliverability for critical contingencies. So iTroops essentially identifies the binding constraints, advisory actions that could be taken, and additional reserve requirements that would be needed to mitigate some of these contingencies. And this list can be utilized by the utility SCED software. and those constraints can be added into the SCED software, and the resulting schedules can again feed iTroops, and these iterations proceed until convergence or until the desired reliability criteria is met, for instance. So overall, with various different studies we have conducted over years, iTroops has shown remarkable benefits, and yeah, if I had more time, I probably would have been able to show a real-time demonstration of iTroops, but I'd be happy to show these demos to anyone interested offline. Please feel free to, send me or anyone on the team an email. With that, I'd like to conclude my presentation. Thank you.
Thank you so much. Any questions? Go ahead. 1 second.
Thank you for the presentation, being from RIT. So I have a quick question related to the models and the methods. So what models are used for the AC power flow? Is that like a black box, or we have options to choose? Like what type of AC power flow model you want to use? And second question is related to solution methodology, the method. Is the same question. So do we have options to choose like what method we want to use to solve the problem? And also one more question is related to computational efficiency. So for the example you presented, how long it takes to get the results?
Sure. Yeah, thank you very much for your question. So firstly, the software actually considers all the AC power flow constraints. It's actually performing AC optimal power flow. So it's basically co-optimizing the generation or load schedules, and also the grid control equipment that could be optimized for given load or contingency scenarios, basically. And to answer your second question, with respect to the methods used, so the core software ACOPF involves very well tested algorithm that utilizes Cplex software internally, but the way in which it overcomes the infeasibility issues is the company protected IP. So, but we can have more discussion on that offline. And thirdly, with respect to solution times, we have worked with really large grids with even like 20,000 node systems and so on. For like one ACOPF run, it could take less than 5 minutes is what I want to say. But it depends also on the type of on the computer we are using. On a Windows 64-bit machine with I think that I was able to solve like a 20,000 node system within 3 minutes.
3 minutes. Okay. Yeah. Thank you.
For a speaker? And none online? All right, well, let's thank her again.
Thank you all.
All right. So next we have data and API standards for clean energy solutions and digital innovation. We have Priya Barua from the Clean Energy Buyers Institute with us here in person, and then her colleague Ben Gerber from M-Emirates will be joining us virtually. So just a heads up, Rob, that that's going to be happening.
Great. Well, thank you. There's Ben. Thank you, everyone. And I'm Priya Barua. I'm with the Clean Energy Buyers Association, and as you can see, Ben is joining remotely. I do have slides, which I don't know if. Okay. Perfect. Fantastic. So we can start with the next slide. Fantastic. So the Clean Energy Buyers Association, or CEBA as we're called, is a business trade association that activates a community of energy customers and partners to deploy market and policy solutions for a carbon-free energy system. We currently have more than 400 members that represent more than 7 trillion in annual revenues and 16 million employees. And that includes institutional energy customers of every type and size. So there's corporate and industrial customers, universities, cities, federal agencies, to name a few. The Clean Energy Buyers Institute is affiliated with CEBA and is an energy customer-oriented nonprofit focused on really solving the toughest market and policy barriers to achieving a carbon-free energy system. And we do that in collaboration with policymakers, philanthropies, and energy market stakeholders. And the reason I bring this context up is that access to standardized, harmonized energy and emissions data through centralized platforms to really help support a broader range of impactful clean energy solutions is a challenge that we're tackling across both CEBA and SEBI. And Ben will introduce MRETS, but MRETS we work closely and collaborate closely with, and MRETS happens to be a member as well. So let me start by laying out why this data is important to energy customers. So next slide, please. So energy customers need this data for 3 key purposes: decision-making around siting facilities and clean energy procurement. So energy data helps customers to set their targets or goals, and then granular emissions data, such as average emissions or marginal emissions data, can also help customers perform carbon-optimized load shifting, help to accurately measure the decarbonization performance of clean energy projects, and help customers site projects and facilities in the most impactful areas to meet their clean energy goals. So that's one kind of reason they need this. Then they need the data for voluntary greenhouse gas reporting. So thousands of companies follow the greenhouse gas protocol guidance with established hierarchies for eligible data and quality, and they report this to various platforms, including CDP. And then finally, they need this data for compliance. The US Securities and Exchange Commission proposed rules for climate disclosure, and that would require all public companies to accelerate their plans to capture, measure, and disclose emissions data following the GHGP or other robust methodologies. And standardized granular data will be critical to helping customers better calculate and answer the SEC guidelines with greater accuracy. So that's really why there is a data imperative. Next slide, please. In addition to these needs, we're also seeing an increased drive amongst customers towards more impactful and carbon-focused strategies, whether that's targeting procurement towards times and places of the greatest decarbonization impact, which is also sometimes referred to as emissionality, or matching electricity consumption on a local and temporal basis, such as on a 24/7 basis. And this includes corporates, federal agencies that need to meet the president's executive order, cities, universities, and small end users that want to better understand their electricity consumption data or make decisions based on emissions impact. So energy customers that are really trying to pursue 24/7 hourly matching are looking to drive grid transformation through increased carbon-free electricity deployment and advanced technology solutions in local grids where they have facilities. So they need more granular information, especially hourly emissions data, to identify the dirtiest grids and times to really calculate their impact. And similarly, energy customers that are pursuing more of kind of an emissionality focused strategy are looking at reducing emissions by targeting their carbon-free electricity procurement in the most carbon-intensive times and places, regardless of where their facilities are located, recognizing that the avoided emissions of bringing a clean energy project to a high emissions intensity area is much higher than siting it in a cleaner grid. So more granular information, especially marginal emissions factors, is needed to really calculate these avoided emissions. And underlying all of this is the need for accessible, standardized granular emissions data So that's really critical for customers being able to pursue these strategies more effectively and to enable even more energy customers to be able to pursue these types of energy strategies. The current policy context also makes this data even more critical with tax incentives and other provisions under IRA, that could really accelerate the timeline for and further improve economics of clean energy deployment, which would drive further demand for this type of data from customers. So next slide, please. So I've talked a lot about why this data is needed. So now I'll kind of dive into what is the actual data that is needed to support energy customers across that spectrum of needs. So for basic greenhouse gas accounting and reporting, customers need average emissions of delivered electricity and the resource mix specific to their supplier. The two methods that customers need to follow to calculate or report emissions from purchased electricity. And I'm not going to dive into the details of that, but that's kind of the essentially the data that's required. And then, of course, as I've outlined on the previous slide, for hourly matching, customers need access to granular hourly data. And for procuring carbon-free electricity in the most carbon-intensive places and times, customers needs access to granular marginal emissions factors. And then across the board, across all of these needs, calculating a customer's impact and avoiding double counting the actions of other customers requires a residual grid mix, which is really defined as the emissions factors of the grid once all RECs, which is renewable energy certificates, and customer claims have been factored out. And the residual mix is increasingly important as customers, as customer-driven clean energy really increases. So next slide, please. So now that we know what data is needed, I'm going to move to the key challenges that energy customers face today. So customers do not have complete access to standardized, transparent, and reliable grid and GHG emissions data to inform their decision making. They also rely on a mix of different data sources with very differing levels of granularity to make informed procurement decisions. And then even where some of this data is available, it's not always available in a digital format or in a centralized location. So it requires someone looking in multiple sources or scouring through spreadsheets to really attain the relevant information. So, in some places there may also need to be investments in electric company software solutions so that customers have better access to the energy usage, which is sometimes also hard to determine. And then also the system, in addition to the system resource mix and associated carbon emissions on a more granular basis. So next slide, please. So diving into that a little bit, I wanted to kind of give you an overview of what is available to customers today. So the Energy Information Agency's hourly grid monitor dashboard has traditionally collected information at the power plant level versus kind of delivered supply. They just started publishing hourly data on CO2 emissions intensity for every balancing authority and subregions of large balancing authorities this January. Which is currently available in a downloadable spreadsheet format, but this doesn't include marginal emissions and residual mix data and is not available through a dashboard yet. EPA provides eGrid data, which is another data source that a lot of customers rely on, and this is average grid emissions factors, but this generally has a time lag of a few years, does not include hourly data, and is not specific enough to delivered supply. Then you have data available from some RTOs, but RTO mixes do not include delivered electricity, and the granularity of available data really varies a lot across regions. There are currently only 3 tracking systems that have the capability to track hourly data, and MLETS is one of them with evolving functionality. And then you have residual mix data, which is extremely limited, is not comprehensive or consistent, and is definitely not granular. There are some data provider platforms that are trying to fill the gap around marginal emissions, but they face some constraints based on publicly available data, and they might apply different calculation methodologies for marginal emissions rates. Next slide, please. So there are some important things that RTOs, FERC, and EIA can do to help make this data more accessible to energy customers. So it'd be really helpful if RTOs could make grid mix data publicly available, collect and publish granular emissions data, and report data to EIA along with utilities. And at the federal level, it'd be really helpful if FERC and EIA could harmonize data collection methodologies and provide centralized access to information through EIA's dashboard. EIA is taking some steps in that direction, but there is more work to be done there. Next slide, please. There are some standardization initiatives that are currently underway. So the Linux Foundation Energy has the Carbon Data Specification Consortium, and the Carbon Data Specification is really a data dictionary for raw data and a standard for data requirements that enable energy data access for measuring, quantifying, and tracking carbon emissions from energy production and consumption. And these standards and requirements are designed to really try and boost confidence in data sources, increase data utilization, and promote scalability and allow aggregation across centralized platforms. This is a global consortium that includes stakeholders from utilities, power systems, engineers, power system software maintainers, corporates, and others. And so that there's some conversations happening around that. The Clean Energy Accounting Project, which is run by the Center for Resource Solutions, is also trying to develop standardized stakeholder-reviewed clean energy and greenhouse gas emissions accounting guidance, addressing outstanding questions in some of the voluntary and regulatory markets. Energy Tag is an independent nonprofit initiative to define and build a market for granular certificates that really enables energy users to verify the source of their electricity and carbon emissions in real time. And Energy Tag has been launched to develop a standard for renewable energy users to track the provenance of their energy on an hourly basis. And then even EEI has tried to develop a database to support corporate customers in their sustainability reporting efforts. And this provides CO2 emissions intensity rates and resource mix information, but it's a completely voluntary initiative for utility members, and calculation methodologies vary quite significantly across utilities that report data into this database. So the next slide. We really recommend the need to digitalize data collection and display as much as possible and access to an application programming interface or API so that there is a centralized access point. Large energy customers, including many corporates, spend at least 1 to 3 months every year pulling their data, both consumption and procurement, and then overlaying them. So this should be able to be done a little bit more easily through an API. And so, I'm going to actually now pass it on to Ben, who is at MRETS, to talk us through what he's seeing and facing from a tracking system perspective. So Ben, over to you.
Yeah, thank you, everyone. And Priya, are you able to hear me?
Yes, we can hear you.
Okay, awesome. Are you able to advance to the next slide? And then the next.
Oh, you might have to switch slide, I think.
Rob, we might have to switch to Ben
Ben
Gerber for 39. There's a second set of slides in the with number 39.
There we go.
Perfect. Thank you.
Okay. All right. Thank you very much. My name is Ben Gerber. I'm President and CEO of MRETS. If you can jump to the next slide, please. Well, thank you again for having me. A little bit about MRETS. We are a nonprofit environmental attribute tracking system. We are our name is indicative of the Midwest. However, we are more than that now. We track across North America for voluntary purposes and for compliance. So, for example, RPS standards or federal energy standards. We track those in the Midwest. We now recently, less than a year ago, launched tracking of the WEC green energy system. So the Western Renewable Energy Generation Information System, or REGIS, now utilizes MRET's underlying tech platform. We've grown quite a bit, and we've really transitioned just from being a nonprofit that administers a registry to becoming a technology provider. And that's really what has precipitated a lot of these conversations that we've had about the need for better access, especially being a smaller not-for-profit technology provider, there's a lot of barriers to acquiring data that we didn't anticipate that not only add to our costs, but add to costs in the overall ecosystem. We are managed by a board of directors that includes state regulators, investor-owned co-op and muni utilities, as well as independent energy systems experts. So really, what is the problem? And I think the best way to describe it is a quote that I am pulling a little bit out of context, but I think, well, I think rightly so, from the Hamilton Project, which is out of the Stanford School of Sustainability. And one of the things that a report that they recently published said is they describe moving energy between balancing authorities as moving at the speed of lawyers and not light. As a recovering regulatory utility attorney, I feel like that's really the best way to describe it. But however, in a similar vein, we're seeing the needs of customers, and those customers that people like Priya represent, and I'm also, in full disclosure, on the board of the Clean Energy Buyers Alliance. But those needs of the customers are growing at the speed of light. However, access and the standardization of that data is moving also at the speed of lawyers, and that's been a huge frustration for us. So we're using this idea of 24/7 CFE and emissionality as a use case to describe what some of the major problems are and what we can do. If you can go to the next slide, please. And what we're seeing is this movement to what I like to call data-driven decarbonization. And really, it's looking at how we can balance production information, both zero carbon, so not just renewables anymore, but nuclear as well. And then the associated emissions with that on the grid. As you heard from Priya, there's kind of two issues that we see. And moving to a granular process. So RECs used to historically be issued in monthly chunks as equivalent to 1 megawatt hour. However, we're seeing this transition, and MRETS has helped pioneer this along with Energy Tag at a global level in moving to a granular production and consumption matching. And regardless of whether a goal, for example, Google has a 24/7 CFE goal, or the goal is emissionality driven, which is where can you make investments on the grid to have the maximum carbon impact and quantify it. So that's the idea of emissionality. You need to get this granular production and consumption data. And right now that's really, really hard to do. And what we're seeing is in some cases, a lack of alignment in the access to that data, or in some cases, a lack of standardization. So for example, it's really great that that PJM already provides via API through their website locational marginal emissions data. Now, I have some personal criticisms of it. For example, it treats imported energy as zero carbon, but they are unique in that they provide access to that data. And we'd like to see not just PJM do that, but other RTOs and ISOs provide that level of data, but do it in a standardized way so that we're comparing apples to apples. If you can go to the next slide, please. So this information is really important. One for providing more efficient market signals. So outside of just the pure electricity market and the trading of or production and consumption of the physical electricity, the markets that surround like environmental attributes actually can have significant impact. And so being able to match buyer demand with consumption is really important, and can also help alleviate market stabilizing swings. Better generation development planning, so understanding where there's demands for renewable power at a consumer level at an hourly or more granular basis than monthly or annual, and so where it's demanded and where it's produced, and ensuring that there's a match there, especially at an hourly level, is really critical. And then battery storage markets. So I know there's been some presentations about battery storage, but if there is an interest in ensuring that storage isn't just a resilience tool, which is also very important, but helps ensure that there's decarbonization benefits. So there are people that look at battery storage, not just for resiliency and other grid stability, but also as a decarbonization tool, getting access to that data is really critical. And there needs to be a suite of technology products. And there are companies, like Granular, Singularity Energy are all working on this, FlexiDAO. However, what we're seeing is that the growth of the ecosystem is really slowed by access to this data. And if you go to the next slide, please. One of the things we're seeing is that all this is really being lost in translation. And what are some of the key data blockers so there's a lack of data access and standards. So one of the examples I use is when we were finally able to negotiate getting hourly data from an RTO, when I handed over the API specs to, well, first of all, it took us 2 years to do that because we were initially rebuffed. But then once we got it, after having a large customer intervene, when I handed the API specs to our in-house development team, they asked me, like, is this a joke? And I was like, no, I don't know enough about this to make this funny. And like, this is what we studied 10 years ago on how not to set up an API. And so, I mean, this is not, I'm not trying to shame anybody, but this is where we see that some of the regulation leads to, outdated and very expensive, by the way, implementation processes. And then each data provider, whether it's an ISO, RTO, utility, are going to have different ways to provide the data. And it's really important that if we want to grow a ecosystem around these tools to help decarbonize the grid, it's going to be important to standardize this, much like the cloud providers were able to help standardize data to move them between systems efficiently. And we need these to be not just North America or US based, but really global. And so providing API access in a standardized way, as well as standardizing the contracts, so the requirements, both from a security standpoint, which are real and significant, and then the way that data is handled will really help grow the market and opportunities around this area. And I think organizations like FERC have a really, really important role to play. Another example that we've given is we were asking for one data point from one RTO, and they said, well, that's confidential under our FERC approved tariff. And then it's the same data point that another RTO is publishing via API in a little bit different way. So that, I mean, it's not a totally apples to apples comparison, but enough that we think it's exemplary of some of the problems that we're seeing, which is this. And why is this important? It's not just the ecosystem around, so it's not just for-profit entities, it's also the government. So ensuring that 45V, which is the green hydrogen incentive that was passed by Congress and is currently in the implementation phase by the federal agencies, being able to verify data and to have either the government do it or third parties do it, to have to individually negotiate access to all of this data, both at a contractual level and a standardized data level. It's going to be really costly and burdensome, makes it a lot more difficult and costly to administer these important government programs. The same thing with meter access, the inability to, for utility. I know, for example, I live in an area that doesn't have any smart meters. I know more about what's happening through my own access to my home solar system than the utility does. And we want to help try to correct some of these things by working through a standardization process. And my 10 minutes is up, so I wanted to open it up for questions with Priya.
Does anyone have questions for Priya and Ben?
Yeah, thank you too for the nice presentation. I think it's a very meaningful work. So I have like 2 questions. So first question is like later on in the future when you have a sufficient data, will you consider like kind of developing like a phone app? So either it's an individual app or it's embedded in a utility company's app. So I can have like a real-time display of emissions in my area. That's like one thing, just a display. And secondly, is that possible to predict the emission? For example, if I can check if I reduce 1 kilowatt hour power within my house, like how much emission I can reduce, or if I like kind of reduce my setup point of my AC by 1 temperature, and what will be the corresponding emission that I can reduce? That's the first question. And second question, if we can do that, how can we handle this kind of data privacy issue? Am I related to like an individual customer?
Yeah, so there are some tools, like I think Nest thermostats are one that try to do that, and it's really great. However, they there's no standardized way to both access this data, and a lot of them are using models. So I mean, I always hate to be speaking on behalf of others that may not be there, but we were having a discussion with an organization that does provide modeled marginal emissions data. And one of the tools, one of their inputs is EPA eGrid data. Well, when you talk to EPA, they were like, well, eGrid data isn't really supposed to be used for that because it's at best 1 year old, sometimes 4 years old. It's really, it's a tool to help you understand what's happening, but not necessarily make those actual real-time decisions. And so if we had better access to that, like for example, PJM's LME data that's available, if you could pull that via API, if MISO had that same data available via API and CAISO, you'd be able to, and if they use the same inputs and modeling to provide that number, you could have a much better idea of what it's like to lower 1 degree in California versus Minnesota versus Illinois. And I think then being able to quantify those benefits. So one of the things we've seen is at an energy efficiency, people tried to create energy efficiency certificate markets. And whether you agree with that or not, one of the reasons why they didn't take off is that 4 to 5 years ago, when there was interest, there was no way to integrate estimated avoided emissions into that, which is its own controversial topic. But if you could give somebody not just the financial benefit of reducing their energy usage when emissions are high and prices are high, but also give them the benefit of the carbon savings, that would be an extra incentive. I used to work for large C&I customers who say a lot of times it was better for them to just pay the penalty than shed load on their interruptible tariffs because it cost them more to shut down their lines. Now those companies 4 years ago didn't have carbon goals. Now that a lot of them do. And so if they could integrate that, there's an extra incentive. I'm not going to say that it's going to make them do that, but it's building these incentives into these marketplaces will be really critical. But if we're not comparing apples to apples, and right now can't even get a lot of this data, we're really stuck in moving forward and kind of going back to that moving at the speed of lawyers and not light. Sorry to all the lawyers in the audience.
Yeah, thank you for the nice insights. Yeah. Oh yeah, privacy question. So if we can do that, then which means my input, like I want to reduce 1 kilowatt, I want to reduce my temperature set point, those data will be collected. So how can we provide this, prevent this kind of data issue? I do want to reduce, but I don't want others to use my data.
Yeah, no, Priya, do you have any thoughts on that? I
mean, I think that's a good question. It's not something that I've looked into, I have to admit. And again, a lot of the customers we're working with are like large energy customers for whom, you know, I think they're really they have these sustainability clean energy goals that they're really trying to, and they really want to maximize their decarbonization impact. So, you know, I think it's not necessarily just like somebody at home who I think might have some more privacy control concerns about that type of information. Although, again, you know, I haven't really thought about it. I don't know, Ben, if you have thoughts.
Yeah, I've thought about it probably more than I would like to admit. And it's more in the context actually of national security, and not necessarily home. So some of you might be aware the federal government has a 24/7 goal that was implemented under the Biden administration. I believe is it 50% by 2030 of all federal buildings. And so, you know, when we've talked with groups like the Defense Logistics Agency, so it's one thing to understand, you know, a state court system's hourly, you know, consumption usage. The value of that probably pretty low. The value of somebody potentially a hostile foreign entity understanding an NSA data center's hourly energy usage, pretty significant. So it is going to require And as a data provider and someone in the middle of all this, we understand that it's going to require us to also harden our infrastructure. And I've been thinking about that a lot today because we're scheduling our pen testing. But yeah, it's a real issue, and it's going to also, I think, asking for these standards also comes with some responsibilities, and those responsibilities will be really critical in protecting that type of information. And there's a trade-off there, right? Like, I think about, giving my utility access to my smart thermostat so they can turn down the air conditioning when power prices are really high might make me a little bit uncomfortable, but I get, $100 a year off my energy bill, right? So there are those trade-offs, and I think, whether these are opt-in programs, for us, I think that the real the reason we're here and we think we've been really pushing on this hard is that we don't even have access to this data in an efficient, standardized way. And then I think we also do, in concert with those discussions, have to provide the appropriate protections.
Yeah. Thank you.
Thanks, Bing. And thanks for the answers. Time for maybe like one more question.
Nobody's asking it. I will. It's jocular. Be advised. So I missed the connection with the reference to lost in translation. So this is what were you trying to say there? On the slide where you made the reference to the lost in translation movie, what was your point?
Yeah, so one of the biggest problems that we've had is that, for example, the lack of standardization I look at things as both process standardization and data standardization. And so if you have one part of the country saying this is how we calculate locational marginal emissions, and you have another part of the country saying this is how we calculate locational marginal emissions. So for example, PJM treats imported energy as zero. And then you have another part of the country, let's say the Cal ISO says, well, imported energy is the average emissions from wherever we're importing it into. You're not really looking at an apples to apples comparison. And so you have this issue of how do we compare this data? Because in the end, these are global entities that are looking for this. And that's also why it needs to be global in nature, is understanding carbon emissions. If we all calculate it differently, there's very little value in it. And so if we're using different data sources, but we're not opening up access to data sources in the same way, we're going to be producing numbers and making decisions off of data in different ways, and that's problematic.
Okay, thanks. I can think of a better reference, and I may send you one. So thank you.
Yeah, please send. No, I'm not good at those things, so I appreciate you. Please call me out on that.
All right. Thanks again to Priya and Ben. All right, and last but not least, we have Daniel Beanstalk from Columbia University presenting mine production scheduling under time of use power rates with renewable energy sources. So just 1 second. The slides will be up. And then just adjust this when you start.
Okay, ready to go. All right. Well, I'd like to thank FERC for having me again, and I would like to thank the attendees for sticking around to the bitter end. Hope nobody falls asleep. So several of you know me. I work on optimization and on power engineering applications of optimization. And in the last 10 years or more, I benefited from a number of funded programs from DOE and from ARPA-E. In particular, I've been in one of the PERFORM programs. PERFORM seeks to adapt the energy markets to make them better suited for this quickly coming future that we've all been talking about in the last few days. Make the markets more adaptable, more flexible in the face of volatility coming from many sources. Part of the goal, given that this is ARPA-E, part of the goal of PERFORM is to actually have an impact in the practice to engage with industry, with any and all
participants in energy markets. As many of you know, it's not easy. It has not been easy to get the ISOs to change. Oh, thank you. Could have pointed. It's not easy to get the ISOs to change. It's only been for us. It's only been in the last year or so that they have shown actual willingness to change and to rethink how they participate in energy markets, how to take on and how to think about financial risk and how financial risk impacts physical risk. I'm sure all of you are interested in this. But also going beyond the ISOs, anybody with any industry with large exposure to energy markets should think about that and not just simply buy energy, but probably participate in the markets in some form. And that is even more challenging. Next slide, please. So for this project, and in terms of what I just said, I'm collaborating with these very talented ladies who are primarily mining engineers. Alexandra Newman has a background in optimization, but she's been working in mining and in heavy industry for a long time. Andrea Berkey is a mining engineer, and Amy McBrayer just got her PhD in mining, and she's going to be teaching mining somewhere, I forget. And the other two are PhD students. The mining industry today is pretty much totally electrified. All the equipment that they use is electrical. They have large exposure to the energy markets. They consume a lot. It accounts for something like 10% of their costs. In addition, they own a lot of land. There is now a call, actually it's beyond a call from the Department of Energy with a lot of money on the table to get mining companies to install solar panels, wind turbines on their land and to either use the power or sell it. It's all very timely. Next slide. So this summarizes what we have been doing. Us, meaning Andrea and Alexandra and I, we have been talking to a number of mining companies, steel companies, and so on, in terms of what I just said, trying to explain these concepts, that they are very exposed to energy markets. Their competitors are going to be looking at financial risk, taking positions, financial positions in the energy markets to hedge their risk in terms of the cost that they're exposed to. Looking at installing solar panels, large-scale solar panel deployments or wind farm deployments to both use the energy and sell it and again hedge their risk. At best, as I said before, at best, there in heavy industry, there seems to be very slowly emerging understanding that they have to change their practices. If you talk to them, their initial reaction effectively will be to say, why? We'll just keep buying power. Why should we even think about this? It's an anathema to many of them to think about finances, financial risks. They don't want to deal with it. Perhaps it'll and therefore be engaged in analytics regarding financial risk and the implications as to actual physical risk. Maybe in the next year or so, that'll change. As I said before, in our experience with Perform, it's been the case in the last 6 months that there has been all of a sudden a huge change in the attitude of the ISOs toward these issues. At best in the last 9 months and not before. And maybe in heavy industry, the same will happen moving forward. But we are collaborating with a couple of mining companies. We are still talking even after the work was done. And we hope that they will keep partnering with us. Next slide. Okay, So as I said before, mining is a very energy intensive industry. The exact percentage is hard to pin down depending on who says that, but it's large. Mining companies have begun to focus on these issues about becoming more efficient in their use of electricity, reducing their carbon exposure, being more sustainable, and so on. So in the study that we conducted for one of these mining companies, and I'll provide details in a minute, we are trying to see how to change the operations of a mine in order to better take advantage of cheaper energy prices when there is more renewable output, and thereby both benefiting from the reduced cost and also becoming greener, both being goals that they are aware of. Next. Next slide.
Oh, you have to speak into the
Oh,
mic.
next slide. Okay, so we have actual real data. All the data is 100% real. So this is not an academic model. And we're going to look at the seasonal fluctuations in price that arise from having renewable output being more plentiful at different times of the year. And also, so this is being done on a seasonal basis and also on an hourly basis. The mines schedule their operations first on a very long-term basis, and then they refine it on an hourly basis, much like the energy markets operate. The goal is to see if, in fact, the production can be shifted from periods of whereas both there is high electricity demand and low renewable output to the reverse. So in terms of the cost that the mine pays, the pricing that they pay depends on overall load, and they would like to shift operations away from that. So that's one leg here. But also they would like to shift up operations to periods where there's more renewable output and get a secondary decrease in their cost. Next. Okay, so the physical setting is of a mine that's located in this area called the Powder River Basin. This particular mine that we are going to talk about is a coal mine. Okay, there's some irony that renewable output is going to be used to power a coal mine, which will sell its coal to a utility. But this is the way that things are. This is an area where there's a lot of coal, and it's a high quality coal, better than in other places. It's highly productive. Of course, coal demand has been declining. The mines are aware of that. The mines might become energy companies using their land as they install panels and wind farms. And this is the biggest coal mine is a surface coal mine is located there. And there's a company called Peabody that is involved in this. That being one of the companies that we are dealing with. A big coal mining company. Next. So where do they buy? So as I said before, the mines are electrified. Right now, they're buying all their power from an energy company, Powder River Energy Corporation, Precor, through bilateral agreements, and they get a price schedule, a time-dependent, peak-dependent price schedule from Precor. And they are both, seasonal and peak aware. A given mine may have a very modest power consumption, maybe 1 megawatt, or substantial hundreds of megawatts. The ones that we are dealing with are big. Next. So now, the way that we are going to be doing this is that there's an optimization problem that the mines are solving today. This is mines all over the world. They solve very similar optimization problems. We will model the greater availability of cheaper energy by modifying the cost function. It's a complicated process. The cost of the activities that they're engaged in depend on many factors, energy being only one of them, and very, very time dependent. And so that has to be done with some care. Now, the mines have excess equipment, excess resources, so there's the possibility of shifting activities from one period of time to another. You will see the structure of this optimization problem that they have to address. It's a very complex problem. The operations of the mine are complex. It's not just one simple activity. And so there's a question even before you do any of this as to whether you can take advantage of temporal improvements in the cost structure. You know, you have to have the flexibility to move operations. This being not simple at all. Next. Oh, here we go. All right. So here I have a couple of pretty pictures. On the right, we have this thing that's called a dragline machine. That one looks to be on the small side. I saw one whose consumption was 6 megawatts. That's a big one. I should say I saw a scale model of one. And on the right we have oh, that's another truck and yeah, no, that is a truck. So one of my colleagues, Andrea, actually drove one of those trucks while in college to supplement her income, you know, as opposed to working in the cafeteria or being a TA or something. You know, she worked at the mine, driving one of those trucks. They consume vast amount of powers, and on the right you see a typical picture. You see a schematic in a few minutes of what a surface mine looks like. They have exposed a seam of the mineral, and then that wall is going to recede as they extract it. Next. Okay, so here we have the schematic. The mine is working from left to right. On the far left, you have land that has already been reclaimed after the mining has happened, and that takes several stages. And on the right, you see the actual mine in operation. That machine that under the wording that says coal mining, that is the dragline, that is extracting the mineral. And more to the right, you have equipment that is used to expose the mineral, remove the topsoil and all that. And I believe pretty much all the equipment is electrical. There are other mines, you know, in terms of the companies that we are talking to. There's what they call hard rock mining, which is other minerals and metals like gold or diamonds or uranium and so on. And some of those mines are subterranean. And even then, all the equipment is electrical. They need ventilation and lighting and such, and equipment for hauling the mineral to the surface and then away. Next. So the optimization model that I'll describe in a minute, which again, I want to stress, this is not an academic exercise where, you know, we came up with the optimization model. This is the model that gets sold everywhere. It does the following. You have this a mine. The mine has been studied in advance by doing soundings and such. Imagine this 3D object that is underground right now, and it has been divided into blocks. Each block is, you know, something like, you know, 20 feet by 20 feet by 20 feet. And there may be 100,000 of such blocks. And you have to produce a schedule for extracting those blocks. Okay, and it has to be a physically meaningful schedule. You know, if you want to dig this particular block, well, it has to be the case that you have already dug whatever is on top of it, for example, to be able to get at it. And then there's equipment availability, and it has to be staged through time, long period of time. And so as you extract the mineral, you're getting revenue from that, but also you're paying a cost. And the optimization problem is one where you want to optimize the net present value, subject to all the constraints. And there are many, and we have only a subset here. And there's a paper that has all the details. Next. And so this is the just to show that in fact I am an academic. Here's the obligatory formulation. There are many variables in here, but the Y variables, these are binary variables that says, okay, for a given block or activity, as I refer to it, in a given time period, it's 1 if that thing is going to be removed, extracted at that time period. And then let's see, at the bottom, the last constraint is one that says mathematically what I described before, which is that there's a precedence order. Before you extract a given piece of dirt, you must have handled whatever is above and kind of in a cone. But then there are all kinds of other constraints that describe the resource utilization that is needed in order to remove, to carry out the mining in terms of the machines that you have, staffing, and so on. Next. Oh, it's already, oh, goodness, I thought I was doing slow. Next. Oh, next. Okay. And so following the way that the mining industry, so again, this is a problem that we did not formulate. Okay, the only thing that we changed is the objective function in discussions with this energy company. You know, how would they price cheaper energy? But this is all by all mines. It's a huge binary mixed integer program. It cannot be solved with the usual solvers that we know. There are third-party software companies that sell software for handling this. They solve the continuous, the LP relaxation, which already can take several hours, and then they use heuristic to get a binary feasible solution. Okay, and as the way in terms of how the industry works, so here we are solving a base case problem that is not energy aware. Okay, this is how the mine operates today. Then we solve a medium term schedule. It's a 2-year schedule. That's considered medium term. On I think we did it with daily fidelity. And then we also solve what would be the switchover problem, where let's say with over 2 days, you look at an hourly model. Next. Okay. So here we have some of the output. I think there's a typo here. What this means to indicate is not compared to. What this means to indicate is what the energy costs are relative to the base month of August 2022. This is the renewable being modeled here is solar panels, and August is obviously is going to be a cheap energy month, a lot of sunlight, and so on. But some months are known to be not as good as others, and this curve shows that structure. Next. Okay, now we have the actual results of the output. In black, what we have is the, so what this is showing is the kind of cumulative activity in the mine, how much mineral, think about it that way, has been extracted. So it's growing as a function of time. And in black, you have what the operations of the mine would be, if not energy aware. And in red, you have the energy aware schedule. And what this plot shows is that in the months that are expensive, where there's less renewable output, the red schedule does react to that. and the schedules less operations, and it seems to shift them to the white months where energy is cheaper. Next. Okay. And this reinforces, so this is now an accumulative output. It reinforces the what I showed before. On the expensive months, which are in green, the drag line basically slows down to a crawl. Instead, it shifts the operations to the other months. So far it looks pretty good. Next. Okay. And so in summary, most of the activities, or a lot of the activities of the mine, especially the more energy intensive, are in fact shifted to periods with high solar. There are details that we cannot present here for lack of time about how the availability of cheap energy is being modeled in the objective function. It's basically cost and a cost incentive. But of course, there, if you're a big company and you shift operations from one period to another, you have to take other costs into account, like employee cost, which we did take into account. Next. Okay. And the curves to look at here are the red and the green curves. The red curve being the higher fidelity short time period schedule, which is more aware of fine data details. And you can see that it really is taking advantage of the high solar periods. It really ramps up production, then it does very little otherwise. Next. Okay, so now having said all of this, in terms of the numbers that we saw, looking at the numbers in detail, it seemed that the magnitude of the benefits that the mine would derive was smaller than what we had originally envisioned in terms of the potential savings because of cheaper energy and how much they pay for energy today. And so, and this is not due to lack of flexibility on the part of the mine, their ability to shift work from one time period to other time periods, even though they really have this complex problem with all those precedence constraints and such. It's not due to that. So what is it due to? Well, this is a mine, they're extracting mineral, it cannot be stockpiled, they have to send it away, and it's sent away by train. But the trains don't have the flexibility to shift their operations. The trains are the trains. They have their railways and their cars, and well, can they actually be effective in shifting operations? Now, presumably, if the mine were willing, and they would be willing, to share some of the extra revenue that they're getting by shifting operations to the trains, perhaps the trains would adapt their schedule. But the mineral is being hauled to somebody else, a user. They have to be able to be flexible and take the material when it arrives in a different schedule that it has been for decades or longer. They are going to use the mineral, whatever it is. In this case, it's going to go to a utility. But if it were some of the other cases, they have to be able to incorporate that into their manufacturing on a different schedule. They have to be able to reap the benefits. And maybe they could, if they could share some of the benefits, but they are probably not the end manufacturer. This is part of a supply chain. They will have to take whatever they did and ship it away. So their shipper will have to be flexible as well. And then the eventual end user that receives the material, they will have to be flexible as well. So you have basically, this seems to call for an entire adaptation of a complete supply chain, which when you think about it, does make sense. And I think that this complexity may account for some of the reluctance that these companies have shown up to now in terms of being more energy market savvy and flexible and so on. And with that, I will end my talk. I think I'm out of time.
Well, thank you so much. Do you have questions for Dr. Bienstock?
Hi, Jesse Holzer, PNNL. Hi, Dan, this is really remarkable. I'm going to ask a really detail-oriented question, and I'm able to do that because I worked with this same company actually at the beginning of my optimization career. I probably know some of the same people that you are working with. So
which one, Precor or the other one?
Peabody.
Peabody, yeah,
Yep,
okay.
Did you get into anything about the blending in that you mentioned?
So I should say Peabody is another one called Newmont. You probably know them, and Entech.
Yes.
These are all big companies in the West.
Right.
Okay, I guess everything is bigger in the West, but yeah, these are very big companies. Yeah, blending constraints. So that's one of the things that makes that optimization problem difficult. Yeah, we're looking at it. We as Andrea and Alexander and I are looking at it, and we have definitely talked with Peabody about that. This is what makes that problem hard. Yes.
Mm-hmm.
Yeah.
Cool. Okay.
But I don't have any insights right now. I have a student who's looking at this. Yes.
Excellent. Thank you.
Yeah. No, that's a great question. The word blending was in the slide, so what Jesse asked is. Thank you.
Okay. Well, you said that you cannot solve the problem with the usual thing. What did you use then?
Is that a lead-on question?
No, I'm just really curious. You know me.
So the big multi-year problems that they want to solve for a big mine, they will easily have 300 million variables, something like that. So even just solving the LP is a challenge. Now, it turns out that about 15 years ago, I had a PhD student who worked on that, on the LP relaxation. And so the mines are using our algorithm to solve the LP. And then there are heuristics that other people have developed that round that with some degree of success to get a binary. They need to get a binary solution, when do I do this? They want to get so that's what they do. That is what they do today. The LP takes a few hours as opposed to a few months, and then they're round. Thank you.
Anyone else? Anything online? Okay, let's thank Professor Greenstock. And I'm just going to make a few final announcements. Let's see. Okay, so yes, that wraps the last. Yeah, so that wraps the last session of a very productive and fun conference. So extra special thanks to everyone who stuck around to the end. Thank you to all the presenters, all the attendees, both in person and online. Special thanks to Masoom Malla. He is with our IT. I've been involved with this conference for 10 years, and we've had a few hiccups, but this has been the smoothest one yet. So thank you, Masoom. And then behind that black window over there, there's a bunch of other IT folks. Rob Hicks, Levon Harold, Darnell Fox, and a couple others. Of course, the team, Alex Smith, our overall organizer. So let's give it up for him. Lisa Sosna, Caroline Engel, Daniel Wagner, Monica Ferreira, and our manager Elizabeth Topping back there. I feel like thank you. So all slides are currently posted on the FERC website. Recordings will also be posted. We encourage you to share your presentations with your colleagues in the industry, and when you do so, you can also advertise our conference with your colleagues as well. If you have any feedback for us, please let us know. Anything else? Okay, if not, we can conclude the conference. Thank you again, safe travels, and we hope to see you next year.
Thanks, everyone.